Welcome everyone. Pleasure to have you here in Stockholm, in this beautiful building. Yeah, I don't have so much to say. First of all, I want to thank the Royal Academy of Sciences for hosting us in this beautiful building, and Peter, who's been very, very helpful throughout the weeks. And KV also sponsored the lunches and some of your hotels. So I think you deserve a big thank from all of us. And Peter, maybe you want to say a couple of words just to...
Yeah, I can say a few practical words. We have, as you can see now, Arnaud does not wear a headset. And we don't need that here because we have a voice lift audio system yeah. so we don't need to pass the microphone around or use headsets or microphones down the podium. You will be heard when you have discussions and when you lecture. There are microphones everywhere here in the ceiling. Lunch and fika, coffee breaks will be served just outside. We also have a garden. We are doing some rebuilding there, so we have a scaffolding, I think it's called, the building. But you're free to go out there and sit at those tables that we have. Some of you, or just get some fresh air. We have a dinner tomorrow evening. And that will also be just an adjacent building, so it's also in the premises here at KVA. And tonight we have an outreach event. I'm sure you all know that. So those of you who want to stay for that are, of course, most welcome. There are room from 6 p.m.
And you said you would show us around maybe before the outreach event?
At 5 p.m. Or shortly afterwards. I can just say a few words and show you the session hall where the Academy have their meetings and where the press conference for the announcements of the Nobel Prizes in physics and chemistry are held every year in October. So that could be a nice room to see, but there is not much else to see around here. There's mostly office spaces, and we won't go in there, but the session hall is a bit of a treat. So I will show that.
Cool.
Thank you.
Okay.
Welcome.
And then just one more piece of information. If you haven't grabbed your badge, it's on the table over there at the entrance. And we also have the presence sheet that will be passed around during the session and then probably again in the afternoon for people who arrive late. Ilaria, do you want to add anything or?
I mean, there isn't much else that I can say apart from welcome. I mean, like you organize locally, so you are better. I don't have any practicality to add, but I mean, we had some difficulties with flights and everything, but I'm sure that this meeting will go well. So thanks for coming.
Yeah.
And
there could be issues with the subway today. They've had a big issue over the weekend. They are still recovering, so you might have to wait a little bit for the subway. As Ilaria just experienced.
Yes. I made it.
Yeah. Okay, yes. Good. I will also take a few pictures once in a while. But if you don't want to be pictured, you just tell me no. Like that. Okay? All right. Enjoy the meeting. First speaker. We need a chair as well. Barry or Francesco, do you want to chair? Okay.
Yeah, so first up we have the working group 2 speakers, and Tobias is going to tell us about seizing the moment with AI in HEP. So yeah, it's all yours, Tobias.
Perfect. All right, thanks a lot for having me and for organizing for this wonderful event in this beautiful setting and for the great weather that I enjoyed over the weekend. So I would like to take you on a little journey and ask a few questions and maybe have as an opportunity to see how do we do physics, right? And is this a good moment to maybe think a bit more deeply and see if we want to change anything in our fundamental operating way of doing physics. So in this sense, I will ask a few more open-ended questions that we usually don't ask. Instead of, how can we improve this particular flavor tagger? Ask questions like you will see them here on the next slide. And I will also go back and review a little bit what has happened so far. And yeah, indeed, we have published thousands of machine learning papers in the last 5 years. But so here, like the hypothesis of this talk, have they really changed in a fundamental way the way we do physics? And if not, then why not? And what would it take to maybe change this now? Okay, so let's start in part 1 of 3 parts with defining the physics problems and reminding ourselves what makes fundamental physics, high energy physics particularly unique and also uniquely hard. So here a few of the things that you can think of. So first of all, we don't have fixed size vectors or tensors, but it's more like a variable size number of events and a variable size number of tracks in a jet or particle objects, and then a variable size number of hits. So rather than tensors, it's more like sets, trees, graphs. And the second important thing which distinguishes us from many other disciplines is that we have a first principles forward model. So we can, from first principles, from our standard model of particle physics, all the way propagate forward to what we expect to see in the detector. And of course, we make use of this in all our physics analyses. So this gives us, in principle, an unlimited amount of truth-labeled data with, by design, perfect truth labels, something which you don't get so easily in other disciplines. But it comes as a cost, right? So it has a compute cost, of course, and it also is not perfect. So there is a domain shift. We don't recreate the reality in a perfect way, and that's the source of a lot of our work, where we have to actually figure out how to assign systematic uncertainties to these differences. And then another one is we look for very rare events. If you look, think about the Higgs cross-section as compared to the inclusive one, it's 1 in 10 to the 12, and for many new physics searches, it's very similar kind of ratio of signal to background. And then maybe the most special one that we maybe don't appreciate so much is that, in contrast to people who just care about prediction, classifying images, dogs versus cats, we actually don't care what, I mean, not ultimately care what we see in the detector, we care what is the fundamental theory of nature. So I want to go back and do inference, it's not prediction. Okay, so this is here directly connected in this sketch. See the forward model, which gives us the likelihood, the probability to observe the data given the theory. And then in this, we have a lot of latent variables that are not directly described in the data, like what happens in the showering, parton density, hadronization. And then the goal is to go back and do inference and get the posterior, what's actually probability of theory, both standard model and BSM, given the data. And of course, this is part of the more general scientific method, where we have the so far mainly human creativity and genius coming up with theories such as the standard model or BSM series, and then we have the data which gives us the evidence, and we're trying to go through the cycle. And what I would like to discuss in this talk a bit is how can we make this more efficient, right? Is there a way of automating, scaling up the way we run this cycle? So, and I want to focus on discovery. So this is actually nice that we changed the agenda, because like we have a talk on foundation model next and one on anomaly detection. So it's a nice preparation for both of them. They will both feature in my talk as well, both of these topics. So here is the discovery pipeline, and you can just replace discovery by measurement, and it will be slightly different. So most of it stays the same. So here are the main blocks. So I chose to call the first one simulation, based on this beautiful forward model we have, Monte Carlo generation. Then we have the reconstruction steps, or the physics objects, where we try already to do a first kind of inference to go as close as possibly back to what interests us most, the hard-scatter event. Then we have to deal with this class imbalance. So we need to dig out the signal from the background, do a selection. then typically we do some sort of a fit, likelihood based, and there also the domain shift comes into play, because it's based on the forward model, where we try to then fit the data and see if we can extract the signal, and then do finally if a discovery was set limits based on a statistical framework. And then you see in blue below that in all of these blocks we have used ubiquitously machine learning to improve, machine learning fast surrogates, graph neural networks, transformers, classification, simulation-based inference, normalizing flow, anomaly detection. However, the pipeline itself hasn't changed. So this is the point I want to make on the next slide. So machine learning replaced the components one by one, but the pipeline stayed the same. And now the question is, can we maybe in this moment change the pipeline itself? So coming to the part 2 of this talk, a little look back what has happened so far in the last decade of machine learning in HEP. And here again, sort of like a little provocative question, has it been really worth it? So let's look at the HEP-ML Living Review. It's a great source to give you an overview of all the things that have happened in the land of machine learning in high energy physics, going back all the way to 2012 when the deep learning revolution started. And what you find there is 15 main categories. Literally every major machine learning architecture is represented in high energy physics. And this is really a remarkable activity. The plot is from April, so I expect 2026 will probably overshoot 25 again in the number of papers. So these are really thousands of papers. And let me go through a few of these success stories. So not all of them have made it back to experiment, but many of them. And these are real success stories I want to share with you as examples. I'm biased here. I show mainly work that I've been personally involved in. And since I'm on the Atlas collaboration, I mainly show you Atlas results, just so you can take this as a disclaimer. So this is about flavor tagging, where you see here over the years how we improved flavor tagging by basically improving the machine learning architectures, going from a simple deep learning feed-forward network in 2017, when I already thought, okay, we're done with flavor tagging, this is all we can do. But no, by going to better architectures like recurrent neural networks and deep sets and graph neural networks, and then GN2 actually stands for transformers. You see in this particular metric, which shows you the rejection for a fixed B-tagging efficiency, that we can improve the rejection of background by a factor of 4. And it looks like this trend continues. So we see a kind of scaling loss in this classification task. Now this is the default tagger for all run 3 analysis, and also impacts all analysis. If you make predictions for high Lumi LHC, you see this gives you equivalent, depending on the analysis, if you have for VH or to CC or some other Higgs to BB, maybe plus TT bar, or for like order factor of 2 equivalent increase in luminosity. I do want to mention some CMS, a very exciting tagger for me. I like this very much, a generic tagger where this is also pre-trained, so this is kind of a reference to foundation models, basically on I think 300 classes. And is shown to be then, if you do fine-tuning, gives you an improvement over a dedicated tagger. So I think this is something we in Atlas should do for sure. So I'm very excited about that. 2 more success stories. One is our flavor tagging. We do train on the data where we have truth labels. So this is the Monte Carlo simulation, which has a domain shift. So it's not perfectly describing the real data. So we need to do some kind of calibration. In the past, we have done this with scale factors, where you assign weights to each event or each jet. And this is a new technique where you literally transport your simulated event to look like the real data event. And this can be done in Rico space, so it's done in the space of the probabilities to be a B charm light in the 3-dimensional space, but has also been shown on mock data. This can be also in the latent space, for example, of a foundation model. And then finally, as an example, I would like to zoom in on anomaly detection, or let's call it more efficient way of searching for new physics. And there we have done a lot on both unsupervised, but here this is a weekly supervised search, which probably will be featured in the last talk of this session. Okay, so I think it's really worth celebrating. These are real advances. They improve existing steps, but in this context of asking more wider question, can we do better? It hasn't really changed the way we ask questions, and it also hasn't changed how many questions we can afford to answer. So I want to in particular home in on the how many, right? So what's the limitation? And we will realize that that human is a bottleneck in this, right? So we'll come back to that. Okay, so in summary again, so very valuable but incremental. Individual steps of this pipeline have been improved. The pipeline itself has not been changed. We haven't changed what questions we ask or how we can ask them. In particular, no new particle discovered by machine learning, no new measurement methodology enabled, and no paradigm shift in the way we do analysis. So I'm going to use searches for new physics as an example. And if you just think about how many possible models and chunks of data you could test for the presence of new physics, and you can do this. This is a different kind of making different kind of assumptions, but you end up that in all of these back of the envelope estimates that most of the signature space is still unexplored. So if you think about boxes here, most of them are still empty, and this has been done in the past by looking at some, for example, here resonances, and you look at just all the possible resonances you can search for, and this is already a few years old, but hasn't changed all that much qualitatively, the number of empty cells versus the number of searches which have been carried out. More recently, people have also looked at the fraction of 3 and 4 body decays, and maybe a question, if you know the answer, you don't have to answer, but what do you think, how many of the 3-body mass spectra have ever been probed for resonances at ATLAS? If we just consider electron muons and their charge, and then light and B-jets, and also missing ET, yes or no? Any wild guess? What's the fraction? This is an ATLAS. I assume it's not all that different. It's not 0, so it's a bit more than 0, but it's still a small number. Yeah? So it's only 15%. So, okay. What about, do we really know that these are the 15% which matter and the other 85 don't matter? I don't know. So the question here is, why is this actually so little, right? And a related question is, have you ever worked on an analysis which took more than, say, 2 years? Maybe sign of hand? Okay, so this is kind of a related question. Does it really need to take so long? So we'll come back to that also in a second to this question. And related to that, don't we have a duty to be more efficient? In particular, since our funding is essentially a gift, right? We have no direct real applications. What we do, if we measure the Higgs boson and its mass, yes or no, it doesn't change anything for humanity other than maybe their curiosity. Right. So some honest questions here. Does a search need to take 3 years and 5 people FTE? If you multiply this by the number of search papers we have, you end up order of magnitude 10,000 FTE years for searches. Is this well invested the way we do this right now? And the last one is also a good one. How much FTE does one calibration loop cost? And again, I don't have an official number here, but a colleague of mine recently made an estimate. Do you want to take a guess? Like all physics objects.
With overhead or without overhead?
An overhead, how do you define overhead?
Whatever the university adds on top.
Oh, got it. Yeah, 15 plus or minus 15% doesn't matter. What does your gut feeling tell you? Okay, I'm not going to quote the person, I'm not going to say who said it, but what I heard is a number of 100 FTE years. Well, it's like a non-negligible amount of. So is this really necessary? I'm coming back to this as well. Okay, so what I rather want, or let's ask, why is it not possible to have like a button which says recalibrate everything, right? So you put input data Monte Carlo, and then you get the calibrated physics objects, uncertainty bands, validation plot, the whole list, one click, full automation. Why is this not possible? I mean, yes, there are many reasons why this is not possible right now, but like I'm just asking, is this maybe a good moment to think this as this becomes a real target, getting closer to something where the human is not the bottleneck? Because otherwise we will lose access to our data. Like people are saying, oh, we can't reprocess because this is going to be another 100 FTE years order of magnitude. And there, we should look a little bit at industry. Meta's biggest asset is their user data, and they make sure it's accessible. Everybody can just press a machine learning button and reanalyze the data. We should do this for our data as well. Okay, so maybe there is a resource paradox where we have 4,000 people in Atlas, similar number in CMS, but at the same time a chronic person power shortage. So let's look at our colleagues from economy. They have a nice model of what their hidden costs are. I mean, I know there's service and we work on upgrade and all this, but I think this is maybe more useful. And one thing we often overlook is called the opportunity cost, and I'm going to interpret this again in the context of searches. Like think about every FTE we deploy on a deeply optimized search for your favorite BSM model. But this FTE cannot be used to probe an unexplored region. You know, we heard about 85% of, for example, for these three body final states. So we operate as if we had infinite time, infinite compute, infinite person power, and we don't, obviously. So taking opportunity costs into account, optimizing in the presence of limited resources, something we don't do consciously as a community. Maybe one person by person, but you need to really think all of us together. Another one is sunk cost, right? So we have to define a model. Now we have an opportunity to do something better, so then we have to get rid of the old model. Once the new one is fully validated, we have to switch. It's a must. And then finally, this goes back to the calibration loop. You know, again, comparing with industry, they built their first airplane, takes a lot of time, but the hundreds is like, you have your pipeline, all is done. Why can't we do this for our calibration? So maybe there's a structural problem. And before we talk about the how, maybe it's also interesting to remember why we actually do physics, right? So something I realized I don't ask myself every day, but it's a good thing to remember. And it's definitely not, so here's actually a nice paper which discusses this in the context of astroparticle physics. And we often say, oh, we just care about the science. But if we really cared only about the answers, then it would be much better to start a hedge fund, as Jim Simmons did it, and get much faster the answers than if we work on it ourselves. So I think it is definitely not turning the crank and do something boring. So you want to do something meaningful, right? You want to do something creative. And I think we all have the best intentions to do the best possible for science, but unfortunately, it has become very complex to do analysis in Atlas or CMS, and we have to do compromises, and the compromises then lead oftentimes to conservative inertia, like, oh, well, everything new, no, it's complex enough, let's keep the way we're doing it. Since it's so complex, we focus on a small thing, and I think, okay, I know how to do this, let's reinvent it again from scratch, or we just over-optimize too much on something where we could use the opportunity cost we forget. So, back to analysis and maybe to searches. How many different kinds of analysis are there really, right? If you think about it, we treat every analysis as if it was an individual thing that needs to be treated completely individually. But here the claim is you can boil it down. I mean, this list is not complete, but you can boil it down to a few different kinds of analysis. And then the opportunity is you build each of these pipelines once, and you configure it many times. And in this way, be ready for automation, scalability. So now back to the last part, the vision. How can we turn this to reality? I think it's a duty, if you think about opportunity costs and the other costs, and not a luxury to use our resources wisely. The physicist has still a reason to be there, so we cannot fully automate yet, and we shouldn't, so we have to build the right infrastructure. Then we decide what are the questions worth answering and with what level of resources. Again, the deployment consciously. We are the physics judge, we are the ones who critically evaluate, but what AI brings, in my view, is automation scaling up. Okay, let's zoom into searches as my favorite example. So I want to go to a scalable autonomous search, and I give you here a wish list of things that I want to see for discoveries. Here's a little sketch which shows you in yellow dots the way we do physics nowadays. We have a model in mind, and we do a dedicated, deeply optimized, supervised search. And in green, you see kind of a sketch of all the possible new physics phase space. And then maybe in red is the new physics realized in nature. And then instead of the yellow dots, I'm more looking for something like this red area where we can have high coverage and keep at the same time a high sensitivity. Automate the way we do background estimation, the way we do systematic uncertainty propagation, scale the statistical frameworks, and then have this human in the loop to check are the anomalies, critically evaluate and judge if this is real or not. But it should not become the bottleneck. So the other things are automated and scaled. You can think of it also in the way of data, and then we make assumptions what new physics is, and this gives you the inference. So this is kind of the link to simulation-based inference. We want to systematically scan that. The human designs the pipeline, and then the machine is used to automate it. So if I had to bet on which are the things that matter for this revolution, so foundation models, we'll hear about it. For me, the main asset of foundation models is that you do an upfront investment, you pre-train once, but then you get the return later by doing, for any downstream task, you have much less work to do. So this is a possibility to eliminate redundant effort. Foundation-based inference, you hear about it tomorrow. I'm not going to talk about it. It's the one unique way to go between in your scientific method from the data back to the theory, right? And then agentic AI is for me the way how to, in a controlled way, automate it and scale it up. So foundation models, again, we hear in a moment all the details about it. The main idea, you go from a task-specific model to a pre-trained model where you would then have the downstream tasks much more easily accessible, all sorts of ways how to train this in a self-supervised way, and the main prospect, eliminate redundant effort, pool resources, shared infrastructure. And this is for me a beautiful way how to put this all together. You can have this pre-training on data, on simulation, and then you create a backbone from this, and then you have the fine-tuning step for all your downstream tasks. And you can use labels here. The pre-training, you don't need labels, but you can also use, of course, truth information as additional physics targets. And you have options to further link this to language models, but primarily you want to train this on physics data. Okay, so let's put it all together. So here, the current way, we have these many different individual analyses, simplify it, one common set of pipelines, and then you can scale this up again by using agentic AI. So I see it a little bit like you have a Lego with well-defined interface. When you define the interface, then perfect. You can configure all the Lego pieces and have more flavors of it, and still have in a controlled way build very fancy integrated systems, very fancy pipelines. So that's the last slide. So let's make this real for an example of looking for resonances in a way where you can easily scale this up to basically search for any resonance. So let's build this. This is just one example how one could do this. Let's build this on histograms of mass spectra, which can be configured. So the human decides the catalog of signatures and which objects you want in there. And you say, okay, I'm going to look in the beginning for narrow resonances to keep it simple. Then you repin according to the mass resolution of your n-body final state. Then you still want to input like the class imbalance, right? We're looking typically for a signal buried under a background, so somehow you need to reject the background. And here is where you have to have some bias. What is it? Is it going to be a theorist who tells me, or is it weakly supervised or unsupervised? Or you take all the excesses and build a model for it and then use that to inform what kind of selection you want to do. So hopefully then we have a signal-enriched histogram. then you need a universal way of estimating the background. So you can scale this up, so you don't need the human as a bottleneck. This can be, again, configured. You can do a fit or a Gaussian process regression or some smoothing. And again, you want to do this in a way so the rest of the pipeline does not need to know what happens inside this module. You have some automated metrics which tells you, is this really a smoothly falling background? Uncertainty control, again, you want to avoid that the human has to go in and hand tune. Finally, you have a step, again, something that you have to be able to scale up, statistical framework, FAIR, Rihanna, and then do interpretation. For example, have common benchmarks so we can the whole community compare to the benchmarks, and then some fiducial limits the way we do. Ideally, you would also integrate this with SBI, like a universal SBI, which brings us back to the theory space, and the foundation models could go there to inform the way we do these BMS, BSM lenses. Okay, so most importantly, this is a single scalable infrastructure where you can configure the assumptions and then have agentic AI plus humans to systematically scan all this space of assumptions, of theory assumptions. The payoff would be that we could now go and look at all these boxes and very efficiently look for them, and it would take not 10,000 FTE years, but maybe only months. So in summary, this is my last slide. ML and HEP has been extremely valuable, but still incremental. So the opportunity now with agentic AI is to go to really an AI native high energy physics. If we start this now, we could be ready for run 4 maybe. The three big ones I see is foundation models, simulation-based inference, agentic AI, combining them in a pipeline like I demonstrated. And the human still has a raison d'etre. It's there to orchestrate and to also, in a controlled way, go from this, go to an agentic automation and scaling up the analysis. Thank you very much.
I think we have time for some quick questions. Everybody? Yeah.
So as I understood, I can just speak up if it works.
Okay.
Okay.
Yes.
So you said we waste a lot of times on these repeatable pipelines, but I think what really is happening there is that a lot of these tasks take so long because it's most often students who do these tasks for the first time. And basically them doing this and also all the other things where you said, okay, we don't want the human to look too closely, have the enormous benefit of teaching young physicists how actually the physics works, which in the end is needed to cross-check what the AI is doing. And actually, I think where we lose way more time at the moment is not writing all these loops. Of course, we lose time. It's not optimal, the system. But especially in experimental particle physics, usually the time where we lose the most is in the review of the analysis, which is at the moment biased, it's slow, it's very complicated. But it's also necessary. If we now just streamline everything, we neither have the people to do the cross-checks and basically also make the cross-checks less viable, so we just remove out the quality control. And I don't think this is a good idea.
Okay, thank you for making this first point. I fully agree with you, right? So we have to educate. We do physics by people for people, primarily. And this means we want to educate the students to become either physicists or also prepare them for the world and the challenging problems, because most people leave the community. But I think we're disguising teaching. We say we teach them, but we give them a boring qualification task. I think that's just not well spent on this. So I think we should take teaching separately as a question. How do we form the best new generation of particle physicists so that they also learn something and do it in an interesting way? And then all the kind of boring service tasks I would outsource to the machine.
Yeah, but you now said basically to outsource the whole pipeline and just occasionally look on the side as a human. So
well, the human will have enough to, yeah, so the review you mentioned will become even more important. So I think we rather should educate the students to become good judges, physics judges, and look at the few key distributions and metrics and be able to judge, is this reasonable or not? So the review would probably still stay very human-centric.
But then I have a follow-up question. Isn't AI notoriously good at hiding, learning the metrics it's evaluated on and hiding basically now what it does wrong?
Well, that's why you have to have this controlled where the agent cannot do anything across all the modules, but you're able to still stay within a module and can evaluate what happens inside. But yeah, so there are hallucinations, sycophancy. These are all dangers we have to think about and anticipate and prepare ways of making sure this doesn't happen.
You started with a provocative question: how do we change the paradigm of how we do physics? But in the end, you kind of boiled it down to making 100,000 FTE years into months. So it's again a question about efficiency mainly. I don't see how it changed the question we ask at this point.
Baby steps.
Okay.
Yes, but okay, but no, I would be happy to go further. Yes, indeed. So there's the FICA coming up, and so yeah, if you have ideas, I'm very no.
I think we've had one more.
All right, so Tobias, I do have a more conservative perspective on this and how far to put AI, but I do agree with you that it's so advanced that it has to be integrated into the pipeline more. So my question comes down to, where do the accidents fit in the pipeline? So one of the cool things about doing a really, really good analysis, either an experimentalist or a theorist, are the silly mistakes you make that you realize, why does this work? Oh, I made a mistake. Hey, this really, really works. And it's this sort of serendipity aspect that makes some good analyses work better than anyone could ever imagine. How, in your mind, how do we keep that serendipity in the pipeline when we're releasing, I'm not even sure if you have a good answer, but when we're releasing control over the pipeline, building up the analysis and just outsourcing this, how do we keep that?
So I ask myself the same question teaching my students at the university, right? I want them to use all these models, but I want them to use the models wisely. So one possible way is this kind of Socratic approach where you say, okay, this is my human idea. And then you challenge the AI to tell you what could be wrong or how could this be done better. And then you take this and say, oh, and you think further about it, and then you put more human input. So it's like really an exchange and not just like, I turn off my brain, the machine tells me everything. So if we go in this direction, this would be a disaster, of course. So the human has to, take responsibility for the analysis and make sure everything is understood.
Okay,
That would be my way.
So in some sense that the AI setup, your agent's going to make mistakes and realizing, hey, that mistake actually might have some sense to it. Okay.
I don't know.
Yeah, no.
That's great. Let's thank Tobias again. Great start to
Sure, pleasure.
next. So our next speaker is Anna Holland, who's going to talk about foundation models for that. It's a great follow to Tobias' topic. So yeah.
Okay, thank you, and thank you for the invitation to come and speak here. So I will talk to you about foundation models, and thank you, Tobias, for introducing it. So yes, essentially this is maybe not necessary then, but in principle a foundation model is a large machine learning model that you have trained on broad data, whose representations you can then use for different downstream tasks. And it can be multimodal, like I've shown here, a couple of different types of data, but it doesn't necessarily have to be. And the goal, or the sort of what we are looking for in foundation models, is to get this representation, a representation that is rich enough and general enough that we can perform these other downstream tasks using those weights. So the pre-training and like all of these things, it doesn't really matter in itself. All we want is this representation. So the most famous foundation models are, of course, large language models. You all know them. They train on enormous amounts of text, the entire internet, books, everything. And the pre-training task for those models is, of course, to generate text, and which they can also then repeat, but they can also do sentiment analysis, they can do coding, they can do translation, and they are becoming real generalists. Some are also trained on images, and then you also get image analysis capabilities, generative capabilities, and so on. But there's, of course, also an interest in foundation models for science. So I picked a couple of examples here. One comes from genome modeling, where you train on DNA sequences. And of course, you can see DNA as a language, right? So they did this, they trained the model to generate DNA sequences, and then they saw that they could actually, the model would learn how mutational effects on this DNA string, how that translates into biological function. And they did this without needing to do any supervised fine-tuning or anything. So this is called then zero-shot learning. This means that the representation they produced was so rich that the model had sort of, was able to figure this out. Next one is a climate model called Aurora. And this one is now trained on a mixture of data. So you have forecasts, analysis data, simulations, and so on. And what's interesting here is that this actually is not only able to do something new, but it actually outperforms the traditional methods. So these three are sort of examples of the things that we can get with foundation models. So we start from the bottom up. So this one outperforms the classical methods because it has trained on so much data, it is so powerful. The second one, it does something new. We call this emergent behavior, something that it wasn't trained for and we didn't necessarily expect that, but the model figured out anyway. And the first one obviously shows models becoming generalists. So it would be nice to have this in particle physics as well, right? And there's a lot of people who also share this opinion that it would be nice to have this in particle physics. And the field is growing really, really fast. A year ago or so, I wrote a review about what we had at that point. And then I pulled this from the Living Review the HepML Living Review. And I think these are all papers that came after I wrote that review. So there's like a ton. But what I can say is that most of these models are transformer-based. The most common object to analyze are jets because they are, a bit complicated and have structure and so on. And the most common tasks are classification, I think followed by generation. And then in terms of pre-training task, I think actually the most common one is classification. And then you fine-tune to classification on a different data set. But other than that, there's some type of like fill in the blank task. So you have, for example, the masked modeling, which Tobias has worked on, where you have your jet and jet constituents, and then you mask out different blobs of it, and then you give the model, given this context, what should be here. And then you can also do next token prediction. So this is essentially you treat the jet as a sequence, and then you predict what is the next particle that's supposed to come. And both of these are based on language methods. And then the amount of physics information that you give your model, that can vary. It can be minimal, like we only give the kinematics of the jet constituents, for example, or it can be extensive, like you give the the particle ID, the trajectory displacement, you can use interaction features, you can use jet level features, like ton of things. You can even design your entire architecture to be Lorentz equivariant. There are many different approaches. I would say that most methods rely to some degree on supervision, but a few are completely self-supervised. So, given this, I'm not going to be able to talk about all the foundation models that we have or the proto-foundation models. So I will focus on what we have been doing in our group in Hamburg. And so we have this picture here where we think about what are the concrete tasks that we would want to do. So you have your detector response, you have your hits, maybe you have your reconstructed objects, and then you encode these somehow. Then you train it with your model. We call this the backbone. This is just the pre-training model. We get our latent representation, and then maybe you want to do event classification, jet tagging, clustering, regression, anomaly detection, generation, and so on. Obviously, you can't do all of this at once. You need to start somewhere. So we started here. We start with the reconstructed objects, and then we do tagging and generation in the same model. So this is the Jet Alpha, and this model is now 2 years old. This was the first foundation model that was able to switch between generation and classification. And this is inspired by GPT. So we use the next token prediction pre-training task, which means that the model learns, given this partial set of constituents of our sequence, what is the probability for this next token to appear. And the idea we had behind using generation as pre-training was that if the model needs to generate a jet, it needs to also sort of understand something about what a jet is, and especially if it has to generate many different types and so on. So we took simulated jets, encode them with a VQVIE. I will briefly mention what this is later. And then we were able to jet tagging and generation. So we chose to tokenize our data. If you think about language, they have to do it. They have to somehow turn text into numbers, because you can't just put text into a machine learning model. Like you need numerical data. So they tokenize, they turn the words and like prefixes or whatever into integers. And because we wanted to use a similar architecture, we chose to also do that. But in principle, our data is numeric. So we wouldn't necessarily have to tokenize it. This is a choice you make. Anyway, how that goes is that you have a jet is a collection of particles. Each particle has a feature vector of some sort. And then you summarize each feature vector with a single integer. And this is using this vector quantized variational autoencoder. And then your jet becomes a sequence of integers. So this then becomes just like in language. And the main result of this first paper, we pre-trained it on generation, and then we fine-tuned it to classification. And what you do when you fine-tune is that you load the pre-trained weights, and then you swap out the part of the model that does generation, and you just attach a classifier instead. And what you see then is that, well, so this type of figures you will see in every talk that it's about foundation models, or you show how much more performance you get and so on. So you have the red curve, which shows if you train your model from scratch, so that is you don't load these pre-trained weights, but you just initialize it from scratch. And then the model needs to learn everything, and it takes some time for it to reach some reasonable level of accuracy on the classification task. But the upper two are different versions of fine-tuning then. And then you see that you can reach the same level of accuracy, which is a much smaller data set than if you need to train everything from scratch, because then obviously the model needs to learn all the structure and everything. So it is able to make use of this representation that we created, which was the point. And then we have continued, because like I said, our data is numerical. In principle, we don't need to tokenize it. And then we thought, okay, we want to keep our pre-training task, which is essentially is a classification task. We have just 8,000 classes for these tokens, but input doesn't need to be tokenized. That can be just the continuous resolution. And this benefits in particular classification, because when you do tokenization, you will lose resolution. Like there's no way around it. So we thought, okay, let's try that. And at the same time, we had seen that this masked particle modeling, so this is sort of the BERT style pre-training task, this is a bidirectional pre-training. So if you think about it, if you do next token prediction, the model cannot look from both ways. It can only look in one direction, because otherwise it will cheat and it will know what comes next. But in this masking, you have more context, and it can look in both directions. So this seems to be better for classification, but it doesn't give you a generative model. So we thought, okay, let's combine them and see what happens. Can we get the best of both worlds? And the answer is yes, we can. So we get to keep our generative model, but we also get performance improvement. So this is now, I don't know how well you can see this, but the gray line is the from scratch. And then you have our old method is in red. Then the pure masked particle modeling is in yellow. And then the combined one is in blue. And you can see for the most part it overlaps, and there's some minor differences at the very large data set sizes. So yes, so this was nice. And then we also thought, okay, but what about real data? Because so far we had trained on simulation, and maybe real data is different, or we know that real data is different, but not to what extent. Because the model does not need supervision in the pre-training, we can actually use real data to train it. So we derived a data set from CMS Open Data, and I put the link here if you want to have a look at it. So it's essentially boosted jets. Most of them are presumably QCD, we don't know because it doesn't come with labels. But the data set is ready to be plugged into your favorite machine learning model. We named it Aspen Open Jets. It's maybe a weird name, but we came up with the idea in Aspen, so that's why. So we pre-trained then our model on this data, which is presumably QCD, and then we fine-tuned it to generate top jets, which were then simulated. And we could see that this pre-training on the real data was beneficial when the model was then asked to generate top jets, which is sort of a morphing, right? And maybe you can see on these histograms that so the gray filled one is the target, and then the other ones is like where it started. Then the more data it gets, the closer it gets to the target. I think this is actually really important, and it's an important question that if you restrict yourself to only have a model that needs labels, then you cannot use all of the data that we have. Okay, and then we thought, okay, now we have done reconstructed objects. What about calorimeter data? So again, the architecture, because it uses integers only, tokens, it doesn't really matter what data you put into it. You can put language into it, whatever. The model doesn't care. So we thought, okay, let's extend this to calorimeter showers. And the goal here is now generation. We have not yet done transfer learning, which it is coming, hopefully. So we just did the same thing. We took our calorimeter data, so you have 3 spatial features, X, Y, Z, and then you have energy. We tokenized everything and generated. And it produces nice showers, and that's not really trivial, because if you think about a jet, it has maybe 50 or so constituents. These showers have like almost 2,000 hits. And if you know anything about transformers, you know that they don't scale super nicely with sequence length, but still, it worked. However, this method does not scale very well to high granularities, because we need to summarize, this 4-dimensional feature space into a single token, which means that we need a really large codebook size or vocabulary in order to cover this phase space. So this is a sneak peek of a paper that's coming soon, hopefully this week, where we just thought, these spatial coordinates, they are already discrete. Why do we need to retokenize them? It doesn't really make sense, right? And then we also split it up. So instead of using like this 4-dimensional feature space, we use 4 1-dimensional ones. We also used a delay mechanism to then preserve the intra-hit correlations and so on. So this model is then able to ingest both the discrete features and the continuous ones. And this method is very general. It's applicable to any type of domain where you have these multi-feature data sets. I'm not going to go into it more because this will be in the paper, but I still wanted to mention it. Yes, and then we come to scaling laws. Tobias, you also mentioned this. So in language models, you have seen that if you change the number of model parameters, or you change the amount of data or the amount of compute, these empirical scaling laws appear. Was it 5 or 10?
5.
5, okay. So this means that you can predict how your model is going to perform when you change these quantities, which is necessary because these models are not cheap to train. You need to throw quite a lot of compute at it. So what you are going to be constrained by is compute rather than like data or whatever. So people have now also started looking into this, and it has been shown that these scaling laws also exist for jet tagging. And I was hoping that Lucas would talk about it. Now I don't know if he will be able to come or not, but I put the links here anyway. Okay, so again, our model is based on next token prediction. It's what most modern language models use. So we should be able to compare pretty like one-to-one with language and see if we also have these scaling laws. So when we scale with model size, the number of parameters, we do see a beautiful scaling law. So here x-axis is number of parameters, y-axis is the validation loss, and you can fit a very nice power law to this. And we also have an asymptotic loss that this curve approaches, which is somehow indicating the inherent entropy of your data. But then again, next token prediction is not necessarily physics, right? It's next token prediction. So we also wanted to see, does this translate to physics quantities? So we analyzed or measure the sliced Wasserstein distance for 5 physics quantities, jet level quantities then, and the model does not have access to this directly. And we see actually that this also scales very nicely, or I mean, not as nicely as the first one, but still it's like a monotonic relationship. So then we see that this loss is a good proxy for the physics as well. But then something very interesting happens. So when we change the dataset size, suddenly it does not look so nice anymore. I mean, you can squeeze in a fit here, but if you zoom in on like on all of the other points except the first one, you see that it's not a very nice fit, right? So what's going on? It seems like the model is saturating very, very quickly. And this is not a lot of data. So what's measured here is like the unique tokens. But it's really like this lowest point is just like, I don't know, maybe 100,000 jets or something. That's really little. So we try to understand this. And then to do that, we introduced this concept of learnable window. So if you think about what can your model learn, there exists a space between the best possible it can do and the worst possible it can do. And if you have a classification problem, the worst it can do is to just assign the same probability to every class. Because if you imagine that it always consistently chooses the wrong thing, then you just flip, invert your scores, and then you're good. And the best it can do is to reach this irreducible loss, or the sort of entropy of the data. So this is what we call the learnable window, the space here. And then we compared this to the language model Chinchilla. So this is one of these scaling law papers. And it turns out that we, by accident, actually have the same vocabulary size. And the vocabulary size informs like the worst you can do, because it's like I just give the same amount of probability to all of them. So the worst case is the same. But then we look at the irreducible loss, and we see that ours is much, much higher than theirs. So this means that our learnable window is much smaller. And this raises very interesting questions about the nature of QCD, because we trained this on Aspen OpenJets, mostly QCD, which in my head is like, some fluffy blob in the detector. But there is structure in QCD, because you have, the shower development and fragmentation, all of these things. There is structure. But somehow in this task, it doesn't pick that up. And then also, what is different then about jet tagging? Because there you see it, but it's a different task. So yeah, I think this raises more questions than we have answers for, but it's also, yes, many, many things to keep on working on. And then, how much time? 2 minutes? 0 minutes?
1 or 2.
Yeah. Okay, I'll do it quickly. Yes. So we also worked a bit on agents, because now I've told you a lot about how we can build all of these fancy models to mimic what's been done in language and so on. But these language models are already extremely powerful. What if we just let them do some of the work for us? So we investigated 4 OpenAI models on anomaly detection. So we gave them the same task that has been given to, I don't know if you remember the LHC Olympics challenge that some people worked on. And the results are very interesting. They range from none to surprisingly competent. So this is the setup. I know it looks complicated, but we essentially have the main agent is the researcher, which gets the task from the user, which is, here's some data, check if there's an anomaly, and we want to have answers to these questions. And the researcher can then assign a task to the coding agent to write some code. The coding agent needs to have a code reviewer, because as you know, these models, they can just make things up, and then your code doesn't work. So they do a bit of iteration. When it's happy, it sends it back to the researcher, which then runs the code on our local machine, containerized, of course, so it can't kill the entire cluster. and they can then analyze the results and so on. And once it's finished, it needs to go through a logic review agent or a peer review again, so it won't just make things up or, yeah. And then it just writes the final report. And so this is what I meant before, that the results range from none to surprisingly competent. So if you see GPT 4.0, there are just 5 dots on that one, and we ran 16 runs. So it means it mostly just failed. It was not able to do this at all. Then GPT 4.1 and 5 are, they have some outliers that are actually really good. And in one of the cases, GPT 5, it actually reached a similar performance as we did with Cathode, weak supervision method, a few years back. So yeah, this is nice. And this field, again, it moves so fast. Nowadays, no one would use GPT 4.1, you'd use Claude or whatever. So it's the acceleration is insane. So yes, looking ahead, I think there are a ton of open questions. So one is that, what is the best pre-training task? It doesn't have to be something useful in itself. Maybe we haven't, gotten there yet, because our problems are just very different from what you see in language, for example. But we still keep looking to language. And then, should we tokenize our data? And if we do, should we then use this sort of split method in order to reduce the dimensionality? How much physics information should you include? Maybe if you just train on massive data sets, you won't need to have a lot of physics information. I think this is what's known as sort of the bitter lesson. It doesn't matter how smart you are, how much physics you put into your model. If you throw more data at it, it's just going to outperform you anyway. Is it a point to making these models multimodal? Should we give it both the reconstructed objects and the detector hits and the tracks, etc., for it to learn something? Or are our methods already good enough for that? And how can we utilize the lessons that are learned in the context of language and adapt it to our field? I think we currently don't necessarily understand how our setup and our data differs from language enough in order to just transfer one-to-one, so we are still exploring here. And yes, and the field of machine learning, of course, is growing extremely fast, both with outside of physics and within. So yeah, I think the future will bring many interesting inventions, and I hope to be part of them and to maybe revolutionize the way we do physics. Thank you.
First question.
Thank you for the great talk. I would like to ask a personal question. What do you think is the problem solving this foundation model, the physics problem, primarily?
Very good question. What I hope that we can solve is both, I think what you mentioned, reduce the redundancy, because if you need to train your own model for everything and maybe your statistics, you don't have enough statistics for your specific problems, then you are wasting compute power on learning the structure of the data, which could be learned on like a larger data set that we have access to. And you're wasting a lot of human resources, a lot of compute resources, and hopefully this is something that we could fix, or mitigate if we use these foundation models. I think what we haven't seen yet is whether it also outperforms the classical models. I think we still have to see. I think one problem there is that we are still at a method development phase. So we are testing different pre-training strategies, different tasks, different types of data we put into it, and we're trying to see what works. Because you don't want to necessarily commit immediately to thousands of GPU hours on all the data before you have some idea of which direction you want to go in. So yeah, I mean, one crazy idea is that you can just throw all the data you have into one big model and continuously. So when you get new data, you keep feeding it into the model, and then it will do something. But we are quite far from that.
Thanks.
Question?
Yeah, thanks. Very nice talk. Just following up on the last point you made. I mean, so you're making a real effort of making a sort of a data input to the foundation models available and so on. But there were some studies at Atlas, like Carpe Datum is last pub note, where they've shown that we're like orders of magnitude below the industry, and we need actually orders of magnitude more real or simulated data. in order to really achieve the power and potential of these transformer models. So what's your comment on that, or what's your suggestion or vision on that? What should we do in order to get trillions of
give us
data?
all the data. Give us more data. No, seriously. So I'm not actually a part of an experiment, which means that I don't have access to that type of data. I have access to open data, I have access to open simulation, and so on. But part of training these models is, like you say, if we are not in the regime yet where we can see these like huge gains because we don't have enough data to train them on, even like in the model development stage, then yeah, that's obviously a problem. So yes, more data. Yeah, it's just my comment. I don't know how else to answer your question, but yeah.
Can I have a follow-up question? Yeah, just orthogonal. Related to the discussion we had with Tobias before, what's your vision on how do we train young physicists to be able to understand and supervise these models? I mean, as you said, and discussion started before, right? It's really critical that you have a critical and informed observer to throttle them and so on. And if we stop doing learning by doing an analysis, which we currently do for PhD students, we have to replace it with something, right? Yeah. Do you have an opinion on that?
I mean, I completely agree. And again, I'm not in any of these analyses, so I cannot really say anything about these things, but I see, you know, my other students who are working only on method development and how much they start to rely on AI, and they are not maybe really thinking as hard anymore about certain things. And I think that's like just a larger like societal issue that we need to address, and that doesn't necessarily have to do with physics. Because what we want in the end is sort of to let the students develop their critical thinking skills. Like that's what's important. For some of it, maybe you need to train resilience by like banging your head against the monitor. Like, why is this not working? You know, whatever. I don't know. Yeah, I also ask myself the same question.
So, first of all, this was a very, very nice talk. So it was heavy talking, it was very nice. So I want to ask you about tokens and tokenization. So you mentioned at some point in your talk that there's this inherent loss of granularity or loss of information when you tokenize. But at the same time, for something like Atlas and CMS, objects that we use, which are nice because we have this nice little intuition about a jet and a dress lepton, this is being constructed from readout chips. So this, in fact, is you're taking something that already is in some sense tokenized, reconstructing it, and then deconstructing it. So my question for you would be, what would be the potential advantages there are obvious disadvantages, but what would be the potential advantages from just going directly on the readout chips and not working, and not trying to attempt to tokenize the reconstructed objects, but work directly from readouts?
Yes, very good question. This is something I want to try when I have some time to work on it with open simulation, and I guess. No, I think then we come back to the question: is it important for the model to learn how to reconstruct these objects, or how to learn from like so extremely low-level objects, or are we like, again, it's like how much physics information do we need to put in, right? So we have very good reconstructing like, you know, algorithms and particle flow and all of this. Is it better that we do it and then we let the model train on the high-level objects, or is it better to just let it do, you know, its own thing and then rediscover it? I would like to try. I would like to see how that pans out. I think it would be a very expensive training. But yeah, no, for sure. This is something I would like to try.
Yeah, good question.
Yeah, I had a question, especially since you mentioned the expensiveness of the training. So very nice progress, and I know it's early days, so it's already very impressive. But actually, what about I mean, it also relates with what Tobias was saying earlier, the cost of all this, because in industry, for example, many are realizing that actually the cost of using any of these models is getting more expensive than the software engineers they're meant to replace. Of course, the idea here and everywhere is that we still keep supervising as human those tools, and they will hopefully become cheaper. But has any benchmark been done to try to compare, maybe you quoted in the papers, I don't know, the cost in electricity, CO2 equivalent, dollars, euros, whatever you name it, of those attempts, and to see how they scale? Because, for example, yes, we have, I don't know, 10,000 people hours, years, whatever, and they have a cost. but actually I'm wondering if what we're replacing it with, yes, maybe we have the response in a week rather than 10 years, but the cost of that could maybe be the same in what our funding agencies will deliver or not. It's a general question on the topic, right? And I was wondering if we have data for it, not that I know it's going to go one way or the other.
Yep. Yes, a very important question, especially also with sort of the resource, like in, for climate and so on. When we train this agent, I don't remember the sum now, what it cost in the end with from the cost from OpenAI, and I don't know how that translates to CO2 equivalents and so on. But it was way cheaper than employing a PhD student. I can say
but
that.
Subsidized by OpenAI.
Sorry?
Subsidized by OpenAI. I mean, we all know that.
Probably, yeah. That is not the real cost exactly, but you still need to have someone who already knows what the end result is going to be. So you need to have already trained that PhD student. Essentially.
Yeah.
So,
no, I understand the problem.
Yeah.
That's very true. Thanks.
No, but this is also something, of course, that we should measure. The footprint and the cost. But how it compares to like employing people, that's.
No. It's just to get an order of magnitude, because we know in our grants how people cost, but the compute is always hard to estimate.
Yes, it is.
And then you rely on either clusters or big, subsidized stuff. You find a deal with Google or OpenAI, you get it for cheap because they want you to test it on their platforms. But then, does it really work on the long term?
So this is something you would, the scaling laws come in here. You want to try to, predict how much it will cost and how do you do it the most efficient way. You also, like when you program, you also need to have some knowledge in order to figure out how do I do this in the most resource efficient way, which I was not taught as a programmer. So what I'm doing is probably not the best, way.
Thanks.
Great, let's thank Anna again. So yeah, our next speaker, well, Lucas couldn't make it, his flight was cancelled, but Marco has kindly stepped in and he's going to tell us about model agnostic signal discovery with machine learning. So yeah.
Thanks a lot. So thank you for having me here. So I will be talking about this topic. So this is what I'm going to focus on is some work that I've done with Oz and Mikael, part of the Verify initiative, where a group of people have been asked to produce some literature about machine learning methods in physics, and especially from the point of view of how to validate these methods and what are the challenges. So I will specifically talk about model agnostic searches. Okay, so this I don't need to. I think I don't need to talk about this too much. So we know that most searches for new physics at the LHC are, let's say, model driven. So we have a model for the signal, so we have the standard model, and we want to test essentially the hypothesis of whether there is a signal contribution in the data or not, given some model for the signal PS. And typically, if you can reject the null hypothesis, which is there is no signal at a certain threshold, then we proceed to claim discovery. Now, again, most searches are model dependent. Means that we optimize them to have power over specific type of signals. So we have our simulated background, we have our simulated signal, and then we have the data. And of course, if the space is high dimensional, nowadays we rely a lot on machine learning. And so this, for example, means that we might want to train a classifier on background and signal and then test on the data, right? But then what can happen is that if there is some misspecification about the signal or the background, we might end up essentially not seeing anything, simply because we pick the wrong hypothesis, essentially. Okay. So this is essentially, in just a few words, the motivation behind going, say, beyond signal model-specific searches and towards model agnostic searches. Now, to do traditional searches, we have to somewhat be able to reliably simulate data from the background or the signal. But these simulations can be unreliable, misspecified, or simply unavailable. And so we can have, if we have a misspecified signal, we might, generally what happens is that we miss a discovery. While if we have a misspecified background model, then we claim a false discovery, so we have false positives. And so we want to try to get rid, let's say, to soften our dependence on signal or background models and go towards more agnostic strategies. Now, if you have, if you've been working on some of these methods, then you can try to place them in this figure. And generally, let's say, current developments are either, let's say, they're either trying to make very weak assumptions about the signal, but somewhat relying a lot on the background model via simulations, or you are probably somewhere in the middle of this plot, where you have like some level of assumption about the signal and some level of assumption about the background. But of course, we are very far from being at the bottom left corner of this plot. So what I want to discuss is, in this work that we did, we kind of discussed two broad categories of methods, one that perform the full statistical test, and I will discuss how this can be framed in the setup of two-sample hypothesis testing, and then a second category of approaches, which are like model-agnostic signal selection strategies, which don't perform the full they don't necessarily perform the full statistical test, but they're used to identify a subset of data which is enriched in signal events. So let me start by just giving you an idea of what does it mean to do two-sample hypothesis testing for signal agnostic searches. So essentially what we have is that we have our data, which is, let's say, so we have two samples, one coming from the distribution P1 and one coming from the distribution P2, and then we have some kind of test statistics, which gives us a real value out of a function applied on the two samples that we use to extract a p-values in a way that I will briefly mention later on. And then we have two hypotheses. Either the two distributions are the same or the two distributions are not the same. Okay? So we try to, let's say, exclude the null hypothesis by looking at these two from data. Of course, this is, let's say, this kind of approach is meant to, let's say, detect distribution shifts with respect to a reference model. Okay, and there are a lot of classical methods to do this kind of tests in one dimensions. Let's say the Kolmogorov-Smirnov test is one of the most common. But then recently, again, in order to handle like high-dimensional problems, classifier can be used to design multivariate tests. So the basic idea is to train a classifier to separate X from Y, and then let's say if our classifier is in some sense successful, we have some evidence against the null hypothesis, and so we can say to some level of confidence that the two distributions are not the same. Okay, so there is some shift between the reference distribution and the distribution that we are interested to test it against. Now, of course, very simply, if we consider the two distributions to be the background, let's say the standard model distribution, and the second distribution to be the distribution of our measurements, then we can design model agnostic searches as two-sample tests. And there have been a number of works on this in this direction. Again, this approach is a full statistical test, so we start from the data and we end up with a p-value, and this kind of approaches can be also considered as part of, let's say, what is also known as collective anomaly detection. So we don't look for to flag individual data points as anomalous. We are more searching for, let's say, localized or not excesses in our data, which are collective. So there we like have multiple. We identify as anomalous a collection of data points in our data set. And generally in these approaches, we try to be agnostic about the signal. Okay, so we rely on a reliable sample from the background. So one again, so the from the value of the test statistic on our initial sample, we want to compute a p-value, and so we need to estimate the distribution of this test statistic under the null. So under the assumption that the two distributions are the same, there are several strategies to do this in the statistical literature. So we might be lucky and simply know the analytical form of this distribution, which is very rare. We usually don't have access to it. So for example, we know sometimes how it is done for a Kolmogorov-Smirnov test, but generally we don't know. And so we have to construct it empirically. So this can be done by generating toy data sets from the null distribution, or for example, by doing what is known in statistics as a permutation test. So we have the two samples, and then we mix, we shuffle the labels to simulate the null hypothesis. And then often this requires, sometimes it requires like full retraining for each permutation, or each toy data set plus evaluation. So these methods can be at times a bit expensive. Anyway, once we estimated this distribution, we can just compute the p-value as the probability that the test statistic is larger than the one that we observed under the null. So I will just briefly show you one example of these strategies, which is the new physics learning machine, which is one of the most advanced methods, which is close to, let's say, which is ready to handle a number of problems and criticalities of in high energy physics analysis, which is based on the idea of training a classifier to reconstruct the ratio of densities, so the ratio between the distribution of the measurements and distribution of the background, and then this function is used to construct a custom, let's say, evaluation metric, which is nothing but a Monte Carlo rewriting of the extended likelihood ratio test. And then this metric is evaluated in sample on the data the model has been trained on. And this is supposed to is constructed to approximate, let's say, the maximum likelihood ratio. And I won't discuss about it, but let's say this method also has the ability to accommodate systematic uncertainties. Okay, so this is just a graphical, a figure that more or less is supposed to give you a view of how the model works. So we have our input reference sample, our measurements, then we train the classifier, we compute the test statistic, so we learn the density ratio, that is also a proxy to check where the model is detecting a discrepancy, if there is one, and then it outputs the value of the test statistic. Now, let me just give you a bit of a highlight of what are the challenges of this kind of methods. So first of all, there is the problem of model selection, meaning that every time you design, let's say, a testing pipeline powered by a machine learning method, you have the problem that model selection, or let's say hyperparameter tuning, can introduce biases. So this thing has two phases. One is that we can actually leverage these biases to make our search a bit more specific. If we're interested in a type of in specifying a bit more what kind of signal we want to look for. But on the other hand, if we want to be, let's say, agnostic, we need to somewhat handle this problem. And there are so this is just one example in which we have some benchmark signal which comes from some effective field theory, and we see that by changing some hyperparameter of this learning model, then we have different type of power. So we have let's say different powers depending on the hyperparameter, and there are different. So there are some proposals to address this kind of problems, and one possibility is to do multiple testing. So we run our analysis several times, and we kind of combine the results in a way which is robust against the Lucas-Swear effect. And then we have a common problem to this kind of, let's say, an important step of this kind of approaches, which is validating the null hypothesis. So we want that once we have the distribution under the null, we want to check that the rate of false positives is not, let's say, above the nominal level. And we want to check, for example, that the distribution of p-values under the null is uniform. So this is, in some cases, this is guaranteed by construction, but it's always a useful thing to do these checks just to see if there might be bugs in the pipeline, for instance. And then, of course, one key question is how to assess the performance of these agnostic methods. So the best we can do at the moment is essentially deploying these strategies in benchmark scenarios. And one thing that one might want to do is to compare an agnostic search against a fully supervised specific search. This is fully aware of what we are looking for. Now, of course, this allows to kind of assess the trade-offs between sensitivity and signal agnosticity. But on the other hand, of course, it cannot be used to fully characterize these approaches, as we would have to test these pipelines over like an infinite number of possible signal scenarios. And again, I want to make the point that there is a theorem actually that says that signal agnostic methods cannot have power against every possible alternatives. So whenever we design a signal agnostic method, there's going to be some corner of our, let's say, search space that is not going to be well covered by our method. So we need to keep this in mind when we think about signal agnostic methods. And actually, if we push this argument to the end, it means that if we enlarge the space of let's say models that we are sensitive, that we can be sensitive to, then inevitably we will lower our overall sensitivity to the point in which we won't see anything. So we always have to be careful about this kind of methods. Now let me go briefly to the second half of the talk, in which I will instead talk about methods for signal selection. How much? 5 minutes, okay. So these are methods that rather than trying to do the full statistical test from data to p-value, they try to somewhat identify a subset of our data which is enriched in signal. So these methods can be, let's say, concatenated with physical assumption, so they can be at the beginning of an analysis that will then lead to a statistical test and a p-value, or they can be used, for example, just to flag interesting events that can be saved for analysis that will be done later on, for example, if you use them for trigger level anomaly detection. And I will briefly mention two sides of this story. One is outlier detection and one is weak supervision. So outlier detection is essentially the idea of trying to either implicitly or explicitly learn the background distribution and then try to assign an anomaly score to individual data points based on how likely these events are under the background distribution. So one common architecture to do this is our autoencoders that are trained to reconstruct data points from the background distribution, and then when these methods are tested on, let's say, measurements, then we can check whether the model is a, let's say, we would expect that if the measurements contain, let's say, some significant difference with respect to the background data, then the reconstruction is not going to be as good, and then we can use the reconstruction loss to try to flag anomalies, or this can also be done directly in latent space. And for example, another way to approach this problem, which is instead explicit, is to simply try to model our likelihood, for example, with normalizing flows, and then try to assess how likely, so I'll try to score our measurements on the basis of this explicit likelihood. Now, the typical challenges of these approaches is that PDFs are not invariant on the nonlinear coordinate transformations, and so low probability data points cannot be, they might not be low probability if we make a change of variables. And so for these kind of methods, data representation is a very important step, and it represents a large inductive bias that we put into the model. Then a second category of methods are methods that are relying on weak supervision, in which a classifier is essentially trained on mixed sample, So we have a sample. We have two mixed samples that will both contain background and signal data points. And we're under the assumption that one of the two samples is more, let's say, rich in signal than the other. Then we can train a classifier, and we can show that this classifier will asymptotically learn the optimal ratio between signal and background. And this can be used to, let's say, then identify regions of your measurements which are rich in signal. Of course, since we are learning the likelihood ratio, we are not so sensitive to issues related to coordinate invariance. Now, let me just briefly go through one important case study for this kind of methods, which are digest resonance searches. So these are, let's say, usually these signal enhancing techniques are used in combination with resonance searches, so that we can compute a p-value. So, for example, this is typically done in bump hunts. And generally, these techniques are used in conjunction with machine learning, also from the point of view of trying to estimate the background data. So we have we define some signal, some sidebands in which we train a generative models, possibly on auxiliary variables which are not the invariant mass. And then we interpolate in the signal region, and then we look again at and then we go to the invariant mass to see, let's say, try to estimate our background. And digest searches are, let's say, relevant because they are, let's say, they're rich, potentially very rich. They have a very rich topology with potentially many anomalies. And these is one of the most published. One of the most used approach on real data, and I'm citing some references here. Now, this also has these approaches have a number of challenges. One of the most common one is mass sculpting. So it means that when we do our selection of anomalous events, we need to make sure that the background distribution is not distorted. So this can be, let's say, addressed through a number of methods that have to do with try to decorrelate. For example, try to use features which are somewhat decorrelated from the mass, or using some custom training strategies that I will not go in details. I will not discuss in details. And we need to do this because it's necessary to validate in such a way that the p-value that these methods will output are sensitive. Now, other challenges, of course, are common to the previous method. So we need to validate the null. So it means we need to make sure that the method works when there is nothing to see, and this can be done in several ways, through Monte Carlo, controlled region, or synthetic data. And each of these methods have these methods has its own drawbacks, and then we need to validate whether the model is able to see something when something is there. And typically, this can only be at the moment can be done simply by injecting either by injecting signal in the data or by using some let's say signal in the data, which is not what we are looking for, but we have let's say some physics knowledge about. So let me just end with a couple. So I have just a couple of slides more to end. So one is this flowchart that I'd be happy to discuss with you on how to, let's say, select what's the best method depending on our framework. So, for example, if we have a very accurate reference sample, then we can go and use, let's say, two-sample testing techniques. If we don't have access to an accurate reference simulation, then we can go through this chain and ask ourselves whether we can estimate it from the data, or if if yes, we can go on and maybe try to use weak supervision, or maybe we don't have access to a reliable sample from the background, and then we go towards more techniques which are more related to outlier detection. So let me just, this is my last slide. Of course, I mean, something that I haven't really talked about, which is super important, is how do we actually interpret the results of these approaches. So, of course, we need to ask ourselves this question in two cases. Either we don't see anything, and then, let's say, excuse me. So, what do I want to say? So, of course, if some anomaly is found, then we need to try to interpret these models and develop techniques to, let's say, open up the box and understand which features are more important and try to characterize the signal that we see. And potentially, let's say, if we don't see anything, then we really need to, let's say, rely on benchmark signals to try to, let's say, assess the performances. So these benchmark signals are absolutely necessary. However, they're like, we can design them to cover, let's say, a wide space of possibilities, although we need to be careful not to optimize our pipeline towards specific signals. And on the other hand, although we have to rely on benchmarks, this is a bit philosophically, let's say, in contrast with the idea of signal agnostic searches. So I think this is the best we can do at the moment, but we might want to think about other methods, other ways to evaluate these approaches. And then, of course, we need to, let's say, try to benchmark, let's say, to evaluate the performance of these methods against fully agnostic searches. For example, in these plots, we have, let's say, the p-value that come out of some of these, or different realization of these anomaly detectors, and we see that they somewhat typically sit between, let's say, a fully, let's say, characterized specified signal and, let's say, some kind of inclusive instead search. And it's important to kind of try to see where we land with our model. And that's it. Thanks.
A quick question. Yeah, Tobias.
Right. Thanks for the very clear talk. Two quick questions.
Yep.
What do you see the role of automation, as I was mentioning in my talk? Like, for example, when you talk about the challenges, you referred to you can tune the level of assumption you make. I was wondering how automatable would that be, that you kind of scan over this space of assumption you make?
So yeah, so I think the way, yeah, so I think that we can design. So we can definitely kind of so what I want to say is that we can definitely take these models and insert them into a pipeline, which is let's say more let's say automatized or let's say assisted by some kind of orchestration. For example, I would say the model selection and hyperparameter tuning is certainly a great candidate for this. So we now for example, we can try to use some machine learning model at the beginning of this pipeline and try to scan for interesting set of hyperparameters, maybe not in a way which is simply a grid search, which can be very expensive. So maybe we can design specific model to try to focus on interesting space of hyperparameters that maybe they can or cannot be focusing on specific, let's say, features that we want to see in the data. Because we talk a lot about signal agnostic searches, but we want to maintain, I think, some control over what we are looking for. So maybe we can design autonomous systems that kind of fine-tune our model in a way to introduce, for example, the correct level of inductive bias for this or that hypothesis that we want to look for. So I think another way, something that I haven't talked about that I think connects very well with your talk and Anna's talk, is the fact that anomaly detection, whether in the form of a statistical test or not, can be very much integrated with foundation models, for instance. For example, especially in the case of statistical tests, there is a clear bottleneck when we want to analyze very high-dimensional problems. And I think that there has been some work showing that trying to extract, let's say, more meaningful representation at the beginning of, let's say, of our agnostic pipeline can be very beneficial. So I think this whole work can be put, let's say, inside some kind of automated pipeline, but of course we want to kind of have some control over like the inductive bias that we are introducing in our pipeline.
Am I allowed for a second?
Yeah, sorry, it was very long.
The second, I want to understand better you had these two, a background model and signal model, and weak and strong. I was wondering, why do we want a weak background model? Don't we always benefit from having the best background model control, either Monte Carlo simulation or data-driven signal region interpolation, cathode, curtains, all these ways?
Yeah, so no, I think that so the question was,
why would we want to have a weak background model? Don't we always want to go to the strong end, like have the best background model we can?
Yeah. So I think that the idea is that if we rely, so I think that the idea of the chart is of the plot was to so if we have a strong reliance on let's say imperfect simulations, then we have to somewhat to account for it and correct for it.
Okay, got it. Thanks.
Yeah.
Oh, it's getting late.
There's a question on Mattermost from Pietro. Is there an example where this anomaly detection approach actually works better than EFT or signal-aware searches?
No, I would say that by definition, so it depends what you mean by they work better. So by definition, there is nothing that works better than a fully agnostic search. So the reason why we are, say there is interest in these methods is that we are not so much vertical, but you're able to explore more. So we're able to look at corners of your, let's say, model space that you might not be, let's say, looking with specific searches one by one. So let's say there is no, if you specific searches on a given signal model will always be an upper bound to the performance of agnostic searches.
Okay, I think we can save the discussion for the speaker. Okay, so let's thank Marco and.
Yes. All right, welcome back from the coffee break. We continue with some reports from Working Group 3, and we start with Julia first with some SMAP combinations.
Thank you. Good morning, everyone. I'm Giulia Lavizzari from Milano Bicocca and CERN, and I will present some SMAP combinations in the electroweak sector made by the CMS detector. So first of all, as this is the first experimental talk with the detectors, I'll just go through the entire presentation. As you probably all know, CMS is a multi-layer, multi-purpose detector. We have, starting from the center out, a silicon tracker for reconstruction of trajectories. There is a ECAL, an homogeneous electromagnetic calorimeter, then a brass and plastic scintillator HCAL, hadronic calorimeter. We then have everything wrapped in a superconducting solenoid that provides 4 Tesla magnetic field. And finally, we have the very high resolution detector for muons that gives the name to the entire system on the outside. As I said, I will talk about EFT combinations in the electroweak sector. So first of all, how do we search for new physics in CMS? In general, we know that the electroweak sector is a very powerful probe for new physics searches, but the question is, where do we search? As everyone knows, no new resonances after the Higgs bosons were observed at the LHC, and many of the tensions that appeared to exist between the standard model and the measurements are slowly disappearing. So even though BSM searches are constraining BSM parameters, we don't really have a clear direction on where new physics might lie. So the idea is that new physics might lie at energy ranges that are not accessible, and the possible tails that leaves at accessible energies at the LHC can be parameterized with SMEFT. SMEFT would provide a common language to parameterize possible new physics impacts on the various measurements. So in general, CMS has a very long-standing tradition, especially, for example, in anomalous tribal and quartic gauge coupling interpretations, and currently is moving more and more its effort towards SMEFT. In general, SMEFT covers a very wide range of UV-complete theories, so it's quite general. It's also well established and tested, and many tools are available, and the technical implementation is relatively easy. So of course we have together desirable theoretical properties and relatively easy practical implementation, which for us experimentalists is fundamental as well. As again, you all know, the idea is to basically tailor expand the Lagrangian of the standard model, and the higher order represents the new physics. We consider a linear contribution from BSM, where we have a linear BSM contribution together with the standard model in interference term, let's say, and then we have BSM-only contributions. The question is then, how do we do those measurements in our experiments? The first, let's say, the first important part is why combinations are so important. The reason is that the SMEFT Lagrangian truncated at any order is in principle a valid description of nature. So you want to retain all the SMEFT operators a priori, and this results in a very large parameter space. So in order to enhance sensitivity and to constrain all possible directions, you want to combine measurements. There are, though, two possibilities for analyzers, in general for running the measurements, but they become very important for combination, which is direct measurements or unfolded measurements. Basically, the second one would mean not to rerun the analysis and use results that we already have. Clearly, this sounds very desirable for experimentalists, but there is a trade-off between complexity and realism. As you might imagine, for reconstruction strategy, so the direct measurement is basically consists in propagating the EFT through the entire detector simulation. So basically, you generate the events, for example, with MathGraph or so on. Then you pass it through the Parton showering, then the GEAN detector simulation, and the reconstruction, and so on. This is the process that we do for every other kind of standard model Monte Carlo. This is very nice because it allows to basically design your analysis entirely for EFT, so it's fully optimized. But it's very difficult to include multiple operators. It's difficult to reinterpret or combine with other different measurements that are maybe done slightly differently. On the other hand, we have the unfolded version, which is basically the reinterpretation of fiducial measurements. So it's basically a bottom-up. So instead, you take the final results, so a nice distribution as the one you see here, and you remove the detector effects and so on, you end up with the fiducial measurements that you compare to your SMEFT prediction. This is clearly not optimized for EFT. It's a recast of standard model into EFT, which also implies assumptions. It's, however, more easy in terms of, for example, reinterpretability, combination of measurements, and the analysis is not fixed to a specific EFT model. So you can rerun it as many times as you want with different models. Again, is a trade-off between realism and complexity. Today I will present a set of results from CMS with combination of measurements using both, let's say, strategies. In particular, we have a combination from the Higgs sector, a combination from the top sector, and one from the boson processes, in particular vector boson scattering. And finally, a global EFT fit, which is much broader. It consists basically of measurements from Higgs, electroweak, top, QCD sectors, and as well as LEP and SLC pseudo-observable. Starting with the first, the Higgs sector combination. This represents the first combination of Higgs production modes measurements with the ST-XS framework. So basically here we're talking about fiducial cross-section measurements. This is done with CMS data that are collected at the LHC Run 2, so 2016 to 2018. And as you can see, this represents the standard model measurements. It's a combination of several different production and decay mechanisms. For the EFT interpretation, dimension 6 is considered, which is the first one after the standard model dimension if you remove the terms that are odd and violate the symmetries. The way the EFT is implemented is slightly different for the various analyses. So we have analytic calculation of the SMEFT contribution for some of the analyses, for example, Higgs to gamma gamma and Higgs to Z gamma. And we have numerical computation for all the other processes. SMEFT-SIM is used for tree-level contribution, SMEFT at NLO for loop-level contribution, and EFT2OBS to map the effects from the theory to the observable. Some results. Those are presented here are one-dimensional scans, which means considering one single operator at a time without profiling the others, so fixing them at 0, the standard model value. The linear and linear quadratic constraints are presented, so including not only the full BSM-only contribution, but also the interference between standard model and EFT. And you might notice that, well, everything is mostly consistent with the standard model. Let's see if I manage to point, yes. Except for a couple of significant deviations that in particular are for CHQ3 operator, which actually affects mainly the region with the high transverse momentum of the vector boson in WH and ZH analysis, which are the ones for which the measurements were the most in tension with respect to the standard model. So this is compliant to the results, standard model results that were obtained. An attempt to profile fits was also performed. However, some of the Wilson coefficients have an almost degenerate effects, so it is not possible to actually fit them all simultaneously. What was done was to use the principal component analysis technique to derive basically linear combination of the various set of operators. The focus was only on sensitive directions, so only the 17 eigenvectors with the highest sensitivity were retained. And the summary is the one you can see here. Again, there is one important deviation, which is, however, which can be, however, linked back to the CHQ3 operator, which is the one that enters more widely in this eigenvector. So everything is, again, everything else is consistent with the standard model. Second combination, top sector. Again, this is done on data collected with the LHC run 2. And 8 SMEFT operators are considered, again, dimension 6. All of them involve couplings between heavy quark and a boson, and the analyses that are considered are of, let's say, two families. We have a boosted analysis, which is basically TT bar in association with Z or H decaying to BB bar. And we have a multi-lepton analysis, so production of a various number of T quarks with a various number of leptons, 2, 3, or 4. Results here are obtained always profiling other Wilson coefficients, so they are not set to 0, they are left freely floating, and the results are obtained by fitting simultaneously the combined likelihood of the two different measurements. As you can see, the 2D scans up here also show some correlations expected for operators that are not orthogonal between each other. In general, the multi-lepton analysis drives the sensitivity of the full measurements, but it's important to remark that out of 8 operator trees, so almost half of them, yield a 10% improvement with the combination. So combining measurements is actually very important and useful. And in general, again, no deviations from the standard model are here observed. Furthermore, limits on the can be set on lambda, basically by setting the value of the Wilson coefficients. Third combination, dileptor measurements, in particular actually VBS processes. This analysis focuses on two productions, WV and ZV, where the second V can be either W or Z, decaying hadronically, and in particular only boosted categories are considered. So the two vector boson, so the vector boson decays to 2 quarks that are close enough to make a single jet. 20 dimension 8 operators are considered in this analysis that are generated with the Minecraft and reweighting technique, and the results are obtained by fitting simultaneously 2 signal regions of the two different separate processes. In particular, here are used the diboson invariant masses, which are particularly sensitive to possible BSM contributions, especially at high energy. as it's clearly visible due to with the contribution depicted here in the plot. The results are quite interesting from this combination. All 20-dimension 8 operators from the Eboli basis were tested individually, so non-profiled, setting all the other operators to 0. No significant deviations were found with respect to the standard model, but several world best limits on anomalous quartic gauge coupling operators are set. In particular, as you can see from the plot on the left, the most stringent ones are for the operators clearly of the T group, which affect the gauge sector, given the input analysis makes a lot of sense. Finally, the largest global combination of EFT, that dimension 6 that we have in CMS, which includes a very broad set of analysis. This is done basically fitting simultaneously the likelihood of these several different measurements. Data is again collected in a span from 2016 to 2018, so LHC run 2. 64 dimension 6 operators here are considered, SMEFT-SIM, TopU3 L-symmetry, CP-even operators. 8 analyses are chosen and inputs. The inputs choice was, of course, driven by analysis that gave the maximal sensitivity to the full set of the operators explored, so complementary analysis, and of course that needs to be statistically independent between each other. As you can see, we have a very large set of processes, including Higgs processes, processes with bosons, with vector bosons, top processes. We have an inclusive jet measurements, and finally, as I mentioned, the electroweak pseudo-observable from SSC and LEP. A couple of details on the fit. This is quite complex due to the very wide and different nature of the analysis involved. Here, a likelihood ratio test statistic was used, but the likelihood is so-called hybrid. So basically, it's a product of an experimental likelihood and a simplified one. For the analysis for which an experimental likelihood was available, it was used. It basically preserves all the correlations and shape informations, and describes all the nuisance parameters. This is not available for all of them, clearly, only Higgs to gamma gamma, W gamma, WW, Z to neutrinos, and TT bar X. For all the other analyses, a simplified likelihood was employed. So basically, it's mapped as a multivariate Gaussian. The nuisance parameters are not included. The experimental and theoretical uncertainties are included in the covariance matrix and are, let's say, separate, not correlated between each separate analysis. This is used when the experimental likelihood is not available, but is also preferred in the case that the computational complexity is too high. Results from this very wide combination are obtained fitting one operator at a time, fixing to the standard model, so to 0 all the other operators, and you can see a comparison of the linear only and linear plus quadratic EFT contributions. It's important to stress that you can see from the bottom panel here basically how much every single analysis contributes to setting the limits on a single operator. So wherever you see bars that are not of a single color, that means that the combination is actually effective and extremely important in making more stringent the various limits. An example is, for example, CW, which you can see somewhere here in the middle. But in general, let's say, just by looking at the colors, it's clear how the combination helps and improves. A second kind typology of fit was done, so a profiled one with the Wilson coefficients not set to 0, but again, as previously, some have almost degenerate effects, so again, PCA is used. In particular, the information matrix is the Hessian of the combined measurements, so the double derivative of the likelihood with respect to the Wilson coefficients. And only 42 eigenvectors were in this case retained, and linear only fit is presented, and those are the results. In general, the results are quite compatible with the standard model. The deviations are mostly coming from the inclusive jet measurements. As you can see, The p-value is of 26%, excluding that analysis, and this analysis is particularly sensitive to PDFs. So in general, the conclusion is that the agreement with the standard model is quite good. Last but not least, a sneak peek into the ongoing efforts. We hoped to be able to show a bit more and maybe also show some data from this analysis, but it's not public yet. This represents an effort to combine direct dimension 6 interpretation coming from 10 different separate analyses. As you can see from the list of analyses, there we have BBF processes, a wide set of VBS processes, WW, so a diboson, and the triboson one. We can only, with this kind of direct measurement combination, so in which we have the full experimental likelihood combined from all the 10 measurements and we're fitting this, we can only, of course, combine analyses that have consistent and very similar EFT implementations. So we use U35 top-top U3L flavor scheme and W input scheme and operators coming from the Warsaw basis. We can only have a very limited set of operators to grant the highest overlap. In particular, we picked 6 bosonic operators which all analyses were sensitive. And clearly the implementation, the practical aspect is quite complex and to handle. We need to generate the events robustly. We generate everything with SMEFTSIN. Most of them were then privately generated through the CMS chain of Monte Carlos and so on. Then the statistical implementation is quite complicated. As I mentioned, we're combining the likelihoods, we're combining the data cards of those 10 analyses and fitting them simultaneously. There is a big effort ongoing towards trying to automatize as much as possible this process, as it's a combination of live measurements, so not all of them are public, so it needs all the analyzers from the different analyses to be active and participating. This is clearly, let's say, a complicated effort on several different levels, not only physics related. And to conclude, in general, we have, I presented a set of several recent combination of EFT measurements in CMS from different sectors individually, so top Higgs vector boson scattering separately, but also a very wide, broad global fit across all of those sectors. Efforts, as you saw from the last slides, are still ongoing towards these directions, and in general, the results that we obtained are interesting. There's no deviations found with respect to the standard model, but many meaningful constraints on the operators were set. And these studies prove that there is really a sizable benefit from combining results. So this is the direction towards which we are collectively going, also in view of Run 3 data, which are now starting to be available, and the first measurements are going to start probably to come out soon. This is it. Thank you very much.
Thank you a lot, Julia, for the nice talk. Any questions? Let's start from Torben, and then we go to Pamela.
Yes, I have maybe a bit more of a complex question. So when we look at a single EFT analysis, how do we decide which operators we want to include? Because when one then thinks about also a combination, it's not only important what the signal is very sensitive to, but in a combination we also have to include the modeling of our background, maybe for operators that we're not that sensitive to. And maybe as an example where I noticed this in your slide, I think you showed this TTH multi-lepton result. And I know that from Heft, TTH is very sensitive to things like the trillinear Higgs self-coupling, but I don't think I see here any operator that corresponds to the Higgs self-coupling. So if at some point, for example, we in Higgs get a little bit further and want to combine with single Higgs, yes, we would have to think about these kind of things.
But as you said, this is a very complex question also because it's, as you mentioned, basically, it accounts for several different layers of developing an analysis. So, of course, there is the physics target as well as the complication of setting everything together. From my experience in working in one of those EFT combinations, there, at least so far, the measurements were in the very beginning conceived separately and individually, and then were merged. So one needs to really account for which analyses are independent, statistically independent from each other, which operators they focused on, and for whatever reasons they picked any of those operators, and try to make that work together. With unfolded measurements, this is a bit less of a constraint because you have a lot more room for playing. But for example, for a direct combination, like the last one that I showed with no data and so on, there you see it quite clearly. There is a set of VBS measurements that are not have included bosonic operators. Some of them we don't have such a high sensitivity, but we needed to cover the broadest overlap for each of those measurements. So in general, this is really complicated, and trade-off must be made in every direction. In general, I believe that as we are currently focusing a bit more on combining measurements, since we have many measurements available from Run 2, in general, we have discovered that this is useful, and as far as I'm seeing right now for Run 3, there's a bit more of an interest in starting to plan out a bit more how we will combine measurements. This also actually kind of reconnects to the morning's talk, related to trying to make analysis a bit more, let's say, structured in terms of framework and in terms of the way everything is described, to make them a tiny bit more consistent, because, for example, trivially, nuisance parameters can be defined very differently depending on the framework you use, and that makes it impossible to benefit from combinations, because you need to correlate nuisances, otherwise a combination is useless. It's just, I mean, not useless, but it's way less powerful. So it takes also a bit of, let's say, planning in advance, which isn't always the first goal you set off with. So then you need to work with the measurements you have.
So it's also a bit about convincing analyzers to have a later on combination in mind already, even though that's not their primary publication, maybe.
Yeah, exactly. For example, for the last one I mentioned, it was a bit like that. It was a combination of measurements stemming from people that worked within the same framework, and the ones that started last had already the combination in mind. So, for example, focused on the operators that were interesting and so on. So yeah, that's exactly it, I would say, at least in my experience.
Sometimes it's very tricky also for analysis reasons, like ability analysis.
Yeah, exactly. This was actually very dramatic, because you don't want to rerun the entire analysis or change the strategy completely, or maybe you can't. If it's already public, you kind of have your hands a bit tied.
I strongly support the statement that we should have channels of, for example, single X, and maybe triple X, even in future, who knows. But one thing that I always miss in the EFTs, on which I work as well, is that, for example, there is this nice, let's say, access type ET in the VH, right? And then it's, or we always say, oh, it's all in agreement with the standard model. So the message is a bit depressing, and last year, for example, we were discussing that you can really interpret them within specific models, and that there are large efforts really to remap them very easily to models that could maybe give a hint to other people to look for a certain excess. So I'm wondering if you are organizing for that. So, for example, if it would. So what is the strategy? As soon as you see that some parameter deviates, can't we try to interpret and then give, let's say, a direction to people that are doing their searches? That would be, I think, would also help the FT people if we could do that.
Yes, I mean, I absolutely get your point, and thanks for the interesting remark and comment. I believe this is a bit more in the mind of people lately, now that many of the results are out and we really have everything laid out in front of us. And as far as I'm seeing, the idea of increasing statistics with Run 3 and maybe combining Run 2 and Run 3 is one of the directions in which we will explore this, in the sense of, let's say, seeing if the excess stays there or not, and then interpreting further. But I mean, I totally stand by your comment.
Thank you for your beautiful talk. You didn't say very much about the backgrounds, though.
Yeah.
How are they modeled? What I have in mind, coming from a theoretical perspective, is that they're large QCD correction, but they are flat. So you can always define a control region and extrapolate. But there are lots of electroweak corrections which can give very large effects in the large energy regime, in the large PT regime. Do you know how the backgrounds are modeled? What
Yes,
corrections are in those?
Well, depends a bit analysis by analysis. This is why I didn't really focused on this, because there's up to, I don't know, I think 25, 30 analyses that are in total combined in whatever I presented today. So it's a bit hard to go through each of them, but in general, they're mostly modeled through Monte Carlo simulations, and all of the analyses I mentioned, they're not actually fit individually, so only the signal regions, but control regions are fit for everything. So as for most of them, this is, let's say, good enough to constrain most of the most important background processes. For many of them, actually, non-trivial part, there's also data-driven techniques. For example, the ones, not the ones you mentioned, but the ones that stem mainly, for example, from detector effects or misreconstruction and so on. And in some of the analyses, also the leading order versus next to leading order becomes a bit of a tricky aspect. So this is treated differently, analysis by analysis, but in general, that's the strategy used. The one I described is the strategy used for Monte Carlo. So this is also why the fits are so complicated. You're not fitting a single region. Usually for a single analysis, you're fitting 6, 7 regions, depending on how many backgrounds you have to model and constrain properly.
Thank you for the nice talk. I had a question about slide 20, where you had this comment regarding the sensitivity to the PDFs when you consider JET data.
Mm-hmm.
Do you have an idea why this tension between the PDF and the EFT shows up, in particular in this case?
As a non-theorist in the room, probably someone else has a better answer for that. But as far as I understand, that is not particularly explored. It was, let's say, we go back to how do we define being consistent with the standard model or not, which Pamela was mentioning before. But this is quite actually consistent in general. So that's the, let's say, yeah, that's the answer to it.
Fair enough. Thank you.
Thank you so much. Thanks again, Julia, for interesting talk. Continue with.
Sure. It's a big jump with P chats. Which is a lot.
So we go from dibosons to di-Higgs, and we continue with the both from upper
Thanks. So, yes, this is an overview about the recent development and progress in di-Higgs measurements, so essentially ATLAS and CMS. Just to set up the stage, I mean, the usual quick introduction. We care about di-Higgs because it connects to the fundamental, let's say, properties of the scalar sector. So we define the existence of a complex doublet scalar field, which is phi. Phi follows the Mexican hat potential. So when electroweak symmetry is broken, we end up in one of the minimum, and then 3 degrees of freedom, which are represented by the blue arrow, become the W and Z polarizations. But then we have a residual degree of freedom, which is its quantization is the exponent. So we have a physical field H. And the good thing is that when electroweak symmetry is broken, the potential can be rewritten as there. So we have the Higgs boson mass, and then we have a trilinear and a quadrilinear interaction, and a constant which is orders of magnitude above what we have from cosmological observation. But here we don't care. So essentially, this interaction gives us a tripole H and a quartic H vertex, and their strength is directly the value of lambda. That is the value of lambda, which is related to the Higgs boson mass and the vacuum expectation value. This we know because V is known from, for example, the Fermi constant, so we have a prediction for this value. So MH now is known very well at the per mil precision. So if we measure lambda, essentially, we test the validity of this brown triangular Higgs mechanism in a way which is associated to the global properties of the potential, so overall the shape of this scalar potential. And that's why this opens all the X business, let's say. So how do we do it in LHC? We need to produce 2x bosons. The plot here is shows the at NLO, so maybe not the most up-to-date, but shows the cross-section of the reproduction modes as function of the coupling modifier, so lambda over lambda SM, so kappa lambda in general. And dominant mode is gluon fusion, which is the gray curve up there. You see it as a minimum around 2.5, 2.3, something like this. And this is because we have two diagrams interfering which are on the top. We have the trilinear, the one involving trilinear coupling, but then we have a box diagram which does not involve the self-coupling. And the interface is negative, the cross-section is very small. It's between 30 and 34 femtobarn, depending if you are, that's not the unit, depending if you are at 13 or 13.6 TeV. But yet it's the dominant production mode. It's 1,000 times rarer than single X. Then you have vector boson fusion in red, and then you have TTHH, and we'll see some analysis about these three later. So we get information on the self-coupling, essentially via the total cross-section, which is still the main access to the information, and then we can disentangle redundant hypotheses, let's say degenerate hypothesis, by using the differential information. So whether we access the low mass range or the high mass range, we can have some idea about the actual value of kappa lambda, even from points that would have the same total cross sections. So we have to choose a decay channel to do these measurements. And essentially we are lucky sometimes because we have many decay channels which are accessible at the LHC. And the branching ratio varies a lot across this display. So this is usual plot where you can see the decay of the 2x bosons, and then you have the combined branching fraction, and every check mark is one analysis covering the LHC run 2. And you see we cover essentially everything because we need to have as much as possible decay channels to search for this process. But then general philosophy is that we always keep either the leads decaying to BB or WW because the branching ratio is high, and then we choose the second decay as a compromise between the branching fraction and the purity. So going down, you typically have something more pure but also more rare. Or we combine many channels which have similar signatures with leptons and photons, and this would be a multi-lepton analysis, and overall we do the combined analysis from a, let's say, signature point of view. So what I'm going to show here today is essentially the legacy run 2 analysis combined, because all the analyses were performed and then they were combined, and then some first run 3 partial results. And this is done both by Atlas and CMS. A note is that there's also a lot of work on resonant analysis, so new scalars going to HH or spin 2 going to HH. This covers a big range of mass from threshold production to TV. It's not covered here for essentially sake of time, but this is also part of what is done in HH. So this is the summary of all the full run 2 results for standard model HH. So Atlas and CMS, this shows the upper limit for the various decay channels that were explored. And then first conclusion is that 2 experiments get similar sensitivity. We are about 2.4 times the standard model for Atlas, 2.5 for CMS, so it's very close, with an observation of 2.9 in one case and 3.5 in the other case. There's sort of a block of 3 channels which have the leading sensitivity, which are 4B, BB tau tau, and BB gamma gamma, with different order in between the 2 experiments. This was largely discussed and comes essentially from the way analyses were developed and optimizations, and we can expect this to improve and converge toward the best results as more time passes. And then we have other channels which are less sensitive, especially BBLL, multi-lepton, and rare channels. The one that you see on top in the CMS case are typically included in the multi-lepton analysis in Atlas. These are less sensitive, but altogether they still contribute to the final result. That's why we want to have the overall combination to maximize the sensitivity. Now, these results are mostly statistically limited because the process is rare. What matters now, the main uncertainties are the theoretical uncertainty on HH, which is order of 20% because of the choice of the top mass scheme. And this is the largest uncertainty for us. Then there is the background, X plus heavy flavor, which is also one large uncertainty. And then the leading experimental systematics are typically from the background modeling. And for B modeling, and then in part the BB tau tau modeling, so essentially processes which are which have more abundant background. Then this is the result for the measurement of the self-coupling, and I also put, even though we are moving towards a measurement of these parameters, so we typically now look at likelihood scans. I also put the one on the left, which is the limit as a function of kappa lambda, because it really shows our sensitivity varies across kappa lambda. It's not something flat, but essentially asymptotically we have the same sensitivity, and we exclude now all the regime where the pure triangle diagram dominates. As we approach the region with maximal interference, we see that between, let's say, 0 and 7, the signal becomes very soft, so our limit becomes worse, so this region is quite difficult to access experimentally, and that's where we benefit from combining different channels. And it's something that you see on the right plot, which instead is the likelihood scan for Atlas. On the left part, which is more hard, we have essentially beta tau dominating the sensitivity. On the right, which is in green there. On the right part, we have essentially big gamma gamma, which is in violet. And then the other channel will still contribute. So we benefit of having different analysis because we probe a different kinematics. Now, today we are at this sensitivity, so we are at the order of between -1 or -2 to 6 to 7. This is the range that we can probe today. And of course, there's a benefit in combining the channels to maximize the sensitivity. Now, the Atlas and CMS combination were also combined recently, and this was done by taking essentially this leading channel from the to analysis, so essentially the one that we saw before, but the CMS tau gamma gamma, VZZ for lepton, WW gamma gamma, PBL radonic, and VHH for B, because essentially for practical arguments of handling the combination, these were overall contributing to less than 1% to the final result, and this simplified a bit essentially the statistical treatment. And another modification done to the inputs was to let's say, implement the scaling of the single X background as a function of kappa lambda, so the indirect dependence. This was existing in all CMS channels, was not existing in some Atlas channels, so BB gamma gamma and BB was implemented. We don't have this in the Atlas multilepton and BBLL because we don't have a split essentially in the various decay channels. Again, we estimate the impact to be below 1% from this effect, so it's still quite safe. And these are just the expected and observed per channel constraints of the various combined analysis. This is more interesting is the combined result. And then, as you can see on the left, this is the upper limit on the signal strength as the sum of GGF and VBF, so the overall mu of our signal. And we observe 2.5 times the standard model, and we expect a 1.7, assuming that there is no direct signal, so as a standard, the new physics search. No? And then this type of expectation always scales down with the luminosity, of course. But if you assume that the standard model does exist, eventually this limit will flatten because you can't exclude a signal that exists. And this will be 2.8 times the standard model. Now, as a hint, if you are optimistic, you can see that the observed exclusion is closer to this one, would be the blue line there, compared to the mu0 hypothesis. Of course, the significance is small. It's still around, we observe 1.1 sigma, we expect 1.3, so we cannot claim a signal. But there is, if you want, some indication that we are approaching this signal and a lot of discussion, as you can imagine on this. But okay, somehow the same conclusions hold as per the individual combination, so it's a statistically limited results. The leading theoretical uncertainties are the one on the X production, the cross-section, and the X plus heavy flavor production. There was some discussion on this point because we have different assumptions on the experiment. This is assumed to be 50% the X plus heavy flavor in CMS and 100% in Atlas. We try to consider a common 100% effect. As of today, this is small. The change in the overall result is the order of the percent level. This is something we should make consistent in event 3 because still it's the same theoretical uncertainty. And then again, the modeling of BBB and BB tau tau are leading uncertainties. But all these are subdominant with respect to the size of the data set. And now in terms of signal strength, as you can see, we have let's say, 0.8 plus 0.9 minus 0.7. We are not at 0 by 1 sigma. Again, it's not a claim, but this shows that we are really moving from something which a few years ago was 20 or 20 times standard model to a measurement of this process, which we expect to have in the run 3, as I'll show a bit later. And again, you can see this is fully dominated by statistics, with some contribution from theory uncertainty and some contribution from experiments. Okay, so what can we do to use better our data? Essentially, we can have an EFT interpretation. Now, we discussed a lot about EFT, so I won't repeat too much, but essentially we parameterize the high energy, the new high energy physics effectively at low energies via an expansion of the standard model Lagrange. We have two things that are done in DAX. One is MEFT, so the one that has just been discussed. We have addition of operator, and so far we limit to MEFT dimension 6. And this is the list of operators with mostly the interesting one being this CH, so the trilinear coupling operator. The others also do exist, but they also correlate other interactions. So for example, in SMEFT, the TTH strength is correlated to the TTH-H interaction, which is at the center. The GGH correlates to the GGH-H interaction, and so on. And instead, in a more generic framework where we release some of the standard model assumptions, we have HEFT, the Higgs effective field theory, where essentially each of these vertex is an independent parameter, as written like here. So we have to do both. There's an advantage because in this case we can disentangle these interactions, for example, and in this case instead we can compare and combine with other analyses which are not the Higgs analysis. While I think HEFT is essentially exploring the Higgs. There is not much more HEFT results in other channels, at least in the Higgs top and the Higgs center. So these are some results. How this is done? We take the analysis, we model the signal in terms of cross-section and acceptance following the recipe which is there. It's essentially a reweighting in bins of the Higgs invariant mass. Now recently there was an improved description where you take into account the NLO effects from jet radiation that is documented in this other publication, but overall we reshape our signal to take into account the effect of these operators. And these are typical results, so you see some HEFT results here from CMS and from Atlas. There's a tension, again, in the one of Atlas, but this is essentially because of an excess in the low LHH. And then this is an example of a MEFT result from the Higgs BB gamma gamma. Now, what you see are essentially only 2D plots because there's a degeneracy between these operators. We cannot disentangle them, and that's why we cannot make a 5D simultaneous fit overall. So we limit to 2D plots. But as we see, if we combine, we can benefit of other analysis to break this degeneracy. And so HH was used as an input to the full SMEFT fit that was done by Atlas. So without going too much in the detail, because that's not the SMEFT Atlas talk, but there was this result published recently, which combines Higgs, electroweak, top HH, and precision observable from Lab Atlas and SNT. So for HH, essentially we include just the BB gamma gamma and BB tau tau, because they were the ones where we could model these SMEFT effects, and we modeled the Higgs effect and the effect of SMEFT in single Higgs background. We don't model the effects on, for example, TT bar or Drelian or other things. And then HH contributes essentially through the CH operator. This is what you see in this plot, which shows the constraint per individual operator that you get from the linear constraint that you get from all the channels and all the channels plus the Higgs, and you see that none of the bar changes essentially, but here. And you see two issues. One is that it changes. You don't see the blue bar in this case because the constraint would be above the limit that is put by authors to consider an operator as interesting. So there's a real impact in having the Higgs here. And then there is this tiny region here. Okay, it seems very tiny, but it's a place where actually the signal plus background becomes negative because we have rare analysis, and then you cannot really make a likelihood approach there. So this poses some problems. These analyses in the Higgs are not very well described by the parameterized Gaussian model, which is used to simplify a bit the treatment here. So overall, they are excluded in the PCA analysis, the one where you find the eigenvector results. So you can see this as a first step into seeing how the Higgs would contribute. But okay, at the individual operator level, the Higgs has an impact, so it's indicated there by the bar. So it still contributes. Of course, it's a drop in this sea of MEFT analysis, but you can have an idea of the impact, for example, from this plot where you do an interpretation in this 2HDM type 1 model, and if you just focus on if you just use single Higgs measurements, you have a type of constraint. If you include also the X measurement, you have a better constraint because in this model, you have a modification on the Yukawas and on the self-coupling. So in this way, you have more handle on these CFT effects. So there's a benefit in including the X. There's also quite still significant challenge in terms of modeling and in terms of statistical pattern, but it's being done. How much time do we have?
We are late.
Okay, good. So what I wanted to make is about SMEFT, sorry, and the inclusion of TTHA. So there's this recent analysis which studies TTHH production, and this is good because you can directly access this effective TTHH vertex. Now the downside is that this is a very rare process because the cross section is the third production mode, is below the femtobar level. It's 0.75, 0.85 femtobar, and it's very complex because you have the decays of the top, the decays of the X, and you have a very complex final state. So this analysis based on run 2 plus partial runtime data with up to almost 200 inverse femtobar, and uses three final state. One is at least 5B plus one lepton, one is 2B plus 2 leptons, and one is 3B plus 2 photons. So you have X or gamma gamma plus B's. And then again, you categorize the events by the number of B, the purity in the one lepton category, and then by the number of leptons in the essentially same sign multi-lepton, and by purity of gamma gamma. Overall, you categorize events based on how pure they are and what is the subset of the final state. So you end up with three categories and three marker decay modes, which have similar sensitivities. Overall, you get to an upper limit on the signal strength, which is around 20 times the standard model, which is not so bad if you consider that the overall combination of GGF plus VBF does around 2. Of course, it's far away, but it's still significant. And then what is interesting is to see the constraint on the TTHH vertex. You see we are between minus 0.4 and let's say 3.5. As a comparison, the full Atlas and 2 combination is minus 0.2, 0.6. So it's weaker, of course, but it's sort of an independent check of this vertex. And then I wanted to move to the second production mode, which is VBF. VBF is interesting because when you do the electroweak symmetry breaking, you can rewrite the Lagrangian term as written above. So essentially, you bind the masses of the weak bosons, the XWW and the XXWW, to the same piece in the Lagrangian. And then you end up having something which is the same manifestation of the same electroweak symmetry breaking. And by this reason, the longitudinal scattering of vector boson is suppressed because these two interactions scale together. So if you find a way, for example, a composite X, some dynamics which breaks this, to break this cancellation, you have an explosion of the cross-section and of the kinematics. So because the longitudinal scattering will scale like kappa 2V minus kappa V squared, with kappa 2V being the VVHH vertex and kappa V being the VVH vertex. And then you see in the plots on the bottom, as soon as you change your hypothesis of kappa 2V, you get a lot of events at high invariant mass, and then your cross-section can easily take a factor of 10 or even of 100 by a few units of change in kappa 2V. So you're very sensitive to this production mode, even if the standard model prediction is very small, is at the order of the femtobar. So we want to do a search in high PTH because we're going to have boosted events in this case. This is what is done. Again, this is from the combination of Atlas and CMS. For the upper limit on the standard model, we have the order of 40 times the standard model. So again, this is even weaker than a single TTHH channel. But on the VVHH coupling, it's actually a very tight constraint between 0.6 and 0.7 and 1.3. And the absence of VVHH interaction is excluded by over 7 sigma just with the RAN2 dataset in a simple framework where this is the only vertex being scaled. And again, this is because if we had no VVHH interaction, there would be no cancellation, and then we would have a lot of events that we should observe. So we sort of observe without seeing anything, we can say. And this is driven by boosted 4B, so it's really the analysis which is the most sensitive. A point that is being explored, and then I wanted to make, even though there's no results yet, is that actually this vector boson scattering also contributes to EFT in dimension 8. So if you check vector boson scattering diagrams versus vector boson fusion HH, you can see some similarities. And in the end, they are sensitive to the same operators. So this is something that you see here when you see a constraint on the same operator, in one case in VBS, and in one case on MHH, on HH analysis, the constraint is similar. So this is from a phenomenological study that is linked here. There is not yet a full analysis interpretation in Affix or CMS, but it is something that is very promising, which could add another random on this dimensionate operator, and could also help to increase the sensitivity on these effects and to bring together VBF-HH and vector boson scattering. Okay, so quick description of the recent analysis from the LHC runtime. The first is the Atlas VB gamma gamma analysis, which was recently redone by reanalyzing run 2 and then by combining run 3 data up to 2024, so it's about rendering less phantom. This gives a 50% improvement on the previous analysis just by the statistical increase. But then there is an improved categorization because with more data you can better split your data in more sensitive category, which gives you 10%. A kinematic fit, so an improvement in analysis techniques, which gives you 5%. And then a new bit tagging algorithm, which gives 20% in the analysis performance. So we move from the run 2 limit of expected 5 times the standard model to this limit of 2.6 times the standard model. This is 30% better than what you would have by just having more data. So there's an improvement in the sensitivity. If you see the limit there, just VB gamma gamma does as well as the full Atlas run 2 analysis for the run 2 combination, for example. So there's a real improvement in that. And in kappa lambda, we are close to -2.7, so again, similar to the full run 2 combination. So there's a big improvement beyond the simple luminosity scaling by having more data here and improving the analysis. You can see something similar in CMS, which also did a partial run 3 analysis with a smaller data set, 2022 and 2023. Main feature of this new work is that there is a new boosted BB category, even though the overall contribution, as you can see, is very small to the result. And then the test of two approaches are one, the approach when you fit essentially just the diphoton mass and you use the dijet mass in a DNN classifier, or to the approach when you fit as before, M gamma gamma versus MBB. And then the tagger is also improved because now it uses this particle net tagger. Again, we move from around 2 results of 5.6 times the standard model to a result that in the best case is 7.3 times the standard model, while we would expect 8.4 for a simple scaling. So again, this result is 15% more sensitive compared to a simple luminosity scaling. Again, analysis techniques are pushing the sensitivity of this analysis. Third channel, which has been searched for with the partial run 3 dataset, is the 4B by CMS, which features many changes and many improvements in the resolve analysis. So the two X's are reconstructed each by a pair of BJets. You have object level improvement, you have a better tagger, particle net, there is an improved mass regression. The run 2 was reanalyzed with an improved classification, so you essentially separate better signal from background. And then there's a new resolve strategy for the run 3, which benefits of new triggers essentially. The run 3 was limited by the fact that the trigger required 3 BJets, so you have a limited control sample. Now in run 3, there's a 2 BJ trigger and a parking data set, so you have a 4B region, as shown there, that you can use to estimate your background in the 4B region and have validation region from the 3B. And then your signal would appear again as an enhancement in the last bins of this criminal. Also improving the boosted analysis with better tagger and improved multi-class, especially for PVF. Overall, this goes to a sensitivity of 4.4 times the standard model. We can make the same exercise as before. We move from the run 2 legacy measurement from 4.3 to a run 2 plus partial run 3 of 2.8 times the standard model. This is 40% better than a simple luminosity scale. So again, even in this case, we get to a much more sensitive result. And you can see this in the main metric. So the upper limit there, the combined upper limit is 2.8 times the standard model, the kappa lambda constraint, and the kappa 2V. This is very sensitive now because it's dominated by the boosted analysis. So we have an observed of 1, essentially plus minus 10%. So it's a very tight constraint on kappa 2V. Final analysis from the LHC Run 3 is the new BBWW analysis by CMS, which is focused on the full leptonic channel, so what W goes to lepton plus neutrino. And this is done with, again, partial Run 3 data set with 62 inverse femtobarn. The challenge of this analysis, it's evident from this plot, is that you have a lot of irreducible variants, TT bar and the Radian plus every flavor. And the only way to suppress this is to have, again, deep neural network, like a separation based on machine learning. And so there are various regions classified by the topology, the production mode, and the number of weak works. And then in each region, you search for the signal as an enhancement in the last DNN bins, with some control regions on the right there to normalize the various background. And again, here there were several improvements in the betagging, in the strategy for the trigger, and in the way you classify the events. Again, we can do the same exercise. We move from something which was about 20 times the standard model in the Run 2 to something which is 18.5 times the standard model, but with a much smaller data set. So this is at equal luminosity, 50% more sensitive. An important improvement in the sensitivity here. One word about the future prospects. So first, by checking these results, how they improved and what to expect for Run 3, I think it's very likely that we will reach an evidence for the X in the Run 3, because you can take the partial results. We see that they scale already better than luminosity, but even if they scaled as luminosity now, and you do a simple combination in quadrature or Atlas and CMS, you get beyond 3 sigma, you get to 3.1, 3.2. So we can make big mistakes, of course, but I think it's very likely that in the Run 3 you get an evidence for the standard model X production by combining Atlas and CMS, which is a great result. If you think that 3 years ago we thought, okay, this was something maybe for the Illumina LHC. And then by extrapolating just the Run 2, so again, without the latest improvements to the Illumina LHC, we have these results. On the left is the result on the Atlas plus CMS extrapolation for kappa lambda. On the right is it informs us on how well we can constrain the shape of the potential with this information. But essentially, we expect to need two aptobarn to have a combined LHC observation, and then with 3 aptobarn, we can have each experiment with a almost evidence of 4.5 sigma, so let's say 4.5 sigma sensitivity per experiment with a full Illumina LHC data set. Overall, this makes 7.6 sigmas combined in the LHC. So we will see this process in the Illumi with all the challenges of the upgrade, of course. And precision of kappa lambda is expected to be about 30%. So this is about the level that we reach. We will be able to directly access the shape of the potential in the Illumina LHC. And so, to conclude, DAX is the key process that we need to study the self-coupling and to access the shape of the potential. It's difficult because it's very rare, and that's why we need to explore different decay channels. It's also interesting because we can use it as a tool for new physics in resonance searches, which are not shown here, but also indirectly, essentially via EFT. So far, this is done mostly in Bloom fusion, so dimension 6 SMEFT and HEFT. But it can be done also in VBS for dimension 8 operator, where there is large sensitivity. And as of today, let's say, there's a lot of effort on this by Atlas and CMS. The combined sensitivity from Run 2 is 1.7 times the standard model. We have already a few partial Run 3 results, which improve by between 20 and 50% the sensitivity at equal lumi. So we will reach an evidence for the X in the LHC Run 3. And in the future, harder to predict, but we should observe the X and have a precision of about 30% on the self-coupling. Thanks.
Quick one on slide 14.
Slide 20?
14.
14.
I always thought that the minimum of the correction was at the standard model, but it's like,
tiny off, yes.
Why?
No, because you also have the cancellation, but then you have also the self-coupling diagram, which doesn't play a role. Because you have 3 diagrams, no?
Yeah.
These 2 cancel, and then this one is also still giving you a sort of offset. So, it's at the edge of being a numerical effect there, essentially.
But
It's
the
very
answer comes
close.
from kappa v, not from kappa. I mean, in the third diagram, you don't
Yeah,
have
no,
kappa
but the
v.
point is that there's not an exact cancellation like this towards zero. So there's a residual small effect which plays.
Okay.
Yeah, a follow up on this actually. From the we saw this measuring trilinear couplings at LEP, where the minimum was also not necessarily the standard model value, but the cross section was limited by a certain point. The point here is you really should determine the limits by toys, because these parabolic limits are 68% +1 and +2 are wrong, which you can easily see by looking at this, right? If you repeat the toys, for all the values you get below the minimum, you'll get the same minimal fit, that best fit value. So it's very far from Gaussian. And if you're above that, you get two solutions as you see on slide 18. Yeah, and you can even get disjoint intervals, of course, which you also see in the slide 18. So you really should evaluate if you're not the limits by toys, not just by cutting on the likelihood function.
I think these checks are sort of regularly done when you have this type of searches. But
Sure.
I agree that yes, it's just that it's very expensive. For example, in the combination, it's very hard to make toys because
Yes,
it
I know.
already asymptotically it's maybe a few days or over time.
Yeah.
But yeah, it's a good point.
But very often we do, and then we quote typically like how much they deviate.
Yeah, sure. Yes, just a warning.
One more.
Yeah, let me go back to your comment on glue-glue fusion, that there is a cancellation between triangle and boxes. That is saying two things. One thing is that any new physics coming through the same kind of loops will come in the same perturbative order. The fact there is a cancellation in the standard model, it means that that correction can be enhanced a lot. So my question is the following. When allowing for new physics, you either change the trilinear coupling or the top Yukawa, or you jump onto the fully fledged EFT. But if you have new physics, I don't know, squarks or vector-like tops, in the dynamical range of the LHC, say 1 TeV, so that you cannot use any EFT, which would manifest themselves as a threshold. There is a cut in the Passarino-Hellman function. Is there any analysis, a simplified analysis, which can try to capture that? Has anybody looked into that? At the end of the day, in a simplified model approach, you will need 5, 6 parameters to model a spin 0, a spin half, even a spin 2 object going around those loops. Yes. Has anything been done in that respect? It's what they call a hybrid EFT.
Yes.
Where if you decouple the fully fledged EFT, you're left with something which is not the standard model, but something else, which lives at low scale, at the dynamical scale of the LHC. Is anything being done?
There's a lot of discussion on, there's the resonance searches, but we just...
No resonance, this is a threshold effect.
There was a big discussion because essentially in the interplay between this new scalar and the standard model, so I guess it's what you're saying, there's not a way to make this so far generic enough to make it sort of model independent without targeting a specific model. It's something that is being discussed at length about how to model properly some scalar which is at the, let's say, some particle, some effect which is at the level at the LHC energy, and give some peak deep structure or something like this. There's a quite extensive discussion in one of the CMS combined paper which shows in which form, let's say, to which extent you have this non-simple peak structure. But I don't think so far there is a clear prescription on how to do this. This is mostly an input that would be the experiment. But I agree that would be.
I think the prescription exists, the implementation doesn't.
Yes,
I think that's the problem.
Stefano, I think what you said is valid, but would it be needed? Because if you're coupling to the standard model particles, you would see it in something with fewer legs and a simpler topology, say through an S channel.
You mean open production?
Yeah.
Yes, that's true. But you can cook up.
You can single Higgs.
No, a single Higgs is not. You cannot use the same argument. There's a technical point to it. But in open productions, right? You could. But you can cook up theoretical models where open production is suppressed because it's a compressed spectrum or whatever. So you could actually see some evidence of BSM physics first through this indirect probe, then a direct open production.
For the vector-like works, I think there was something from CMS on PKHH associated production. And there they had a couple, it was still model dependent in the sense that it was not so generic, but there were a couple of models that had vector-like works tested through PKHH with the argument that you have it more enhanced. and double tops and double hits than PKH simply. But in very, very preliminary studies, I don't even remember if it's only in a PhD thesis even or also in the paper. Have you ever follow up? No. Anything else? If not, thanks a lot. Look again. Yeah, so the idea was we go through the boson, we go through the Higgs, and then we also look at the tools that we have. So we'll focus on flavor tagging. This should be up in a bit. Thanks a lot. And you have a pointer.
Thanks. So, hello everyone. Today, on behalf of Atlas and CMS collaboration, we will go quickly on recent flavor tagging developments in our experiments. But I'd like to start with a little bit of introduction to, let's say, start the discussion. So, as far as we know, many file states that involves X, Z, W, and top quark basically contains heavy quarks as final state. And this is, sorry to be a bit trivial on that. But for example, the Higgs boson and its large, let's say, decay mode is going to a pair of bottom and anti-bottom quarks, 60% of, basically 60% of its branching ratio. Also, the Z and W boson in their hadronic final states consist of a huge amount of B or C quarks at the end. And of course, maybe like 100% of the time, we have the top quark producing a B jet at the end, a B quark at the end of, let's say, retroweak decay. In general, though, a quark, whatever quark, not just, of course, B or C quarks, produced at LHC undergoes an initial state of parton shower, where basically partons are emitted from a quark that eventually hadronize in a bounded state that we call actually hadron, and we reconstruct it as a, let's say, singular object that we call jet, both in Atlas and CMS. All the jets are similar to each other, but B and C jets have some particulars and some, let's say, distinctive features. The main one from B and C jets is the presence of their, let's say, relative hadronized meson, or what we call a B meson or a D meson inside. And the distinctive feature and the characteristic of such mesons is the fact that travels a measurable amount of, let's say, length in our detector, and so therefore we can resolve this distance and we can tag the jet using this kind of information. So what we do is actually reconstructing what we call the secondary vertices, which are, let's say, agglomeration of charged particle tracks coming from a vertex that is displaced from the primary vertex one, where basically the interaction of proton-proton is happening. So what a flavor tagging algorithm is doing is basically we take a jet, that can be whatever jet, use some models, most of the time are going to be machine learning models, to tag the jet to be a B jet, a C jet, a light jet, or a tau jet, so hadronic decay tau. The status of the art of Atlas and CMS collaboration flavor tagging algorithm is depicted in these slides. So on the top we have Atlas GN2 tagger, which is the revolutionary, let's say, tagging algorithm that we used for the run-2 full run-2 analysis, and also now for the partial run-3 analysis. While in bottom panel of this slide, we have the CMS UParty, which is very similar to Gen2M, but we are gonna let's say delve a little bit more inside that, so we can start a discussion on this. So as all the machine learning algorithms, we need inputs to provide to the network, of course. Regarding Atlas, so what we are using for as input to Gen2, we give the full set of charged particle tracks to the network as token to a transformer. Well, basically, as a feature of such charged particle tracks, we give, for example, all the kinematics information, so basically the four momenta of the charged particle tracks, but also the impact parameter. So basically, how is displaced a track with respect to the primary vertex? It's a proxy of that. From CMS side, the full set of particles is used by, let's say, using the collection of particles reconstructed with the particle flow, very good particle flow algorithm from CMS experiment. They give directly all the set of particles as input to the network. Of course, after the first step of, let's say, initialization of such inputs, we need to give this kind of tokens directly to the core of our models, which is a transformer model. So we should leverage the attention mechanism in order to, let's say, enhance at maximum the performance of the network. And at the end, what we have is as output from those transformers model, transformers layers is basically a refined version of what we gave as input to the network. So refined charged particle tracks for GN2 and refined particles for CMS. And then at the end, the last thing we need to do is basically provide those objects to a multi-layer perceptron, so a basic, simple machine learning layer in order to perform what we need. So jet flavor prediction. So is a B jet, is a C jet, is a light jet, is a tau jet, or so on. It's not the end of the story. For example, for Atlas, what we are doing for GN2, we are not just targeting to do jet classing, jet classification. What we also are doing are some auxiliary tasks, so some tasks that are not the main one, but are helpful for to the convergence of the network. Something very similar is performed also in CMS, and what they add also is an adversarial training to, let's say, tackle some potential mismodeling learning of the network of, let's say, what we give as input to the network, so Monte Carlos. The performance of the network, we usually, let's say, benchmark it with showing the actual, let's say, background rejection for Atlas as a function of the B-jet efficiency. Since we don't want to be, let's say, more clear between each other, they use the inverse, CMS they use the inverse of the background rejection, so the misidentification efficiency. But basically what I'm trying to highlight here is that for the left plot, so in GN2, higher is better, for the right-hand side plot, so CMS U bar T, lower is better. So basically, let's say, common general things is that the fact that and the switch from a transformer model from the previous, let's say, status of the art of algorithms that was based on deep set architecture is clear and evident between the two, let's say, experiments. So we have seen very, very nice improvement both in B-jet, let's say, efficiency, and so background rejection of any backgrounds that are, let's say, polluting the B-jet signal phase space, but also the C-tagging has improved by far by switching to transformers model. Of course, the performance that I've shown you is just on simulation, but this can be the end of the story, because of course any let's say machine learning model that we are training on with the supervised learning on simulation, we should, of course, then apply it on data. And sometimes can happen that what we learn actually is the simulations and not the real, let's say, situation. So what we are seeing in our detector after the real protocol collision. Therefore, what we need are calibration. So what we are tackling by those mismodeling effect that we are learning inside intrinsically by our model is perform, let's say, what we need to do is performing this calibration of those models on, let's say, phase space region where we are enriched of a category that we want to calibrate. For example, we want to calibrate B-jet in a certain B-tagging scores. What we need to have is, let's say, phase space where we have more B-jet, we are enhancing of B-jet. In GN2, so in Atlas, what we are doing is targeting, for example, calibrating B-jets in the TT bar 2 lepton phase space, C-jets in TT bar 1 lepton, and light jets in Z plus jet. While for CMS, they calibrate a robust party, which is a similar version of U bar T. U bar T is not yet calibrated, but it's going to be in a bit. They are using different phase space. For example, B-jets, they are using QCD multi-jet with soft mirror requirement, using 5 different methods between, and combining them all together at the end, while light jets are performing QCD multi-jet as well. So here I'm posting just to give you some, let's say, references if you want to go in more details how it's performing this calibration. But the outcome at the end is what we call a calibrated tagger. What is a calibrated tagger is basically the tagger, the machine learning model that performs now equally on data in Monte Carlo. You see, for example, the plot on the left, which is from Atlas and GN2 in particular, that basically we have the performance on simulation, which is the GN2 with the empty dots, and the performance on data, which is the, let's say, field dot. And as you can see here, we have differences, but not that much in terms of data and Monte Carlo, let's say, disagreement. This is shown for both B-jet efficiency, so both for B-tagging, but also for C-tagging in the next slides. And on the right, we have the same version, but from CMS robust party tagger. As you can see here, basically the uncorrected performance was basically the one on simulation with respect to the corrected, so on data, with the application of scale factors. You see here we have a drop in actual performance. This is something intrinsically that we are seeing, because of course we are biased intrinsically and naturally towards simulations, because we are performing training on that. But let's go in the what is going to be the next algorithms that we are going to leverage for full run tree analysis that are coming from both Atlas and CMS. So here I'm depicting Atlas GN3, which is the update of course GN2. They look very similar in terms of the diagram that I'm showing, but maybe someone already has spotted some different things, but I'm going to highlight it right now. So basically what we added on top of GN2 in Atlas is the presence and a tag on each charged particle track to be a muon or not. Basically is a reconstruction tag that says if a muon was present tagged as a track. The electrons, which is basically very similar to the muon concept. So we have electrons that possibly can come from semi-leptonic decays of B mesons, and therefore can be leveraged as a proxy for B tagging or C tagging. And last but not least, actually, I think the most important is the inclusion of the neutral particles inside our tagger. So we use the calorimeter information also now as input to the network in order to perform what we need to do, so jet flavor tracking. Not just in input sites, also what we add are new auxiliary tasks. For what we are doing is jet PT regression on top of GN2. The heavy quark charge prediction, basically if a quark that is, for example, a B is a B or anti-B or C or anti-C. If you want to delve a little bit more on that, both Atlas and CMS published very nice results on this, so you can have a look. It's very fresh and new from last week. And also here, last but not least, what we added on top of that is the track particle identification. So if a track is a pion, is a kaon, and so on and so forth. From the CMS side, they switch from U-T to U-T B2 that let's say surf the wave of the scaling of their model. So basically they doubled both the training statistics and the training on trainable parameters, and the performance improved by a lot. And also they do this test of trying to fit the scaling law model in order to see if it is actually flavor tagging is scalable as well in CMS, and the hypothesis on the right is showing exactly that. So the performance of the network are here shown as before. So on the left we have GN3 that, as you can see here, improved by far with respect to GN2 with the inclusion of these new inputs that I was mentioning you. We improved by a lot, like 1.8 in C-jet rejection, 2.4 in light jet rejection, times 5 in tau jet rejection, up 70% B-jet efficiency. So for example, if you let's say cut a line on the 0.7 on the x-axis, you see this improvement. And it's difficult on the right-hand side plot because the CMS doesn't provide a ratio plot, so I try to do it by hand, by eye, but it should be around 1.7 and 1.6, the improvement in C-jet rejection respectively, and light jet rejection. Not just B tagging, as I said before, we also are trying to aim C tagging, and the results are reassured. I'm not gonna go into much details on that. So algorithms of the future. What I mean here is basically using algorithms that are already present, but for the future in terms of the potential benefit that we can have of using a transformer model, for example, for what is gonna be the iLumi LHC Atlas upgrade, so ITK detector. So what the flavor tagging team of Atlas did is actually to train GN2 model with dataset collected I mean, simulated, of course, with the ITK template, and the performance are shown here on the right, and there is a comparison between the RAM4, so the Illumi LHC simulations in a high jet PT, transverse movement to phase space, with respect to the RAM3 one, with way less pile up, and the performance, as you can see here, is improved, even though in RAM4 we have way more pile up. That is actually very affecting our let's say jet tagging performance. From the CMS side, also what I want to, let's say, highlight is the results that they got with the new and updated online BEC tagging algorithm that now is leveraging particle net, which is a graph neural network. And as you can see here from the plot on the bottom, on the top on the bottom, a plot that is showing B and C jet tagging efficiency and a comparison with respect to the offline one. The performance has improved by far, and also I think it was mentioned by Luca before that this was used in the 4B analysis. The X4B analysis has improved a lot. Here, last but again not least, I just want to highlight the connection and the correlation that we have between flavor tagging, which is basically a software-oriented discipline with respect to physics, because of course we are using such models in order to do some physics at the end. So I just want to highlight the main analysis that leverages this kind of updates of flavor tagging algorithm. The first one is the Atlas DX BB Gamma Gamma that also Luca was telling us before, that is showing basically a huge improvement with respect to the previous round by including GN2 that was quoting at plus 20% with respect to the previous round. But also on the bottom panel you see the Atlas VHCC high Illumi LHC projection that is showing the upper limit on the discovery of the VHCC process, because of course H2CC still is not yet was not yet found. And as you can see here for Illumi, when we jump with a scenario with the GN2 included in the analysis, we basically get more data, of course, like 700 inverse vector in total integrated luminosity, something like that. From the CMS side, what I said just now is basically the inclusion of the online tagging for the DX4B that improved by a lot the signal acceptance for, let's say, doing all the residual analysis that of course the team was doing. The output was huge and the results were amazing. And last but not least, the CMS VH TTH2CC process and analysis that is actually at the moment the best limit. They got the best limit so far on the Charmy-Gawa coupling discovery using some machine learning models such as particle net, so a graph neural network, and also for a signal and event categorization with a transformer-based architecture. So as conclusions, I want to highlight just two main things. So the fact that transformers has actually brought great performance improvements, yes, in flavor tagging, but also mainly in analysis that, and so in physics research, that is something extremely good and actually interesting to see. And also what I want to highlight is the fact that new models such as, for example, GN3 and UPRT, new version of UPRT, are gonna be the, let's say, leading in the sector for entry analysis in the coming future. And yes, basically that's it. Thanks a lot for your attention.
Questions? Go ahead. For the Charmy-Gawa coupling, so our projections were at 1.6 times the standard model, not really sure. But now with the GN3 or maybe with CMS work,
it's
it will be much better. You have an idea of how much could be?
Yes, actually yes. And we can do some maths together later, but I can give you, let's say, some numbers before. So in C tagging, we improved a lot. We know that BHBB and BHCC are, let's say, flavor tagging for those kind of channels are, say, the best algorithm so far that we can use. Improving what we expect is actually very similar from the switch from DL1D to GN2. So we expect something like 40-30% of improvement. What we can do is to redo the game that we did a couple of months ago, actually last year, to do the scaling of the legacy analysis with the GN3 algorithm, of course. But we expect very similar things.
Right. Thank you very much for the nice overview. I have a question about the robustness against mismodeling in the Monte Carlos, and how, what the measures are, how you can essentially measure how robust you are against, say, modeling in Pythia.
Yeah, so measuring the robustness of, let's say, Monte Carlo dependency is something basically that at the end is gonna end as a calibration measurements, because what we include, for example, in Atlas is not just data Monte Carlo mismodeling, let's say, but also Monte Carlo maps. So basically, we measure how it performs in a alternative generator with respect to another one, and we perform maps in order to, let's say, tackle all the possible generators that analysis are going to use. So I have a flavor tagging algorithm that is going to use Sherpa samples in an analysis, so we have, let's say, the map to go to one to another. How the mismodeling of a, let's say, precise, let's say, model, Monte Carlo model, is difficult to answer, let's say. How
I wonder how you, because when you calibrate, you select a certain data sample, which has been essentially labeled to be a TT bar type of event,
Yes.
which you correlate with the corresponding theory simulation.
Yes.
So isn't that a bit circular? That you can essentially, these are the events which Pythia predicts should be roughly TT bar, so this I get a label TT bar, I enforce it, that it maps onto each other.
But then we apply, for example, the calibrated tagger to another phase space completely different, Z plus jet, for example, no?
Okay.
So you see what I mean. So basically, yes, there is a, if I'm doing TT bar with a flavor tagging model, then that I calibrate
many of the
on
plots
TT bar.
always show TT bar curves, right? So it's a
What?
bit, many of the curves show always, oh, these are TT bar events. I mean, if you're
Because we are training on TT bar. That's the point.
Right. Yeah. Okay. Good. Yeah, maybe we can discuss
Yes,
a bit
sure,
more
100%.
details.
I mean, it doesn't matter where you train. You can train on XBB as long as you are reaching
Now,
some
you
samples.
introduce a certain correlation with the rest of the event,
No,
radiation.
You eliminate. You try to eliminate this kind of event-wide correlation by training at the per jet level. So you marginalize everything that is at the very event out. So there might be a small effect that survives. And this is why you have calibration that are, on digest event, different things, but we don't see any mismodeling that would trigger this kind of effects to be relevant with the precision we have.
Thanks for a very nice talk. In your intro slide, you mentioned also the Higgs boson as being an object became predominantly in BB bar, but you didn't use it for calibration purposes. I understand that it's not as numerous as TT bar, it's not as clean as Z plus jet, okay? But if I think of BS, and you wouldn't do it if you want to improve the measurement of the decay, the standard model Higgs in BB bar. But if I think BSM, any new physics model with an enlarged Higgs sector, any companion Higgs boson would primarily decay to BB bar unless it's very heavy. So the question is, what would it gain? What would you gain if you included in calibration Higgs to BB bar when using the tagger in the search for new Higgs bosons? Because we're talking of spin zero objects and so on and so forth. So the distribution of hadrons in your jet is different with respect to spin 1 or spin half.
Yes, because this is also connect what
Yeah, it's
Francesco
connected
was
to-
saying. Because
yeah.
what we are doing is a training at jet level. So basically, we are not considering at all the, let's say, event stuff. So basically, out of million of events, we have how many jets inside. We are trained on top of those jets. So all these, let's say, event level, let's say, information are, let's say, a bit separated, because we are basically what we are calibrating is the jet showering, so all the quark showering and the hadronization of a quark from Pythia, for example. That is a model. Then, in principle, a Higgs boson that decays in BB bar and a TT bar process should be the same in terms of simulation at least. A B jet should be equal. Then, of course, a jet transverse momentum from a Higgs boson is different from a TT bar one, of course. But what we are doing is tackling this, let's say, this distribution of jet PT by flattening in the training. So basically, all the jets have the same jet transverse momentum. We train on top of the.
Maybe just to add that there are phenomenology at work. Lucas, for example, at some point will connect with one of these things, probably not, but correlated to what Tobias was saying, if you think about this reconstruction step as Lego, so you train the tagger and then you have your analysis sensitivity. If you have a machine that is able to minimize from the start, then you have what we are talking about precisely. So this has been proposed, but the issue is how do you calibrate that?
Especially since we're still measuring Higgs to CC bar.
Yeah, thanks. Thanks to you. All clear now.
Last question. Yeah. I have a curiosity in a similar topic. But how do you, so this is done in simulation. So how do you assign a label to the jets?
Okay, yes, good question.
Yeah,
so basically, it's a hadron-based labeling. So basically, we look into the truth particles inside a jet that we reconstruct, because of course we link the charged part, for example, in Atlas, but I think it's the same in CMS. Basically, we look at the truth particles contained inside the jet, and if we spot a B hadron, we label as B hadron. If none of B hadrons is present, then we look at C. There is a D meson, okay, then it's a C jet. There are no D mesons, we look at tau jets. So basically, if an hadronically decaying tau is present, then it's a tau jet, and all the others are light jets. That's the labeling that we are doing. Of course, simulation.
We still look at the reconstructed jet.
Yes, we linked from the reconstructed jet the truth particle of the, let's say, charged particles that are inside the reconstructed jet. So the reconstructed jet is composed by charged particles that are, of course, simulation based. So we have a link that go back to the truth particle that produced that track. Yeah. And yeah.
So okay, I believe if you take anti-KT, this is not robust towards, for example, a radiation with flavor which is not reconstructed. So this can change the.
Yes, the labeling. This labeling actually is the best one in terms of, let's say, infrared collinear safety stuff. But also there are other let's say, flavor labeling scheme that are being developed right now that is improving by a lot. For example, like gluon splitting in BB bar, that is actually the moment that there are studies saying that this is a B jet or a gluon jet, and all these things are actually very, very understudied at the moment.
So thanks again, Michael, and thanks to all
All right, thank you very much. Welcome to the first Working Group 1 session. And we were starting off with Timo Jansen talking about accelerating theory with machine learning. Take it away.
That's right. Thank you. So, as an introduction, I want to motivate this work. So, the thing we are looking up to is the high luminosity LHC, going to start around the year 2030, which gives us about 10 times roughly as many data. At the same time, we have a limited compute budget, and the projection by both Atlas and CMS show that we are probably over the budget. So we don't want the predicted line to be above the budget line. So we have to invest some R&D to work on the speed and precision of our simulations. So where can we actually save? The computing models from Atlas and CMS show that the Monte Carlo event generation is between 9 and 20% of the total compute budget at CPU time. So it's a significant part. We should also work on the other parts, but that's not my job to do. So I'll focus on the event generation. And if we look at this Sherpa analysis on the right side, we see that then a multi-jet merged NLO calculation is dominated by the tree-level components. And that is mostly the high multiplicity parts of that calculation. So we should focus on that. In my opinion, machine learning and Monte Carlo event generation is a natural fit. So event generation is already a high-dimensional generative modeling problem. So we have a representation space, typically a unit hypercube in our case. We have a generator, which is our phase-space generator and the Monte Carlo event generator. And then the generator maps to a data space, which is the space of our form momenta, including all observable definitions. So from a data science perspective, the differential cross-section is an unnormalized probability distribution, which we can learn. It's highly non-trivial. It's conditioned on many parameters, which we want to vary. Something that is special in our field is we have excellent training data. It's practically noise-free. We just simulate as much data as we need. It's expensive, but it's high quality. We have strong inductive bias. So we know a lot about the physics behind the simulations. We can build this into the simulation. And we have special challenges. So we have very high precision demand, which you wouldn't have in other applications, like for image generation, mostly needs to look good. But we really want to get even the rare events right. We have hard constraints, for example, kinematic cuts, or on-shape constraints, or energy momentum conservation. And at higher orders, we have to deal with negative weights as well. So in this talk, I'll focus on two methods. One is a generative task for phase-space generation. And there we want to learn phase-space remapping, which we do with normalizing flows. So we learn a map from a simple distribution to a complex target distribution to have an accurate proposal density for important sampling. And I'll show you applications from leading order up to next to leading order. And the second task is a regression task. It's neural surrogates for matrix elements, for amplitudes. And there we want to reduce the number of calls to the expense of 2 matrix elements. And to debias our surrogates, we can do a second unweighting step to get a right description again in the end. And I'll show you realistic applications where we don't have to compromise on the precision. Okay, so what do we do in Monte Carlo event generation? So we have a full featured simulation going from high to low energy scales. We have at the center, I have this pointer around. Yes. So at the center we have the hard interaction of quarks and gluons, which we can describe with perturbation theory. So this is first principles. And then we factorize from that other parts like parton showers and particle decay, heteronization, and so on. So in this talk, I'm going to focus on the hard interaction, which is the most expensive part typically. And the tools that we use all are Monte Carlo integration in the end. So we want to integrate our differential cross-section given by the matrix element squared times the loads invariant phase space times PDFs and cut definitions. And we map all of the phase space variables to a unit hypercube. And then we use Monte Carlo integration, so we approximate the integral by a sum. The easiest case, we use uniform sampling. If we want to do better, we use important sampling, so we come up with a proposal distribution that approximates our target and try to reduce the variance by that. And if we want to do even better, we can use a multi-channel, where we use like 2 or more different channels that approximate different parts of the target to get a nice approximation. And then if we want to do IID sampling, so generate unweighted events, we have a limited unweighting efficiency, which is given by the mean of the weights divided by the maximum of the weights, where the weights are this ratio between the target function and the proposal. One more thing we can do, and which we typically use, is Vegas. So Vegas is a piecewise constant density over the hypercube. It's a factorized ansatz, so we look at only the marginal distributions, not at the whole joint. And then we simply adapt bin edges to equalize the variance among the bins. So it's like adapting a histogram to your target. And this works really well as long as your target is factorized. And then if you use a multi-channel, you can actually use this in each of the channels of the multi-channel. The limitations of this approach are that okay, the channels are not perfect, so we have interference effects, we have complicated cut definitions, we have high-dimensional correlations, which you don't get with Vegas. The number of channels scales badly with the multiplicity, so for high multiplicity processes, we have a lot of channels to deal with. The unweighting efficiency is dominated by the worst weights because of the maximum of the weight going in there. So it really scales badly. And then the Vegas factorized ansatz does not allow us to learn the actual joint. So if we have like something which is on the diagonal of two variables, Vegas only sees the marginals, and then we get these phantom peaks. Okay, that brings me to normalizing flows as an alternative to Vegas. So normalizing flow is a generative model which is based on the change of variable formulas. So if you have a transformation psi transforms our base variable or latent variable to our variable x, then the distribution of x is given by the distribution of z times the inverse of the Jacobian determinant. So we know how to transform a simple distribution into a complex one. And then the key properties to make it a normalizing flow are it's invertible, and that allows us to evaluate the probability density exactly, which we need for the important sampling weights. It's parameterized by neural networks, so we can profit from all the optimization methods that have been developed in the recent years. And it's composable, so like we can compose the Vegas map with phase-space mappings in the event generator, we can also compose several normalizing flows. So that makes it a very nice candidate as a replacement for Vegas. And the way we do this is, instead of using Vegas here in the chain, where we map from the unit hypercube with a uniform distribution to a non-uniform distribution, then use our phase-space mapping to bring us to the physical space. We just replace Vegas with the normalizing flow, which now is able to learn an actual joint distribution, which gives us a better description of the physical distributions and a higher acceptance rate for the unweighting. So how do we implement a normalizing flow? I want to present two different kinds of normalizing flows. So one is coupling layers. In coupling layers, you split the input variables into two parts, A and B, and then you transform only one of them. So you transform only part B here. And that gives you a triangular Jacobian. So the Jacobian determinant is just the product of the diagonal elements. And well, obviously, just transforming one part of the inputs is not enough. So to transform everything and make all components influence each other, we need to use a layered map where we compose several of these coupling layers with permutations in between. So the other kind of normalizing flow is continuous flows. Here we look at a transformation continuous in time. So we get an ODE with this velocity field V. We make that velocity field a neural network because we don't have to invert this part. And then for sampling, we simply solve this ODE numerically. So we have to integrate over the neural network velocity field. And then for inference, if we want to evaluate the probability density, we have to solve the ODE backwards. Now, the numerical solving of the ODE is rather expensive because we have to do many steps. So people came up with a simulation-free training method, which is called flow matching, and that makes the training much, much faster. So the training part basically is solved. Inference is still slow with continuous flows. So in the first application I'll show, our reference is this Pepper event generator, which is a GPU parton level event generator, extremely parallelized, optimized for high throughput. It's using Behrens-Gilo recursion for the matrix elements, and for the phase-space sampling, it's actually using a single channel sampler, because it turns out for many processes you actually don't need a multi-channel, as long as you're dominated by the jets or the jet cuts. So if you sample in the variables that you use for your cut definitions, PT, eta, phi, it works really well. And it's basically perfect to apply normalizing flow to, much nicer than having a multi-channel. And also, Pepper is using helicity sampling to avoid the helicity scaling. And to deal with that, we condition our normalizing flows on the helicity state. So we learn the conditioned distribution, which is something that would not be possible as easily with Vegas. To talk to Pepper, we developed a simple interface where we do our random numbers, we put them into our normalizing flow sampler, which produces non-uniformly distributed numbers and the Jacobians of the transformation. We write that out to an HDF5 file, which is read in by Pepper, and Pepper again writes out events as an HDF5 file. That's very simple, very generic. We looked at Z plus jets and TD bar plus jets production at the LHC with up to 5 or 4 jets in the final state. It shows the protonic channels with many gluons. Now dimensionality goes up to 19 dimensions, and we have up to 256 helicity configurations, which we put into an embedding layer. And our baseline is the Vegas trained on a lot of events, so it's really converged. The flows we train on 170 million events. So it's quite a lot, but I would still learn more afterwards. But at some point you have to stop. Okay, these results show the unweighting efficiencies. So the acceptance rates of events when you do unweighted event generation. And on the left-hand side, we see Z plus jets, on the right-hand side, TT bar plus jets. On the x-axis, we have the multiplicities, the number of extra jets in the final state. And we see that especially for the high multiplicity cases in the Z plus jets example, we get really huge improvements. So with the continuous flow, which is labeled ODE here, we get up to a factor of 200 better unweighting efficiency than Vegas. The TT bar case, it's a bit less because the baseline is higher. Here it's about a factor of 25. In both cases, we see that the coupling layer flow is typically below the continuous flow. And for the highest multiplicities, the performance really drops off, and I'll come back to that later. These are the distributions of the important sampling rates. So what we want to see here is a really narrow distribution. So we reduce variance of the weights, and especially for the unweighting, reduced endpoint, so lower maximum. And we see both here. So compared to the blue Vegas line, we have much more narrow distributions in both cases. The ODE flow, the continuous flow, is doing better than the coupling layer flow. And especially for the maximum weight, we get a huge reduction by large factors here. But you have to remember the ODE is slow for inference. So calculating the weights is expensive still. And we found one way to deal with that, which is these regression flows. So for this, we have to look into the training objectives. So if we train a continuous flow with flow matching, we have an objective that is local in space and time. So we have a defined coupling where we couple basically points from the base distribution to points from the target distribution, and we connect them by straight lines. That gives us a defined local objective, which is good learning environment. The coupling layer flows we train by a maximum likelihood estimation. So we minimize the KL divergence, which is defined at the distribution level. So it's a global measure, and the coupling is not explicitly given, so it has to be learned implicitly, which can be expected to be more difficult in practice. And this WAC flow approach just gives us a technique to train a coupling layer flow using a regression objective. For that, we need to train a continuous flow first. So we train a continuous normalizing flow that gives us a defined coupling. We use that to generate training data. And then we can train the coupling layer flow on this training data using regression objective. This leads to a loss of unweighting efficiency because it's a distillation of a model practically. So the unweighting efficiency is reduced, about a factor of 10 here, somewhat smaller factor in the TT bar case. But the model evaluation is 100 times faster. So that solves the inference problem. And then if we combine that, we get a much higher gain over Vegas in the end. for unweighted event generation. So this gives us now an order of magnitude practically. And we calculate the break-even points where it pays off to actually train the normalizing flow and using it for unweighted event generation. And this is now a value that really pays off for a large production campaign. So this is useful. Okay, that brings me to the next topic, which is higher order calculations. For higher order calculations, we use subtraction methods, which gives us negative weights that we have to deal with. And the phase space is separated, so we have positive parts and negative parts, which we see in this example here from an NLO calculation, or I think it's the NLO part, whatever. So we see a positive part and a negative part, and the boundaries are not trivial. So it's not factorized, and this is just a 2D projection. So the actual phase space, it's a complicated mess. So this is really difficult to learn for Vegas, which is with a factorized ansatz. What we typically do is we learn the absolute value of the weights, like shown here, but that only gives us a lower bound on the variance. So we can only do so well. We are practically limited by the cancellations between the negative and positive weights. So we thought we can do better by splitting this into the positive and negative part and learning them separately. And now this is something a normalizing flow can really do. So it learns the boundaries of the positive and the negative part and can represent both separately. And so in the end, we teach the flow where the positive part of phase space is and where the negative part is. And we use this in the stripper scheme, where we developed a Python interface, the C++ code, which is, again, it's just random numbers in and cross-section out. We considered the gluonic channel of TD bar production up to next to leading order, which gives us 11 different contributions. And for each of them, we trained 2 normalizing flows, one for the positive part and one for the negative part. And for the discrete indices given by the sectors of the super scheme and the polarizations, we again conditioned the model to learn these separately. Okay, this is the result for the weight distributions. So we see an NLO part in the top and an NNLO part in the bottom. And we see the absolute value of the weight on the left-hand side, and on the right we see the positive part only and the negative part only. And what we see is that in all cases, we get a much more narrow distribution of weights with normalizing flows. Here, it doesn't seem to make a large difference whether you use the continuous flow or the coupling layer flow. But we have to remember it's also lower dimensionality than before. But at least we see it's a huge improvement in the variance of the weight distribution, and we also get improvements in the maximums of the weights. For the total gain, for the integration of the total cross-section, we end up with a factor of 2 if we learn the absolute integrand, and a factor of 8, so almost an order of magnitude, when we use the positive-negative splitting. This is, okay, we assume the matrix element evaluation dominates, which it typically will, so we did not include the training and inference time, but I think it can be, it's not a huge part of this. And finally, I want to talk about surrogates, matrix element surrogates, and how to use them in an unbiased way. So the event generation cost is driven by low unweighting efficiencies and expensive matrix elements, especially at the high multiplicities. And we've seen that neural network-based surrogates have shown to be very good approximators of matrix elements. But just on their own, it's not too useful for event generation because it's biased. So our idea is to split the unweighting into 2 steps. So we do a first unweighting against the surrogate, which is very fast, but wrong, and which gives us a low efficiency, and then we correct this with the true matrix element in the second unweighting step, which is then slow, but we don't have to do it as often, and the efficiency is very high. So overall, we can gain if we have a fast and accurate surrogate, and if the unweighting efficiency is low to begin with. This is like a simple diagram to show you how the algorithm works. So we start by inputting a phase space point, just randomly drawn. We calculate the surrogate weight, and then we do a first accept reject step. If we reject, we start from scratch. If we accept the point, we have to calculate the true matrix element weight and get this ratio between the true weight and the surrogate, and then do a second accept reject step. So now we have a high acceptance rate, before it was a low acceptance rate. So most of these will actually be accepted. And then if it's accepted, we return it as an accepted event, accepted unweighted event. So first we try to do this with very naive, simple MLPs. Then later we switch to this factorization aware model, which is based on the Catani-Seymour dipoles. So the idea is the network learns the coefficients to a linear combination of the dipole terms. So to the first order, it already knows about the QCD structure, about soft collinear enhancements, and it only has to learn, well, what else is happening in phase space. And we applied this to a Sherpa calculation, multi-jet merged, Z plus up to 6 jets. Merged with Spartan shower, we used a special loss function that optimizes the gain factor. And we found that overall we gained a factor of 11, so again an order of magnitude in CPU resources in a realistic setting. And what these pie diagrams in the bottom show is that if we introduce surrogates, we now reduce the share of the 6-jet subprocesses so far that even the 5-jet processes get a significant part of CPU time, which were basically not visible before. Okay, to conclude, I think ML in event generation is a great match. I've shown that order of magnitude gains are possible in realistic settings, where so far we have focused on Z plus jets and TT bar plus jets. We want to look into more. We need to guarantee unbiasedness, and we need to show that we can gain overall efficiency. For the normalizing flows, we saw that we can increase the unweighting efficiency in tree-level calculations, and for higher order calculations, we improve the integration. We reduce the variance, and our simple interfaces are basically agnostic to the generator. And the two-step unweighting enables us to use matrix element surrogates effectively. And in the future, we also want to look at surrogates for next to leading order and make the whole thing production ready for the high luminosity LHC. Thank you.
All right, thank you very much for the very nice talk. Questions, please. Hey.
Yeah, thanks for the nice talk. So with the surrogate model, I didn't catch how exactly you make it unbiased. Don't you risk completely neglecting certain regions of phase space that you wouldn't catch?
I didn't get the last part, sorry.
Don't you risk just neglecting regions of phase space?
Why?
So if it doesn't pass the accept reject stage,
yes.
Just because if the model is not predicting correctly, right?
Yes. But and that you will find that you just get a very bad distribution of weights for the second unweighting. So what happens then is you get a very low acceptance rate in this step. So the whole thing becomes very inefficient. So in the worst case, you do worse than without surrogates, but it will still be right.
Oh, okay.
You can talk about that later, maybe.
All right.
Thanks for the talk. I had a question about the boundary of positive and negative weights with the normalizing flow.
Yes.
How robust is it to inefficiencies or inaccuracies in regards to learning this boundary? Do you know? Let's say you have a mismatch, or when it's not fully accurate, what happens to the distribution?
So like when the model predicts the wrong sign.
For example.
Yes. Well, you like predicting the cuts wrong. So you just have to reject the event. So it reduces the efficiency overall, but it doesn't break anything.
Thanks for the great talk. Just a suggestion for you for future work. So you've compared to one approach to calculate the scattering matrix element, which is to calculate the full square and then do multi-channeling on a positive definite integrand function. But another school of thoughts breaks down the amplitude in known topologies with well-defined phase-space structure. And for each of these components of the matrix element, generates the suitable phase space.
Like the single diagram.
Right, like AlpGen does, for example.
Yes,
Nobody come across that. Yeah. I think it would be nice if you could do a comparison against those and see how you can improve that approach, because there the shortcoming is that you have negative weights because you have interferences, and you seem to be dealing so efficiently with it. So I think you should try that as well and see whether you can improve that approach as well.
Yeah, thank you. It's a good idea.
All right.
A question on your rect flow.
Yes.
So what most people do to reduce the complexity of DoD is to rely on some self-distillation. So you try to reduce the number of steps you have to do when solving DoD. But your approach seems different.
Yes.
Is it the case, and why didn't you just do distillation?
Well, we need an approach where our model in the end is still invertible. And this gives us this because we just train another coupling layer flow, which is perfectly invertible by definition. If we distill just the continuous flow into a few-step model or one-step model, it's an approximation of exactly integrating DoD. So it gives us slightly biased weights, and we don't want that. Okay.
All right. So no further urgent questions. I would ask to thank the speaker again. All right. We have now Paolo talking about W gamma gamma production at CLG.
Thank you. Okay. So thank you for the opportunity for being here, and now I will discuss our work on W gamma gamma production at LHC. This is based on this paper which came early this year, and this is in collaboration with Massimiliano Grazzini, Stefan Calveit, and Chiara Savoini. This is a brief outline of what I'm going to discuss. So we start with a brief introduction and motivation. So why we actually need next-to-next leading order predictions for such processes, so the Terboson in general, Terboson class. Then I will move to the results, so for W gamma gamma production at LHC, and then I will briefly conclude. Beginning with the introduction and motivations. The motivation has a name, which is electroweak gauge couplings, which we already heard of earlier today, and this is basically motivated by the fact that in order to better understand the electroweak symmetry breaking mechanism within a standard model, we need both precise measurements and theoretical predictions for processes with, in general, multi-boson states in a final state, multi-bosons in a final state. This is in order to constrain the electroweak gauge couplings. Nowadays, we know that linear gauge couplings are well constrained, and we are now approaching, as we already saw, better constraints also on the quartic gauge couplings, which can be extracted by both weak boson scattering, which will not be discussed in this talk, but also from Terboson production, which is, of course, the topic here. And here I'm showing a representative leading order diagram for W gamma gamma production with the off-shell W. And here, as we see already the leading order, we access, in this case, the W gamma gamma vertex. So we already access the quartic gauge coupling for these processes. And this is, of course, needed in order to look for potential anomalous quartic gauge couplings.
And deviations from the standard model are in general can be parameterized in a model-independent fashion within the EFT framework. We start at dimension 8 in order to not introduce anomalous trilinear gauge coupling, since they are already well constrained. This is the general form of the EFT Lagrangian, which we already saw this morning in Julia's talk, and I will not discuss this. So why triboson production? First of all, triboson production with heavy bosons is now measured at the HC, and this allows us to study the quantum gauge couplings, and they provide irreducible backgrounds to, for instance, BH production at the HC, when of course the Higgs boson decays into 2 photons. From the theory side, at next leading order in QCD, they are known to have large K factors, which range from 1.4 for Z gamma up to almost 4 for W gamma gamma, as we will see in the next slides. And therefore, NLO QCD predictions are required in order to size the impact of the corrections to these large NLO QCD corrections. But as we all know, the current bottleneck is represented by the missing loop amplitudes, which are in general not available for such processes, with the 2 remarkable exceptions of triphoton and W gamma gamma, which is of course used in this work. And when they are not available, they can be this absence can be taken by using soft boson approximation, for instance, as done in these 2 papers among all the papers. And even when available, of course, one needs these results to be in a format which is suitable for a Monte Carlo implementation and, if possible, a relatively fast numerical evaluation. And as we will see, this is a non-trivial task at all. Nevertheless, we managed to achieve first NLO QCD predictions for such processes, and we implemented, by implementing the 2-loop leading color QCD amplitudes for W gamma gamma. In general, these are the ingredients of our computation. So everything is implemented in the matrix framework, which exploits NLO to handle purely NLO singularities, the dipole subtraction local method. Whereas when moving to NLO, since we are producing a colorless finite state system, we can use the usual QT subtraction formalism as implemented in this framework. And the required lower order amplitudes, so Born 1 loop and 1 loop squared, are generated mainly using OpenLoops 2, which is our default tool, but also using Ricola 2, mainly for the 1 loop squared for W gamma gamma, which is not available from OpenLoops, but also in order to perform checks against OpenLoops 2. Specifically for W gamma gamma, we have built a C++ library for the 2-loop leading color QCD amplitude, and of course this library exploits the pentagon functions ++ library. Okay, let's move to the main topic. So W gamma gamma production at the HC. So this process has been observed by both Atlas and CMS collaborations at both 8 and 13 TeV of central mass energy. And as I already mentioned, it provides an irreducible background to WH, in this case, production when the X decays into 2 photons. The large NLO QCD K factor, which is known from the theory side, can be explained by 2 effects, mainly by 2 effects, so radiation zero pattern and the opening of a large QD channel, as we will see in the next slides. For this process, we do have 2-loop QCD amplitudes, which became available already 2 years ago now, though in the leading color approximation. And we will try to make an estimate of this, trivial estimate of this approximation. As I already mentioned, these 2-loop amplitudes are implemented in the C++ library, which allowed us to achieve first NLO QCD predictions for a triboson process, which also involves a massive external lag. This is a brief overview of the finite remainder structure, which is given by the authors of this paper. And they deal with dimensional regularization, 4-dimensional external momenta, and everything is the coefficients are parameterized in terms of the momentum twisters. The Berg amplitude, so after we strip all the couplings, assumes for W plus gamma gamma this is this A6L, and everything at 2-loop is expanded in the leading color approximation. Also the 1-loop, but of course the 1-loop can be computed without any approximation. then one can find the amplitudes for W minus gamma gamma starting from those for W plus gamma gamma simply by charge and parity conjugation relations. And the finite reminders, after subtracting UV and infrared poles in Catani scheme, are given in this structure, so the usual structure, namely with rational coefficients and in terms of master intervals, which are written in terms of the pentron functions. Moving to the library we built, the purpose of this library is, of course, to implement the true finite reminders, and this is done at the recognition scale mu r equal to 1, which then can be fully recovered at the end of the computation, of course. And we also decided to rescale the momenta in order to have a better stability, because this basically leads to having all the momentum twistors of the same order of magnitude, basically. As I said in the introduction, this is not a trivial task at all, because one usually experiences large numerical cancellations in this implementation, in this numerical implementation, mostly on the coefficient side. So the pentron function, which is actually should be the most expensive part, numerically speaking, can be kept in general in double precision. Whereas for the coefficient side, we noticed how double precision was never enough. So our default is quad precision for the coefficient, the rational coefficients, and double precision for the pentron functions. In order to achieve high precision, we also need some rescue systems, and in this case I will present a very first naive rescue system, which is for sure not the best possible, which relies first on the fact that, of course, this amplitude must be symmetric by swapping the two photons, because they are identical particles, and this allows us to introduce in this naive rescue system basically the two ratios to Born, so to the Born squared amplitude, R. In particular, are 3,4 and 4,3, where 3 and 4 label the two photons in this case. And then one can apply user-defined thresholds on the number of digits in agreement between these two ratios, and then decide how and if one should promote first the coefficients, since the pentagons, as I said, are very expensive, to octuple precision, and if this is not enough, we can also promote the pentagon functions to quad precision. But this is, at least in the test we performed, this basically never happened. On average, we managed to compute a phase space point in less than 6 seconds for the true finite reminder. And here in the lower right corner of the slide, I'm showing the comparison plot between our library implemented in the matrix framework versus the Mathematica notebook provided by the authors. And what I'm showing here is the number of digits that we have in agreement between the two implementations. And apart from this outlier here, which resides at -1 digits in agreement, which means already the order of magnitude is the wrong one, which is probably coming from the fact that this rescue system can be further improved, of course. We know that we see how the average number of digits, this distribution peaks around 9 to 10 digits, which is, of course, more than enough for a true finite reminder for Fino studies. Okay, moving to the actual results, what we did was to compare against the Atlas paper, this paper here, and therefore we have implemented the same experimental setup. And here I'm showing results for both W plus gamma gamma and W minus gamma gamma, as well as their combination, which is what is actually compared against the Atlas result. So the first thing we can notice is how our result is actually both our NLO and NLO QCD results are compatible with the Atlas stated result, and this is in part due to the still quite large uncertainty, experimental uncertainty that they quote. But coming to the size of the corrections, as I already mentioned in the introduction, in general for this class of processes, and in particular for this process, we have large NLO QCD corrections, which in this case, with this experimental setup, amount to around 3.6, which is in line with the literature, and this can be explained by the opening of a large QG channel, as we will see now, and the radiation zero pattern, which I will explain in the differential distribution part. Moving to the NLO corrections, we find that they add around 23% to the NLO QCD cross-section, and the impact of the two loop, which is again in this case in leading color, on the full NLO cross section is around 1%. In this case, we can try to estimate the impact of this approximation, so treating the leading color approximation as any other approximation along the same line as, for instance, soft boson approximation. And even if we would be missing around 20% of missing subleading color terms, we will still be accurate to up to a few per mil, which is of course very, very good. And here I'm also reporting the impact of the different channels, partonic channels, at both NLO and NLO on the full cross-section for the combined result. And as we can see, most of the cross-section is given by the QD channel, which first opens up at next reading order. And this is one of the two reasons, as I already said, why we have such large NLO corrections. And therefore, the next to next reading order is needed in order to have an idea of the size of the corrections to this large channel. And we see how the picture is basically not changed at NLO, with the QD channel which still gives the most of the cross-section, and then the other channels which open up are quite small. Another important thing is the size of the scale uncertainty band, which is here in this case is the usual 7-point scale variation band, which is reduced below 5% at NLO. And as you can see, as we'll also see in the differential part, the distribution part, basically we start with around, let's say, for the combined 6% at leading order, and then this band increases when moving to next leading order, and this is understood by these large corrections which open up at that perturbative order, and then they go down around 4.5, below 5% at next to next. So since we are applying, we are exploiting a slicing subtraction method, this is not local, this means we have to deal with power corrections in general, and we know how photon isolation, so in this case friction isolation, in general introduces sizable power corrections in the fiducial cross-section. Nevertheless, it was shown for triphoton production in 2021 how the matrix extrapolation procedure allows us to control these power corrections at a level which is around the per mil level. And we show the same here also for W gamma gamma production, which has an even more complicated phase space due to the W decay into leptons. On the left, we have the next reading order plot, where we, of course, can always compare against the NLO QCD result computed using the local Catani subtraction dipole method. And on the right plot, we have the next to next reading order extrapolation plot, and we see how in both cases we have these power corrections very well under control. Moving to the differential results, here I'm showing two representative distributions. Of course, we have many more, but these two are particularly interesting because on the left we have the rapidity separation between the charged lepton and the diphoton pair, and on the right plot we have the PT of the leading photon. In both plots, what I'm showing in the upper panels are the leading order in gray, next to leading order in red, and next to leading order in blue. Whereas in the lower panels we have the ratio with respect to the next leading order. In both cases, the bands are the usual 7-point scale variation bands. And first of all, we can we have a similar pattern to, for instance, P gamma production, in particular W gamma production, which also exhibits this radiation zero pattern, which I will explain in a second, and also sizable NLO QCD corrections, which are in general not captured by the NLO scale variation band, especially in the bulk of the cross-section, and this applies to all differential distributions we studied. So this radiation zero pattern is very well understood from the left plot, and basically it's this large dip which is present in the leading order contribution, which is already washed out by the next to leading order corrections, which add in the bulk, so in this central rapidity region here, I mean, this corresponds to a K factor which is 7.5 in the bulk, so this is a really huge correction. And these effects corresponds to phase space configurations in which, in this case, basically for W gamma gamma production, we have the two photons which are almost collinear one to each other, and then form a particular angle with the W boson in the center of mass frame. Another important thing to notice is again the scale variation band, which, as I already mentioned, enlarges. Basically, it's larger in phase space regions where the real radiation matters the most, and this again is linked to the large QG channel that we have. And finally, as I already mentioned, we have around 23% correction, next to next leading order corrections in the bulk of the differential distributions. Okay, this brings me to my conclusions, which are not there. Okay, but you can imagine what they are. So yeah, I can stop here. It's fine. It's fine, it's fine. You can read them.
All right, thank you very much. So, we have some time for questions.
Yes.
So in this, the table of the cross sections.
Yes.
The 3 which you have there for the last digit is like a numerical error.
Yes.
So it's not the one you assign because of the leading color, but
no, we do not estimate let's say the only estimate we give is this in this green box here.
Okay.
This is because this would be again an uncertainty which is few per mil. So we decide to not add it. But in principle, one could estimate this. Actually, there are the subleading color terms are available upon request to the authors of the paper. Okay. But the only numeric, you can evaluate them numerically, and they are very, very. The evaluation is very slow. So it's we decided to not do it. Yeah. But this 20% comes from I guess from triphoton. Yes, triphoton, because in the first place only the leading color amplitudes were available, and then like after 2 years or so the full color became available, and then they compared, and I think they found something around 20-25%, if I'm not mistaken.
100%. But yeah.
100%?
Yes. I mean, in triphoton it turned out to be 100% correction.
The subleading term.
Yes. But the thing is similar to here, since the two-loop part is very small.
Yeah, sure. This few
the overall impact is relatively small, but it was about 100% actually.
Okay, I will check it again. Yes, thanks. Yeah, the point again is that the two-loop impact on the full cross section is so small that you have them basically under control.
Yeah, so even if it's 100%, it would be 1%.
Exactly.
Okay.
It's few per mils, like some per mil, yes.
Thanks for a nice talk. I didn't quite get what happened to the PDF error. Is it buried somewhere? Did you look at it?
The PDF?
Yeah.
It's in the scale variation.
It's buried in there, yeah.
Yeah, the μF, the factorization scale, yes.
Was this a question about the factorization scale or the PDF dependence? So the PDF uncertainty?
Yeah. I mean, the PDF, you mean varying the scale, or?
No. What error you assign to the fact there are hundreds of PDF sets in the market with different prescription for the use.
Okay. In this case, we're using
next leading order, this scale, that scale, dynamical fits, all that.
In this case, we are directly using an MPDF 40.
Okay.
So we are using that set, the PDF set.
It would be good to check what is the systematic associated to change.
So which PDF set do you think would be like?
I have no preference. Just say there are hundreds out there.
Yeah, sure, but maybe you have something in
so
mind.
One should look at what they predict.
Okay, yeah. In this case, it's an NPF 40. So
one remark. I mean, these calculations are relatively expensive. You didn't mention it, but it's probably very expensive. So PDF uncertainties are typically not calculated directly, but you can infer them more or less from the next to leading order part.
That's not obvious.
No, I know it's not true. It's not correct, but in most cases it's quite accurate, and this is what people typically do. If it's very expensive to do one single run, if you have grids, this can be estimated directly. But I don't think you probably produce any PDF grids from this.
No. Actually, there is like a matrix improvement, which is this pineapple thing. I don't know if you're aware of, but yeah, in this case, it's just using the PDF set they provide.
But I think the main message is that you're already stable at 10 NLO, and with one PDF set, and presumably you would be with any other PDF set. I think that's the main message of your talk.
Yes, I think so.
I don't think that message will change if you change PDF.
No, hopefully not. Yeah.
But you should check how much is systematic then.
All right. Further questions?
Do you use a grid? Or do you compute the tool amplitudes at every phase space point, or you have a grid?
No, we do compute it at each phase space point with the library.
Okay.
The loop, yeah.
Okay.
If not, I have a small question. You were discussing this rescue system to catch unstable points.
Yes, here.
I was a bit surprised about your point 1. Is the smallest ratio to 1? So how does this meant? Because I mean, this could introduce a bias, right?
Yes. That's why in the first place I said that this is for sure not the best rescue system. This is just a choice we made, but I mean the bias shouldn't be. I agree that let's say the ratio which the troop finite remainder which leads to the smallest ratio is not always the correct one. Yes, this for sure. So this for sure has to be refined. This I agree on.
Okay. Then let's thank the speaker again. About next to leading order PS calculations for Swift.
Can you hear me? All right. Okay. Wow. This is big. Good afternoon, everyone. Thank you for to the organizer for the invitation. Maybe let's stay here. I made it, which is the first achievement of the day. But so without further ado, let me jump into the topic. So what I would like to discuss with you today are a couple of new results in the context of SMEFT, including analog QCD corrections and also, in some cases, also partial shower matching. So this is the outline. So I will give a very brief introduction, as I guess most of you know what these topics are about. I'll show you a couple of partially randomly picked examples from recent literature, and then I will devote the central part of my talk to our results, which I think add something on top of what was available in the literature, in the sense that they allow you to also perform NLO plus PS simulations, including taking into account polarized intermediate vector bosons, which can be useful for a number of reasons. And at the end of the talk, if I have time, I will also show you some recent results that are at the edge between SMEFT and the quantum observable business that seems to be trendy these days, and then I will conclude. So here are the two main references. Very quick introduction, very super quick introduction. So as you know, it looks like we are not finding any smoking gun evidence for new physics. Hence, one key idea is to look for hints of new physics, or anyway tensions with respect to the standard model predictions using an effective field theory that in this context is the standard model effective field theory. So what you do is to assume that you are integrating out heavier degrees of freedom that you cannot directly produce, and from the point of view of the Lagrangian, this leaves you with a part to be added to the standard model Lagrangian that is made of non-renormalizable operators built only with standard model fields, and depending on what you're doing, also keeping some symmetries in this potentially huge tower of operators, at least the gauge symmetry, you want to keep it. And the name of the game, armed with this Lagrangian, is to try to constrain these so-called Wilson coefficients in the hope of finding discrepancies. So from the point of view of computing
predictions. You start with that Lagrangian, meaning that when you compute an amplitude, you will have a standard model part, and at least as far as this talking is concerned, a part of the amplitude arising from the higher order non-normalizable operators. This holds at the level of the amplitude. The moment you go to cross-section, you have to face the fact that you can add on top of the standard model prediction both the contribution from the interference between A6 and ASM, but also a priori the contribution from AD6 squared, which is what I denote here with the sigma quadratic, to be contrasted with the linear so-called part of the cross-section that arises from the interference. Okay, I need this detail because it will be useful at a later point. So in order to extract information on these objects that might also appear at the quadratic level if you include the squared of the purely beyond the standard model part of the amplitude, you need to compute not only the standard model prediction as precisely as possible in order to be able to measure this difference sufficiently well, but you would also like to include at least the dominant higher order corrections to the SMEFT prediction. Okay. In the context of LHC, at least so far, this amounts to add at least NLO QCD predictions, if possible, next to leading order. And given the fact that most of these processes have an electroweak nature, adding electroweak corrections is, I would say, these days quite tough. And indeed, it's not there in the literature. Probably it's not urgently needed. There are experts in the room here that can correct me if I say something wrong. Yet, there have been some recent results where at least you can include part of these electroweak corrections in the regions where you would suppose them to be relevant, namely in the high tails of distributions, which is where all this game is being played, typically. So here I will discuss dimension 6, and also, in the context of dimension 6, also dimension 6 squared. So this is a very messy slide that whose details are not really needed to be understood. Just to give you an idea of what is available in the literature, as long as we are focusing on diboson type processes and di-Higgs processes, which is the core of the COMETA action, right? Most of the core. No, the reason why I say this is because there are many other results, especially in the top physics sector, that I have not listed here for space and time reasons, and also for relevance in this context. The short story here is that there are several approaches that you can use. There are some computations being performed within PowerEgg box. There is a high level of automation, at least for an LOQCD plus Parton shower within MATGRAPH, in conjunction with the use of dedicated packages, which is the reason for why this list would have been a priori much longer than what I quoted here. I just quoted a couple of papers where I found some interesting physics results and recent results. There has been also work in updating other one-loop provider packages to include the EFT contribution. Sherpa and Derwig also support UFO models, hence you can perform simulations also in that context. Maybe noteworthy is this result because it's the first, as far as I understand, result where the HELAC group has included also SMEFT effects. And given the fact that HELAC is a one-loop, it's an NLO code which is to a large extent automatic and able to compute many processes, this is certainly something to keep looking. A couple of examples. For instance, for di-Higgs production, the group of Gudrun Heinrich and collaborators has been working on including higher order corrections in the SMEFT context for di-Higgs production. And here is a relatively recent results where they show that now they can include chromomagnetic and all types of four-top operators. This is tough from the technical point of view because given that the Higgs production is loop-induced, adding this correction implies performing essentially a two-loop computation with standard model vertices arising from all these operators. Okay. Here is something that I will comment later on because it's the core of my talk. You can also look at this result by Eleni, Giovanni Pelliccioli, and Hesham from almost 2 years ago. 2 years ago. Where they looked at diboson production, looking at SMEFT in particular with a focus on trilinear or triple gauge anomalous triple gauge boson coupling. Okay. A couple of results. You can see, for example, that for Higgs production, for instance, there are some operators that if you change them in values that to me look big, but I'm not sure, perhaps in this context this is not totally excluded yet. I don't know. It is. Okay. Anyway, the point here is that there are many operators that you can play with and get NLO QCD results as an accuracy, also mentioned in Partner-Schaller. Okay. What is interesting here is that they have also implemented the running of the Wilson coefficient, which is something that not always is included in these computations. Here instead is a result from Eleni and collaborators, which I find interesting because it tells you that if you look to differential distributions, you can constrain, for instance, the triple gauge boson operator more than what you would be able to do by looking at inclusive observables, inclusive cross-sections. Maybe not surprisingly, but still, that's, I think, a good motivation for why these tools are useful, because they allow you to constrain better the SMEFT operators. So here is now the part that I wanted to discuss related to my work, recent work, mainly with Giovanni Pelliccioli, but also with other people from Munich. So what we focused on was to compute SMEFT prediction for polarized vector bosons. The reason why this is interesting should be relatively straightforward. Longitudinal polarizations are the leftovers of electroweak symmetry breaking. Hence, by being able to measure, ideally speaking, cross-section for longitudinally polarized vector bosons, you are more likely to study the core of electroweak symmetry breaking with respect to when you do it on a more inclusive level. And it's also interesting because in principle you are more sensitive to new physics effects. In the ideal situation, you would do this for DBS. The boson production is much more abundant and also easier to measure, hence this study. Having a tool capable of computing NLO plus PS corrections for polarized boson is also interesting because it's a tool that in principle would simplify the job of Atlas and CMS people involved in this type of analysis that typically they use a template fitting strategy to extract polarized cross-sections by means of several steps of increasingly complicated approximations in order to correct a computation that was not polarized in the first place. Here, you would have a tool that does that from scratch. How does it work? Well, first, the overall picture, which is the one that I have already mentioned. So we included in the software all these operators from the point of view of the plots I will show, and also from the point of view of what is the allowed value for the Wilson coefficient in front of all these operators. What matters more are the trilinear gauge boson coupling, the CP odd and CP even. So if you want to compute something with polarized bosons, you better be in a situation where it makes sense to talk about polarized bosons, meaning that from the theoretical point of view, such objects should be on their mass shell, which is not what you measure. Hence, a chain of approximations that can be well justified also from the theoretical point of view. So first of all, you have to discard the non-resonant diagrams, which is a very violent thing to do. And in order to keep gauge invariance within your computation, there are strategies. You can either work in the narrow width approximation, or you can work in the so-called double pole approximation that allows you to retain kinematical effects having to do with the off-shellness of these bosons and gauge invariance. Okay? In order to do that, you have to come up with mapping that need to be used while you perform your computation. And this is a strategy that is known since a while. The other thing now that we can talk about objects that are polarized is to see how different polarizations do contribute to the amplitude. In order to do that, you can decompose an a priori unpolarized amplitude as a sum of polarized amplitudes, and when you square such object in order to compute the cross-section, you will have a part of the result that you can interpret as probability to produce one, or in this case two bosons with a given polarization state, plus a term which is an genuine interference. Polarization states that are the objects that you need in order to decompose the amplitude are, by definition, not Lorentz invariant. Hence, all this approach requires you to fix a frame where you first define polarization and second measure observables, which typically is the diboson rest frame for a number of practical and also theoretical reasons. Recola 2 is a provider of amplitude that is capable of producing such results, and put together within an extruding order integrator allows you to get NLOQCD results. This is a slightly too technical slide, which is there just to remind you that from the theoretical point of view of an extruding order computation, you have to perform two intermediate mappings in order to be sure that first you preserve gauge invariance, and second that you preserve infrared cancellation. And this has been achieved, particularly thanks to the work of Giovanni and Giulia that was performed before, that was in the standard model, and it was an earlier work with respect to what I'm talking about here. Such code and computation has been validated with the results for unpolarized cross-section produced with matter 5 by Lane, Giovanni, and Esham. And here you see only 3 lines because there are 6 of them, but pair-wise they are totally completely in agreement. From
A relief. A relief.
A relief, indeed. Well, Joanne is very serious. Me too. I try. You can check how good the approximations I discussed are, for instance, by comparing this double pole approximation with respect to the full results. And long story short, in the region where you would expect such approximation to work well, namely when you are sufficiently close with your kinematics to the double resonant configuration, you get similar results, not only for the standard model result, but also if you add SMEF effects. And by thinking about the helicity structure of what happens in this computation, you can also understand why in some high energy region the difference between the full of shell result and the polarized double pole approximation result is. Namely, you see that here there is a non-negligible difference having to do, whereas for the linear term, so without adding the quadratic term, you get a rather good agreement. Which has to do again with the fact that if you only have an interference, there is an helicity suppression rule that essentially brings the helicity structure of the standard model result very close to the one of SMEFT at linear accuracy. And here you can see some more end of the simulation chain result having to do with NLO QCD correction and NLO plus PS corrections. And by performing this computation, you can, for instance, realize that there are some helicity structures that are not affected at all by SMEFT contribution. And this you can see from the fact that there is no red line here and here, which is the contribution from SMEFT associated to the doubly longitudinal polarization. And you can check analytically that this is expected. And why is this interesting? Because if you have a computation like this, such effect will propagate through all the studies that you want to do, including using such tool to produce events to perform a template fit. And there are also interesting effects arising from the fact that some helicity configurations are underpopulated when the WZ system is at rest. Hence, the moment you have a gluon emission, namely you are at an NLO in QCD, you get a non-trivial pattern, namely a difference between the NLO result, which is the dashed line, and the NLO plus Parton-Shower result. Why is this the case? Because in this region there is a non-trivial contribution from quark gluon-induced doubly transverse object being produced, and this is different if you compute it at fixed order or with some resummation being included. 5 minutes. Okay, then let's do it. So let me use the last 5 minutes to show you something that deviates a little bit with respect to what I discussed, but I believe it's interesting and it's something that can be explored further with the type of tool that I discussed. So spin correlations are, and hence studying angular patterns between typically charged leptons, are interesting because they allow you to enhance the discrimination power between beyond the standard model and standard model results in the paradigm where you have different helicity, different relative weight for different helicities if you add BSM insertions, SMEFT insertions. This you can also interpret and think in the context of entanglement measurements. I don't want to enter too much into the technical details here, also because it's a new way of thinking also for me. The point is that there are some observables that allow you to test how much a system is close to be, for instance, in a pure state. And such observables, at the end of the day, are linked to spin correlation measurements, as I will try to discuss in the next couple of minutes. Okay, so for instance, if you have a situation like this, a generic amplitude or squared amplitude cross-section with an intermediate vector boson decaying to leptons, what you can do is to measure the angles of the objects here, and given that this is a spin 1 object, you can decompose the cross-section using spherical harmonics. That's at the bottom line of the discussion. Not only you can do this, so you can measure these alpha coefficients. X is generically denoting all the observable dependence that does not have to do with the angles. But you can also realize that this system, this cross-section, or this ratio of cross-sections can be expressed as a product of a spin density matrix having to do with the production quote-unquote squared amplitude times the quote-unquote squared amplitude for the decay. Okay? And this spin density matrix can be decomposed with tensors having to do with the fact that the intermediate object, in this case, by assumption, was a spin 1 object. Okay? Pay attention to the fact that rho now can be reconstructed by means of the alpha coefficient. That is something that you can measure. This can be extended to a system where you have two vector bosons, as what I've been discussing so far. And the formula, the equations are slightly more complicated, but if you stare at them and you compare with the previous slides, it's not difficult to realize that they are a straightforward, quote-unquote, straightforward extension. Now, the trace of rho squared, again, rho is something that a priori we can reconstruct by means of angular measurements, can now be computed, okay? And rho being a spin density matrix, its trace is such that it gives us information about how close we are, for instance, to being in a pure state. Not only that, by ordinary quantum mechanics, you can verify that the trace of rho squared must be between 1/3 and 1 if you have a single object decaying. Okay. Now, it so happens that everything works well if you go through the exercise of computing rho and rho squared and the trace of rho within the standard model. If you start to add SMEFT contributions linearly and quadratically, then you have to be careful. And in particular, it can be verified both semi-analytically and also numerically, as I will show in a second, that the trace of rho squared, yes, if you are only computing it, keeping the standard model and the linear term only without the quadratic one, violates basic quantum mechanics, to make a long story short. Okay. For example, the trace of rho squared can exceed 1, and this is not possible. It should not happen. So what do you learn by this? You learn that if you want to use this type of observables to at least this is our current understanding. If you want to use this type of observables to infer something on properties of SMEFT operators, then for sure you have to be careful, because if you are not careful, you use concepts that are not making sense as they are supposed to. Okay? So this is a bit abstract. What you can check, for example, is that if you, again, here is WZ production, I change the Wilson coefficient associated to the triple gauge anomalous gauge boson coupling, and the further away I go from the standard model, the more likely it is, and eventually it will happen, that I go outside the gray area if I only compute the SMEFT results keeping the linear terms, which is depicted here with the acronym SMEFT6. If you include NLO corrections, things can even can improve a little bit from the QCD point of view, but still, if you have a result where the trace of rho squared for a given intermediate boson, or also for the whole system, exceeds 1, you are in a region where your rho spin density matrix is ill-defined. And this also has an impact on some of these quantum observables, such as the concurrence, which is a marker of quantum entanglement. by purely theoretical considerations, this number should be between these two boundaries, and what you can check is that if you use SMEFT only at linear level, these two boundaries do intersect. So what should have been stayed always higher than the other one get flipped. Again, a sign of the fact that you are doing something wrong. Okay, and with this, I think I can stop just to show you that you can play more visual games. For instance, this is something that we are exploring with the student. You can check what happens if you vary simultaneously the CP even and the CP odd SMEFT couplings. And again, if you are in SMEFT hypothesis, you don't exceed 1. Here instead you do. And I think I can avoid reading the conclusions, and I'm happy to take questions.
All right, thank you very much. So, questions, Richard.
Hi, Manuela. It's good to see you. You gave a nice talk, and I'm wondering if you can jump to slide 11. I have a comment or two, and then a question. So it's not just comment, or maybe 12, and where you go, or this maybe go back where you were saying, talking about the narrow width approximation, the double pole approximation. Maybe it's 10. Oh yeah, no, it is here, 11. Okay, so there's an overstatement here, and I want to clarify this because this has been going around now for a little while. You don't have to be on mass shell to define polarization, to have a good meaning of polarization. For example, deep thin elastic scattering and condensed matter systems, things are off shell. Now, what does become very difficult is to make the correspondence between polarization or an angular momentum state and the underlying Feynman graph. I think you illustrate this well in your in the red X, but you don't have to be on mass shell. That's an important statement. That's what we actually teach. If you go through Weinberg, this is an important point. The other bit is to retain gauge invariance. There's a third option. It becomes more process dependent, but if you're able to organize the cancellations, the gates cancellations correctly with the Goldstone bosons, or at least impose hard enough cuts to remove these other diagrams, you don't necessarily have to impose these approximations from out of the box. This is what I did with a couple other people. Now that's the comment or two. Now the actual question is whether or not you guys, since you guys are working also with Julie on the on polarization, any plans to extend the polarization to also top quark decays, W's from top quarks? You have all the machinery for it.
So, are you referring exactly to what? To bar?
TD bar or even single top. I think single top would be particularly interesting, having polarized predictions for single top or TD bar plus SMEFT at high precision because you need the QCD corrections for TT bar.
I'm not doing it.
Any plans for this? Because you guys have the resources and the talent.
I appreciate the comment. Yeah, you're right.
All right, no plans. Okay, got it.
All right. Okay, further questions? Elia.
I actually wanted to understand a bit better this thing of the race you were mentioning. The basic question is this problem the same thing as the cross-section can go negative? Is this on the same level? And if the coefficient is small, then it's okay. Or is there something?
I think it is, morally speaking, probably at the same level, but technically speaking, I'm not sure I would say it's the same, because there is no cross-section here that becomes negative.
No, but I mean, I'm not saying that one implies the other, but I'm saying it's like, is it a problem in the same way? So like, when you have pure interference, you also find non-physical results. They're not necessarily the same configuration, but there are many things that can go negative because basically you're only truncated, so you're not taking a full squared amplitude. So for instance, the cross-section can go negative, but that only holds if your Wilson coefficient is outside the regime of validity of DFT, basically. Because if the coefficient is small, then the cross-section is positive. So I'm wondering if this is something similar, that like within the power counting, stuff is physical, but then if you push it to large coefficients, then you can find non-physical things, because you don't have a complete amplitude square.
So, okay, thanks for being very precise in the question. So, I'm not sure in this right now I would be able to make a statement on which I can be very solidly confident. In the sense that, I mean, yes, at the end of the day, this comes out of the fact that an object like this is not positive semi-definite.
Which is the same kind of problem.
So in this sense, I would say that it is similar. I'm not sure if there is a deeper connection. Okay.
I'm not saying that one implies the other, it's just that they have a similar.
In a way, yes.
Okay.
I think the origin is for sure similar, but I think you might be getting more like into trouble with this one, like in the sense that like you might violate things faster than what you would do if you just looked at the cross section.
It's a stronger constraint, basically.
Which is the reason for why our current statement would be that, Stockholm said that if you are tempted to use this in order to put a stronger constraint, maybe it's not a good idea. You see what I mean?
I agree.
Right? But this is a matter of debate, if you wish.
Oh, okay.
Thanks for a nice talk, Emanuele. Can I ask you something on slide 6, please?
6.
And apology if you mentioned it, I had to leave to pick a call. No, sorry, it's where you had the PT distribution for the polarized.
Maybe this
Look
one.
6 on the web.
16. Look at 16.
I'm sorry.
Yeah, because your plot is hiding.
Yeah, that one. Ah, that's it. Okay, sorry. I didn't notice that.
If this was the only problem of the day.
Yeah. Yeah, as I said, I left the room at some point. So, what's the error on the plots at the top, which means what can I see of the effects at the bottom?
So come again, sorry.
What is the systematic error on each of the curves at the top, so I know whether I can see the effects that you're showing at the bottom?
So here it's not shown, you are right. It's not shown for clarity, but your question is of course relevant. So I don't have a plot. You are talking about the theoretical uncertainty scale variation.
Yeah,
like this.
Whatever you want to put in it. The band around the central value at the top.
These lines would be maybe not in every single phase space point distinguishable, because this is now okay. One
that I can buy. My question is different. Once I put an error on, say, the green plot above, and you tell me that if I put in my SMEF effect, right, I get a correction to that average of 20%. Can I actually see it? Or the error on my starting distribution at the top is larger than that?
So you are asking what is essentially the theoretical uncertainties, for instance, of this plot, because this is the ratio. This is the ratio between SMEF and standard model.
No, I'm asking whether the effect of the SMEF are living within the error band of your QCD and LO or not. That's the question.
I don't know.
Well, they live outside in the tail.
In the tail, yeah, I can buy that probably. Yeah.
I think it's like 5% in OQCD, and so
this was the what I had in the back of my mind. The reason why I say I don't know is because I don't have the plots to show.
Okay. It would be nice to know where you can start seeing the effects.
You're right. Yes, we should.
All right. Finito?
The plots might be in the paper.
Okay.
And for simplicity here, the uncertainty bands have been removed.
All right.
I don't remember if we have all the uncertainty bands for all the lines.
Okay. I would say that thank Emmanuel again and all the speakers of the session.
Series of 7 short talks, so we have a limited amount of time, so I will not talk much, and I will ask you to keep the time. But then Christoph will talk us about electroweak PDFs at work.
Thank you very much. I will try to keep this talk short, even though the topic is quite broad. I'm going to talk about electroweak PDFs. This work was a part of my PhD and also subsequent work with the people mentioned here at this slide. I want to start my presentation with a short introduction to this business of future colliders. I think we haven't heard it yet today, so we know that now we are working on some proposals. Here I mentioned some of them. The results of this work might be applicable to all of these machines, even though I think the muon collider is the most interesting because we are really talking about the multi-TeV regime here. Why VPF is interesting then? I think we know that, but just to give you some formula is that if we look at these two processes, so we have VPF production of some particles versus annihilation, and then production by annihilation. Then we have this scaling, which you can see here on this slide. So the ratio of the cross section for the standard model VPF process over standard model annihilation process goes like this. So you can see here that we have coupling squared, we have S over mv squared, which is the mass of the vector boson, and then we have 3 logs of S over mv squared. So it's obvious from this that at some point this ratio is gonna exceed 1 because it grows with S, and typically it occurs at the scale of a few TeV. You can see that here in these plots, this is Higgs, well, production of double Higgs, triple Higgs in different channels. The dashed lines are for annihilation processes, the racing solid lines are for the VBF. You can see that typically at the scale of, I should do that here probably, at the scale of a few TeV, we can see that the solid line is higher than the dashed line. And it's a general feature not only for Higgs, not only for for a vector boson sector, but also for top production, for example. So even if you don't really care about VBF, at some point when you want to do some top physics, you need to switch to the VBF picture, and that motivates the usage of electroweak PDFs. But before that, I want to talk a bit about electroweak factorization. You can see a simple process here. Okay, maybe it's not a simple process, but it's an example of a process which is initiated by a vector boson. We don't really care about details of this process. We want to stay as general as possible. And then the idea which we have is that we want to factorize this process into 2 pieces. One of these pieces is some universal structure function which does not depend on the details of the process, and it describes the emission of the weak boson or any boson which we take into account in this approximation or in this description, and the hard process matrix element which is specific for a given scenario. So that's our framework, and now what we want to do is that we want to do some approximation. This actually dates back to 84 and Solidoson's effective vector boson approximation. You can see here an example of this process. So if we assume that we have a weak boson in this propagator line, sorry, I'm not really doing that well with this pointer, but then we can observe that we can write the cross section as for this process FA FB to FA prime X as a sum over polarization of the vector boson, and then we have this integral where we take into account this F lambda V, which is the structure function, and the proper cross section for the simplified process where we have only vector boson initiating with the other leg. And of course we can also do the same for vector bosons in a very similar way to this one. Now, we are at very high energies when we are talking about the muon collider, for example, and then we can also say that we can observe that the single muon can emit multiple vector bosons. The coupling suppression which we get from subsequent insertions of these vertices can be compensated by the logs of the ratios of scales between the energy of the particle and the mass, typical mass for the given process. Also, if the scale separation is large, then these partons can split further, and we are getting to this picture when we don't even have a single emission, but we have some subsequent emissions, and each of these particles can take part into hard process. So it really resembles the situation which we have in the QCD, because we have these multiple emissions that then we obtain multiple logs of this kind. So what we can do, we can try to resum them to get more reliable predictions, and that brings us to the full electroweak D-glab equation, which you can also see here in this slide. So we are basically saying that the variation of the structure functions go as sum over different couplings, and then we sum over different possible interactions, splitting functions for the given parton convolved with the corresponding function. Some special features of this framework is that at the electroweak scales and above these, all standard model particles are activated and they can become partons. I will comment on that in a second. And also, the standard model is a chiral theory, so we always have partons polarized even if beams are unpolarized. Here I'm showing you what I meant in the previous slide. So of course, if we are thinking about the muon interacting at high energies, we can take this muon to take part in the hard interaction, but we can also have this muon split into a muon and a photon, for example. Then this photon can take part in the interaction. Then the photon can split into quarks, and the colored content of the muon becomes activated. We can also have a gluon emission and so on. So we basically have all the particles present in the standard model to be available for interactions at the muon collider. You can see the full spectrum of particles or partons, which can be included here. Also, as I said, with their polarization, we also have some special states mixed for Z gamma or 8Z, which comes from the mixing in the standard model. Great. So here I'm showing you some examples of parton distribution functions for muons at different scales. You can see that at X, so the energy fraction of the muon, of course the muon is dominant with the subsequent contributions of the neutrino, but at lower X's, typically the X's which are available at the muon collider are down to 10 to the minus 2. But even at these energies, we already have the dominance of the weak gauge bosons with the contribution from transverse W's and so on. But you can also see that the quark content is non-negligible if the luminosity is high enough, because it's just an order or 2 orders of magnitude below the other components. Great. So the title of my talk was Electroweak PDFs at Work, and now let me show you a bit of work. So we implemented this framework in Wizard. We hope to publish this soon. So our implementation is almost complete. We want to release that, as I said. We got inspired by LHA PDF, so we are able to handle various PDF sets. We just have grids which can be used for any different variations of the sets if you like. We still have some limitations, but they should not really be dominant for the effects which we are talking about. Here I'm just showing you our syntax. You could not really to make you use it straight away, but just to make you aware that the syntax is pretty easy and pretty user-friendly, if I can say so. So let me show you a few examples of how this works for the muon collider. So here I'm showing you double Higgs production. So we have WW to Higgs at 10 TeV with some cut on the eta. Yes, sorry. Here we are comparing full matrix element to electroweak PDFs in blue and EVA, so just the leading order approximation. And what you can see here is that both describe the full process pretty well, at least at lower invariant masses of the Higgs, which you can see here on the left. On the right, it's a bit more complicated because we have different topologies contributing to these diagrams, and that's why you have these gray curves here. So you can see that this line for ZHH production here, right? So you can see that that's the contribution which is not really captured in the VBF approximation realized in the framework of PDFs. And you can also see that then if we take E minus mu plus collider, then we basically compare perfectly, because then these contributions are suppressed because we don't really have S-channel annihilation. Another process which I want to mention here is TD bar production. You can again see that we get quite a reasonable agreement, and the same issue here in the tails. So we are really swamped by these S-channel topologies, but once they are switched off in the E minus mu plus case, the agreement seems to be much better. It's not really clear which approach. Okay, yes, maybe I will skip that for now. But you can see that the agreement is reasonably well. That the band plot is for the scale variation by a factor of 2, and then you can see that basically for both frameworks, the line agree with the full matrix element calculation for the with the PDF picture. And finally, let me show you the last plot where we try to explore something else. So QCD interactions, so colored particles, colored interactions of the muon content. You can see here 4 different processes. So for example, gluon, gluon to gluon, gluon. That's here in this blue line, and you can see that we get quite sizable contributions. We are above single picobarns at energies accessible by the muon collider. So one has to take into account these processes as well once the project is approved, or if the project is approved, maybe that's the current statement. It brings me to my conclusions. I think we are all convinced any multi-TV collider is mostly a vector boson collider, because that's how the interactions occur. Electroweak PDFs allow to resum certain logarithmic contributions and then potentially improve the description in the collinear regime, and we expect many new results using the framework implemented in Wizard quite soon. Thank you.
Thanks a lot. We have really only time for one question. I don't know if somebody in the room has an urgent question. Go ahead, Richard.
Someone else wants to ask a question. All right. Can you show the distributions you're showing for the TT bar production?
I'm afraid okay, maybe I can.
Yeah, yes. Okay. So what you're saying makes sense, that for the low invariant, when you turn off the topologies, you're able to reproduce the full matrix element, because it's only you're in a good region where you can approximate the effective W approximation, and at the higher, as you go to larger masses, you're also starting to turn on all of the fragmentation contributions. Do you guys have any plans, since this is still preliminary, to estimate just with a naive, to estimate naively the fragmentation contribution and then add it on top of it to see how well you're getting this, and therefore being an estimate of the interference stuff which you would neglect in the factorization picture?
Yes, so it's not something which we want to do right now, but it's also in our plans to do that at some point. Because we had this work in the past on electroweak fragmentation functions, and we also want to include that in this framework, but it's not something which we can do right now or in next weeks. So yeah,
the stuff that I put out last year with Inash, it seems like the naive Sudakov factor works well for the reweighting, but it'd be nice to see you guys do this to see what you guys figure out.
Sudakov factor in
as in for, just
as for parton showers, typical parton.
Yeah.
Okay.
Just as a since you don't have the parton shower, no one has a parton shower. Just as a proxy, just do the full the full matrix element and just reweight it by a naive Sudakov factor.
Yeah, then I think it's something which we can do quite easily.
Yeah, for you guys, yes.
Yeah. Okay. Yeah. Thank you.
Thanks a lot again. So the next talk is a 2-part series, FMS on the lattice, and Georg will start.
This works.
Yeah, there is a quirk if you go back. Try go back.
Okay. So don't go back. This.
No, you can go back, but there is a double.
Okay. Hello, everyone. Thank you for the introduction. Yeah, I would like to start with the first part on FMS on the lattice, where we basically want to investigate the structure of asymptotic states in weak physics. And I would like to structure this talk a bit differently. I would like to start with some recent results and use them motivate the whole topic. Fitting to the last talk, I want to talk about PDFs from lattice calculations. So first of all, the lattice as a method is actually quite nice because we don't need to gauge fix. The problem is, if we want to look at PDFs, is that we cannot go to infinite momentum. So we have to use large, but still finite momenta. And what we basically do is we write down our quasi-PDF as it's given here. So we have now not only the dependence on x, but also a discretized lattice momentum. Then we use probe currents for either 0 plus or 1 minus, depending on a Higgs-like PDF or a W-like PDF. And then the important point, because we are on the lattice, we have to use gauge invariant operators to sandwich the probe current. Why does this still work to some degree? The reason is because the corrections you get are basically of the order of the coupling. Now in QCD, this would be more of a problem, but for weak physics, this is actually quite good under control. And what we get is basically what you see here. This is an example for the W boson PDF in the 0 plus singlet state. Therefore, the error bars are quite large, but what this actually allows us to do, and you can see this here on these black curves, is to fit our result and get a grasp on the form of PDF we will find in the end. We can play this game on and basically do fits for all the momenta we have and see where the function evolves if we go to larger momenta. And what we find in this case is this type of overall form, and this is actually compatible with some phenomenology results. So that is actually quite nice. Now comes the motivational part. I talked about internal structure of W and Higgs, and if you think about elementary W and Higgs, you basically would say, well, they shouldn't have an internal structure. And that is true, but on the lattice we have to do everything in gauge invariant formalism, so we also look at the internal structure of gauge invariant operators. If we would do the calculations again, but now use the real elementary W and Higgs, as it's usually known from perturbation theory, we would get 0. And the reason is because the W and the Higgs in this case are actually not gauge invariant. And this I would like to use to motivate that we should actually think about the W and the Higgs as gauge invariant objects, similar to QCD, where we would all agree that our protons and neutrons are color singlets and the quarks and gluons are elementary states and have color charge and are therefore strictly unphysical. Now, where does this come from and where is the problem? The issue is that standard perturbative approaches always come with some problems. There is a theorem which basically says you cannot break a gauge symmetry spontaneously. You also have Gribov copies which ruin the perturbative BRST construction. But in the end, also it's a gauge-dependent construction. So you could still, for example, choose a gauge where your VEF and therefore the W mass is 0, which is just not what the experiment tells us. Now, how would we avoid these problems? By simply saying, well, we want to use a gauge-invariant approach. And how we do this is we basically require that our asymptotic states are gauge-invariant, and we can do this by looking at composite operators, which have the same global quantum numbers as the elementary fields. Now, one question still remains, namely, why does perturbation theory still work so well? And the reason for this can be explained by the Fröhlich-Marquez-Strachey mechanism, which basically predicts a one-to-one mapping between the gauge-dependent and the gauge-invariant states. So the masses you calculate from perturbative calculations are basically in a one-to-one correspondence with the masses you get if you look at these gauge-invariant objects. But more on this also in the next talk by my colleague Sophie. Now what we are doing is we want basically gauge-invariant objects for the Higgs, the W, and also leptons. And we can do this by simply writing down composite operators, which have now the same quantum numbers, but regarding a global symmetry, which is the important point. And what we can do now is simply put them on the lattice and try to calculate, or not try, but calculate the spectrum. One thing I would like to mention is that we cannot actually simulate weak physics directly on the lattice because we cannot deal with chiral fermions. So what we do is we substitute with a vectorial coupling. And the important point is that for the FMS mechanism, this does not matter because parity violation is not an important part. And the second point I would like to mention is that at the current moment we use vanishing Yukawa couplings, but in the future we would like to extend this and also include the right-handed leptons as well. I shortly want to discuss the plots you see here. So in the first plot on the left, you basically see 3 curves. The blue one corresponds to the 0 plus singlet, so basically the Higgs, and the red curve is basically the gauge invariant W boson. And the green line is now a physical lepton. And what you see here is basically the dynamics of the system is completely determined by this green line. So the subdynamics of the gauge scalar sector do not change at all, only this green curve changes. And this result is actually in favor of the FMS mechanism, because what you see here at very low physical lepton masses, we have a huge mass defect, because this green curve basically comes from an operator which is phi times psi, and you see that the Higgs doesn't change the mass. So this is something you would never see in perturbation theory. It's simply not possible to get this result. Now on the right-hand side, I show another quite interesting plot which also supports the FMS picture. Namely, there I plot leptonium. Now, what is leptonium in our theory? It's basically a meson in QCD, but now for a weak theory, so for SU2. So it's basically an E plus E minus state. And all those leptonium states are above the threshold of 2 physical leptons. And what this tells us basically is that here there are additional Higgs contributions involved, which perturbation theory could not account for, but are well accounted for by the FMS picture. And now lastly, I would like to answer the question, why should we care about this? I told you that there is a one-to-one correspondence for the masses for this gauge invariant approach and the perturbative approach. However, there are deviations if you go beyond that, for example, in vector boson scattering. There you see deviations in cross-sections. More on this also in the next talk. The second point, we do this to deepen our understanding of quantum field theory, because we have to take gauge invariant seriously, and either this FMS picture is correct, or we are missing something. So in this sense, there is a guaranteed discovery. Also, what we are doing has huge implication for future experiments, because we would like to set a baseline for future measurements to avoid false positives for new physics, because what we are doing is still the standard model, but just from a different point of view. And lastly, there are also phenomenological implications, especially when it comes to model building, because if FMS for the weak sector is correct, then this should also be kept in mind when considering other gauge groups with a scalar field and the Higgs effect. Now lastly, let me give you a short outlook. What we also would like to do is look at the PDFs for our fermion bound state, so look at the internal structure of weakly charged leptons. But we would be also interested in doing a scattering analysis, especially lepton scattering. Now those 2 points are extremely interesting when it comes to future lepton colliders. And lastly, what we always have to do is we have to compare our simulations on the lattice with analytical calculations in this FMS picture, because if we don't do this, we cannot distinguish between if FMS is correct or we see genuine non-perturbative features in our calculations. And with this, I would like to thank you for your attention.
Thanks a lot for introducing the topic. Any questions?
Thanks for the nice talk. A very simple question, but if there are no Yukawas, why is it a surprise that you change the mass of the fermion for the electroweak part, the Higgs boson, the W doesn't change? Like, what is the coupling if there are no Yukawa? It's like two.
So first of all,
sectors,
the fermions are still weakly charged, so there is you have a coupling to the gauge bosons. But the interesting part is more that we are looking actually at composite operators. So the operator for the lepton consists of a scalar field and a fermion field. And so this mass defect you create because you go below the Higgs mass, basically, is what makes it so interesting.
Okay, thank you.
Thanks again. So we have Sophie for the second talk.
see. Okay. Okay, so yes, I will talk again about the topic. We're doing lattice simulations of weak physics, and especially I want to focus on this question. So we propose that there is some more complex structure to the asymptotic states in weak physics, and how can you actually use this? How can you account for this in your computations, in your analytic computations? I want to talk about this part and also show how we can confirm this from the lattice. So first of all, I wanted to have this little part with matching perspectives because we have this very particular perspective from the lattice. So first of all, we have this issue that because our simulations, as Georg already said, are naturally gauge invariant, we choose our operators quite intuitively in this more complex way. And the question is more like, are those composite states that we wrote down from our lattice simulations maybe actually the asymptotic states? And if so, what changes analytically? So this would mean, for example, that you replace the gauge variant operators with gauge invariant operators in your calculations. But due to the FMS mechanism, your original perturbation theory reappears, plus some higher order corrections that are due to this additional structure. And we can compare this to the experiment by what Georg already presented, the PDFs and the particle masses, which we can also compute on the lattice. And we can also compute spectral densities and cross-sections from this modification, augmentation of perturbation theory, and compare it to what we can extract from our non-perturbative lattice simulations. Okay, so how does this analytic approach work? As I already said, you write down an asymptotic state. It has to be gauge invariant, so it would be, for example, due to the coupling, due to the writing down with a scalar, you sum over the gauge degrees of freedom. And then you do a gauge fixing and expand. This is analogous with this additional field H there. But now, when you, for example, let's say you want to compute a two-point function, it has to be a two-point function of two composite operators, like in this example. So I'm going to try this. Okay, it doesn't work very well. So this part here, it would be like our two composite operators, two-point function, and then we have a first term, which is the original two-point function of the fundamental non-composite particles plus corrections. And this would be the way this goes. So the first part here, the first term is exactly the FMS mechanism. It's the correspondence. It's saying what regular perturbation theory is just, it works exactly the same as this with this augmented structure, plus some additional effects that are these structural effects. Okay, so one example that I wanted to show you is if you use regular perturbation theory, you can compute the spectral densities from the two-point function as it is written there. So this means this is just how you compute the spectral density from this decomposition. And you write down this two-point function, but you can also examine this two-point bound state, gauge invariant bound state function, which would be the spectral density of this bound state gauge invariant Higgs state. And what happens is, well, in the case of your fundamental spectral density, you get just tree-level and loop corrections, which are denoted by this blob. So let's see, this blob up here. And if you use the bound state, then you get a more complicated expansion here, which also has these tree-level plus loop corrections, but also these phi-square insertions. But from there on, you can just continue with perturbation theory as you know it already. Okay, and what will be the result of this? Well, you get spectral densities that look like this. So this is from this publication down here. On the x-axis, you see the energy, and on the y-axis, you see the spectral density amplitude. And then you have here these colored, so finely dashed and more coarsely dashed and coarsest dashed line here, which are the fundamental Higgs spectral densities. So this regular perturbation theory, but this spectral density will be dependent on the gauge parameter because it's not gauge invariant. But if you compute the spectral density from this complex bound state, then you will get the solid black line like this here, and it corresponds to a gauge invariant spectral density of this bound state. What you can see, and this is one part of the FMS mechanism, is that the pole structure here is exactly the same for any gauge parameter and also for the bound state. Okay, so how can you check this on the lattice? Well, we have a technical issue with the lattice, and that is because we're on a finite volume. We only have discrete energies, so our spectral densities will be something discrete. So what people have invented in order to solve this is that you compute the target continuum spectral density, a continuum infinite volume spectral density, but in terms of a convoluted version. So we convolute it with a smearing function. That means the function is smeared out, like you can see here. So it's very technically challenging to actually do all of the expansions. So you need to first take the expansion, the limit to the infinite volume, and then after you need to do the smearing width that is associated with this convoluting function to 0. But what you can do is you can check it the other way around. So we can compute the analytic bound state function, spectral density, and then smear it with the same function. And this is what you see here. So on the x-axis, you see the energy, this time in lattice units. So maybe you can gauge it in GeV by knowing the mass of the Higgs. And on the y-axis, you see the amplitude of the spectral density. And you can compare so this ribbon is the lattice result with the statistical errors, and the dashed line is the analytic curve that we have computed, or that was computed in this publication down there. Okay, so you can compare it and kind of get an idea that we're relatively close. So we think that we can actually make a statement about this. Another example are cross-sections. So we can compute cross-sections from this augmented perturbation theory approach. And here you can see examples of how we can gauge the differences between the standard perturbation theory and this augmented approach. So on the left-hand side, there is here on the x-axis the energy, and on the y-axis the cross-section, and you can see that here in the low energy region there is some compatibility but statistically significant differences in the higher energy region. And what can also be computed is the tangent of the phase shifts here, which has been done, first of all, the dashed line here. You will see the perturbation theory results, so the standard perturbation theory, the dashed line. And then down here is a fit that was computed, so a function extracted from augmented perturbation theory, and then fitted to the lattice data results. Okay, so what I wanted to stress here is that all that is really needed is a small modification of the perturbative approach. So this is something that you can actually apply, and it will give you the same that you have already, plus some corrections. So any standard perturbative calculation is still valid. So in the lower energy regions, you will just get the same. But we think that there might be small corrections that are associated with the structure of the physical states. And now the point is necessary evidence for this composite structure of the asymptotic states is quantifiable from lattice and analytic techniques. So we can actually use this augmented approach and get corrections that we can compare and measure. And we can also compare this with the lattice and compare it with APT, and we can also compare it with standard perturbation theory. And experimental proofs are actually within reach. So we hope that we will see evidence of this complex structure of the asymptotic states at the high luminosity LHC, or maybe don't see it. And then there are more questions which were already raised by Georg. Do we understand QFT correctly? Or what does this mean for weak physics? Okay, so thank you for your attention.
Thank you very much. Again, time for one question.
Thank you very much. I have a question. So one of the things regarding the other higher order perturbative calculations, do they completely factorize in this approach for your cross-section computation so that you say higher order QCD corrections, you can use them on top of them, of your calculation, or is there some complication?
Higher order QCD corrections.
Because in the end you want to compare to a cross-section, right?
Mm-hmm.
So you need to kind of take into account, say, what's not related to your asymptotic state, but which is...
Well, so when we simulate, we really do the SU2 gauge theory in isolation. So at this point, yes, you're just saying that, like, well, can you decouple this? And I mean, I think this is something that you need to check non-perturbatively, what the interaction is there really in the end. But in principle, you can do the expansion and then have order it in terms. Yeah.
Thank you. Next, we have Eleni on diboson production in SMEF at dimension 8.
So, thanks a lot. So I'm actually replacing Hesham, who couldn't make it. So I will talk about diboson production at dimension 8 in the EFT, and this is based on this paper that came out at the end of last year. So the first question is perhaps what kind of dimension 6 operators enter in diboson production at dimension 6, and here is the list. So of course this depends on the flavor assumption, but with this assumption here we see that we have essentially 11 degrees of freedom which can enter in our diboson process. So the one I will be focusing on is this one here. So this triple gauge operator, which modifies triple gauge coupling. So I will start by looking at the constraints that we get on this operator, also motivated by the fact that the other operators also enter in other processes, also including electroweak precision observables. So focusing on this triple gauge operator, so this is in fact the plot which Emanuele showed earlier today. So these are the constraints that we get if we take the experimental measurement from W plus Z, and then we use the various distributions to constrain the Wilson coefficient of this operator. And what you can see in these results is that the linear and the quadratic bounds are very different. So if we take the next to leading order predictions and we compare red with orange, you see that the red constraints are a lot more stringent than the orange ones, which are the linear ones. So whenever we see something like that, then we start wondering what is happening, and we also need to start thinking whether we are breaking the validity of the EFT expansion, and start perhaps also thinking about higher order operators. So I wanted to also say that this is not the only place where quadratic effects can be large, and this is a comparison of linear and quadratic bounds for quite a lot of operators from a feed that we did 2 years ago. And the difference between orange and blue is telling you how different the linear and the quadratic constraints are. And you see there are also other operators where the two are very different. And this is where we start asking questions. So what does this mean for the EFT expansion and for the validity of the EFT? Should we start worrying about dimension 8 operators, given that these quadratic terms are enter at the same order as the interference of dimension 8 operators with the standard model? And if indeed we want to start thinking about higher dimension operators, what can these operators do on the constraints that we set on dimension 6 operators? So we use boson production as a test case to see whether we can quantify a bit, staying still model independent, quantify what kind of impact higher dimension operators can have on the constraints that we set on dimension 6 operators. So the way we approached this was to focus on dimension 8 operators, which have the largest energy growth. And these, in fact, have been listed in a couple of papers. So I'm writing here the references. So what they've done in these two papers is to essentially write down the structures that one can get at dimension 8, and we end up with a small number of operators which have the largest growth with the energy, and these are the ones we want to check. So depending on which boson process, we have a different operators. Some of them are common in both WW and WZ. And what we want to do is start turning these operators on and see how that can affect the constraints that we were getting before on this triple gauge dimension 6 operator. So first, before doing any kind of fit or marginalization, we can start looking at some differential distributions, and I'm showing some examples here. So the operators are the ones I showed before. They each they have some numbers just to tell them apart. And you can see, for example, here in this PT distribution, what kind of contributions these operators can have. And what one should check here is that for some of these operators, we had to multiply them by, in fact, very big numbers to make them show up in the same plot as the contribution of the standard model and the dimension 6 operator. So for some of these coefficients, we had to multiply them by 100 to make them comparable. And the reason for that is that you see also here on the right, for some of these operators, we have cancellations between different regions of the phase space, which give us very small contributions. This is why for some of these operators, we had to put their coefficients to be 100 to see them in the plot. So if we had to put these coefficients to 100, it basically means that we don't really have to worry about these two operators. Then we also looked at, so the one I showed before was WZ, but we also looked at WW. And what is interesting to see here is that there is one particular dimension 8 operator which I didn't have to rescale at all. So you see this C10 here. Its coefficient is set to 1, and its contribution is in fact comparable to the square of the dimension 6 operator. So given this, this is where we should perhaps start worrying and see what kind of impact turning on these higher dimension operators can have on what we can say about the dimension 6 ones. And in order to do that, we took our distributions that we had before from diboson production, and in addition to this CW which we had before, the triple gauge dimension 6 operator, we now turn on the dimension 8 operators and we marginalize over them. And of course, like when we do this kind of marginalization, we need to pick a prior over the dimension 8 Wilson coefficients. So we allow them to be from -10 to 10. And then what we see in this plot is how the bounds on the dimension 6 coefficient change when we turn on the dimension 8 operator. So what one can see is that this line of 1 is basically when there are no dimension 8 operators. Then we turn them on, and the bounds, of course, as you might expect, they get worse. So by allowing some of these dimension 8 operators to be turned on, we get worse constraints on the dimension 6 operator, the triple gauge one that we're interested in. And what we see is that this impact is in fact larger for the observables which go in the high energy region, which is perhaps what one would expect, because we are really focusing on the dimension 8 operators which grow in the largest way compared to the standard model. So what we see here is that we have effects which reach up to 30%. So when I say 30%, I mean that the bound on the dimension 6 operator can change by 30% when we marginalize over the dimension 8 operators. Then we see that for some of these angular observables, the effects are much smaller, which means that for those, if we want to use them to constrain the dimension 6 operator, we can do it without worrying that much about higher dimension operators. But of course, the constraints which we get from the angular observables, at least with the precision we have right now, are worse than the ones we get from these high energy observables like the PTs and the invariant mass. Then this was for, the one I showed now was for WZ. But then if you remember when I was showing the distributions for WW, there was this operator which had this big contribution. And in fact, when we check what happens in WW, we see a bigger effect. So what we see here is that the bound on the dimension 6 coefficient can change up to 60% when we turn on the dimension 8 operators. And this effect is coming from this one operator which had the big contribution. So this is just to get some idea of what effects we can get. So one might say that 30% is not tragic, but this is something to keep in mind. And then there might be another question that we want to ask, and that would be, can we actually use these measurements to say something about dimension 8 coefficient? So instead of marginalizing over them, can we actually constrain them? And the answer is we can get some information. So we show this in these two operator feeds where we feed the dimension 6 coefficient with some of the dimension 8 coefficients here on the x-axis, and the same here for WW. So what we see is that if we want to do something like this, of course, including as many observables as possible is important, because they start breaking correlations between the different operators. And we also see that some of these angular observables can be important, and this is what is shown here for WW. So then that's all I had. So we've seen that, at least from the diboson process, constraints on the dimension 6 triple gauge couplings are dominated by quadratic terms, which is what motivates us to start thinking about the validity of the EFT. So we've checked what happens when we turn on dimension 8 operators by considering the ones which have the largest growth with the energy. And then we see that the marginalization over the dimension 8 coefficients can indeed change the bounds of dimension 6. And that depends on the scale that we pick, on the prior that we put on the dimension 8 operators, and also, of course, on the observable we're looking at. And as an outlook, I would say that there are more things that one can look at. So even if we stay model independent, which is what we were trying to do here, one can start thinking about positivity, perhaps unitarity constraints, and how this can play a role. And of course, if we want to say more, the only way to do it is by also considering some UV complete models and use this to get a more concrete picture of how big dimension 8 contributions can be. So that's all I have. Thanks.
Thank you very much, Eleni. Time for a brief question.
I have a very quick one. So is this operator the one with more derivatives?
So
the dimension 8 you have considered?
Oops. Here, well, they all have the same. They all have the same counting. If you are asking about comparing between them, they all have the same counting. But we see, so they also have the same growth with the energy.
It's just a matter of elicity and this stuff.
Yes, and also there are some which suffer from cancellations. So some of them, in the end, like even if the amplitude squared grows, or rather the interference between the dimension 8 and the standard model grows, in the end you get something which has like two regions of phase space with the opposite sign, and then you get a small contribution. And this doesn't happen for this O10, and then you get a big effect.
Okay, thanks.
Thanks a lot. So next we have Samuel on partial wave unitarity bounds on CPO dimension 8 anomalous AQGC gauge coupling.
Yeah, longer title.
Sorry?
Yes. Well, I'm gonna be as brief as possible and trying to be understandable because my English is garbage. So, okay. This is a collaboration with Alvaro, which is come to talk other day here, and Oscar from Brazil. This is well introduced in the previous talks, and the interest here is to derive, this is well known for all of us. The only difference is that here we are working with anomalous quartic gauge couplings in order to avoid all the problems from the triple gauge couplings. Yes, in that sense, we are going to derive the limits about the growing amplitudes in order to say how is the limit of the coefficient in order to effective field theory to remain self-consistent without considering positivity in that sense. This is a work in progress also, it's not finished. This is going to be important at the end. Yes, what I say here. Yes, there is now from 2024 basis of anomalous quartic gauge couplings established in order to put all the previous reference in concordance, because there was some misleading things like one says CP even, other says CP odd, one or whatever. In our work we we are extending a previous work of Oscar and Eduardo Almeida, where they work with CP-even and P-even operators of the dimension 8. We are completing with all the remaining ones. About positivities, because we are trying also to put the first complete positivity bounds involving all the CP-odd operators, because previous literature say things about how to derive it or put some examples, but not enlist the analytical relations. Yes. Nice. Okay. Also, we are working only in SMEFT because it happens. Maybe I'm wrong. I do it this. Maybe I like cagao, how it says in Spanish. Doing the homework. I do not find any order before CP-odd operator that has no correspondence with triple gauge couplings. Maybe yes. Who knows? Here is the basis in SMEFT. These are the two CP-even P-odd operators. Mix is some kind of name in order to account that they have two Higgs particles. Here are the CP-odd, also mix, only 6. And here are the tensorial and only involve field strength, so transversal polarizations. Polarization because we are working with partial wave expansion. 2-2 scatterings, not 2-3, not 2-4, not 2n, only 2-2. A convention is Jacob-Wick convention. I'm gonna say on the slide. We are using elastic channels, but the problem is CP-odd cannot allow for elastic channels. So we do some kind of mathematical trick, just diagonalization of partial wave amplitudes that also are at 3 level, of course, and this is important because at 3 level this is simple, are just hermetic matrices. If you choose correctly your helicity basis. Yeah, some remarks, okay. We are working only at j equals 0 and j equals 1 for the angular momentum because, of course, lowest momentum gives strongest bound, and also it's not required to go up because the bounds are well determined within those values of the angular momentum. This is our framework to determine the bounds, one operator at a time. Full operators of one of the given types said before, mixed or tensorial. And the 3 is involving same kind of particles. Later will be more clear the example of what I'm trying to say. I only put in 2 examples because if not, this cannot be read. So just the analytical values depending on S. I choose an energy of 1.5 and 3 teras that also was chosen in the previous work. We are continuing. Some kind of energy for the 2-2 scattering that can be remanded from the 13 teras of the whole process. Okay, downwards, down in the down part, yes. There are the analytical values of considering full all the operators of a given type. I suspect the bounds are the limits are greater because you put more room inside all the other coefficients that are on. Yeah, that was for the CP-odd mix. That is for the CP-even and P-odd, also tensorial. Okay. in that sense are the same. Doesn't change the work done previously. Okay. And here is the third example of the framework. Simple, involving 4 B particles above electroweak. Of course, we are working also below electroweak in the sense of the scatterings of the WW, seed, photon, but it's the same at the end because it comes from the same operator. Also, it's interesting because I'm not a very good mathematician. Maybe there is some stupid, simple relation that allows to say that if you consider only these operators, you get the maximal bounds. You don't need to consider all the tensori at once. Maybe there is some simple, I don't get it now, maybe. About positivity bounds are important because some work from Remen and Roth, and also very, very old work, well, old, it's 2006, also prove that you cannot put, you cannot shut down or shut off, and I'm not very good at phrasal verbs, some operators and putting on other ones, because you will spoil positivity. And the spoiling positivity makes your effective field theory spurious because cannot come from any ultraviolet. So it's very, very important for me at the first principles to put first positivity and also unitarity later, maybe. Or maybe I'm wrong. But for that reason, it's important to add also positivity bounds on top of the unitarity bounds. It's not a problem to only work with unitarity, because if you work with the minimal positivity bounds that are, and understanding also, I think by me, that only minimal in the sense that you are on, ¿cómo es para atrás? This one, yes. Minimal in the sense of only the operators of the same kind of particles. The bounds you get are a bit lower always than the unitarity. Of course, you are mixing two things. Well, cannot interfere maybe, but they interfere. So in some sense, it's only working with unitarity is some kind of conservative. I mean, okay, at the end, when if we get the positivity bounds, we will actualize the results. So yes, I think no sé si se ha entendido. Okay, and these are my conclusions. I think I'm extending. So okay.
Thank you. A question in the room? Shy? Okay, seems not. I don't have one.
Well, it's not necessary. There are just results.
Exactly. Thanks a lot.
Yeah.
It was clear. So next we have Richard on polarization interference in multi-boson production at the IH.
Yeah, I'm totally curious about that triple B stuff. I'm going to be asking you about it later. Does this work? And the laser? Yeah. Not obvious. I swear I have a PhD.
And then to finish, you have to find where the button is, and then you run it, or you use.
Okay, Sam, I promise you, your English is better than my Polish. Renee's Polish might be better than mine at this point, but we need to have a chat. All right, I'll just move along because I have way too many slides. I'm not going to go through all of them, but thank you very much for the invitation. I'm very excited to give my lecture here in the Nobel Auditorium, or the Nobel Building. So I'm surprised no one's made that comment yet. Okay, so I don't need to say why polarization is important. We like it, it's cool, WZ bosons are weird. What I want to talk about are state-of-the-art predictions for polarizations, and I promise it's already late in the afternoon and we have lots to do still today, so I'm going to try to be more qualitative than the hard nuts and bolts and all that stuff. As we had a nice talk by Emmanuel earlier today, there's a modern paradigm, where am I? There, modern paradigm in trying to understand how to make predictions for polarized processes. And usually what people do is that they take their favorite process, vector boson scattering, diboson production, single jet inclusive, and
And then they, when computing Feynman diagrams, they just take this propagator and say, well, hey, this is what it looks like if I were to open up my favorite textbook of Collider physics or Hausen Martin or whatever. And then remember back in the day when you were learning all this fun stuff that there's this completeness relationship. It's essentially the same thing as in introductory quantum mechanics or linear algebra, in which you have a full basis that the identity can be decomposed into an outer product of eigenstates. And essentially that's what's going on here. And then this, and really it was Giovanni and company who had this fun idea, and all of this is stemming from the Lam and Tong papers back in the 70s. But Giovanni resurrected it. And this is and when you replace the propagator here, I'm just going to point with my hands. When you take this propagator and replace it with this combination of polarization vectors, that's what you get in what's we call the polarized propagator or polarized cross section. And there are different generators, and Renee and Giovanni really herded a bunch of cats together to really stress test the different generators and how they were implemented, and things seem to be in agreement. There are small little differences that I think we understand what's the origin. It's really just the implementation. It's understood. But overall, there are these fantastic plots from CMS and Atlas that showing that this polarization paradigm really, really works really, really well. And that's remarkable because there's a lot of subtleties that have been swept under the rug. I mean, very clever people have thought about this, but you know, a lot of details that are not discussed every day. But at the end of the day, because I'm too short, I am going to use a laser pointer. There's this question about what about this polarization interference? You know, because what data is saying is that the unpolarized process is to a good approximation well described by polarized matrix elements. And then as this, we want to know, can we neglect the polarization interference? When is it small? When is it big? When is it really, really big? And when is it just completely nonsensical to just ignore quantum mechanics? And so my PhD student, I feel bad for her. I really just put her through the works of the past 2 years. But we've been really trying to understand this. And we have a much clearer idea that really polarization interference is being driven by helicity inversion and the fact that you have non-zero masses. And because you have non-zero masses, you kind of get this helicity flipping, and then one polarization can actually be accessed to different kind of kinematical regimes, and this is just a giant mess. And if you were to invert this and say, well, let's just ignore the masses altogether, then if you think about, say, W's or Z's decaying into massless pair of fermions, then this is a conserved current. It's conserved current in the sense that the inner product with the momentum vector is 0. But there's a classical analog with electromagnetism about the current being conserved. It's just that there's a source, so it's a little harder to make the analogy. And so the idea is that if you're in this situation, then the transversal longitudinal polarization only sees the transversal longitudinal polarization of the current. Remember, the current is a vector current. It has angular momentum information contained in it. So the current itself has a longitudinal and transverse component, and if you're in this conserved limit, then the longitudinal W will only see the longitudinal component of the current. That was kind of what took a lot of math to work out and to convince ourselves that we're doing things right. And when you actually do the direct calculation, it turns out that the transverse longitudinal interference is odd symmetric under the kinematics, so that when you do the phase-space integration, it essentially vanishes or is quite small. And it's being able to make these last two statements rather concretely and mathematically, that actually being able to write down a formula. That's the new part. And I'm going to show you this in like 3 slides, because what's the timing? Okay, I'm just going to move on.
You have 7 minutes.
7 minutes, all right. All right, so the starting point is something that something that the COMETA crowd probably is bored by this point. A paper that appeared a couple of years ago, and it was to actually to do something really silly and stupid and consider the polarization itself as and promote it to a Feynman rule. We thought this is kind of, I'm also being recorded live. I have to be careful with what I say. It's a great idea. It's a Nobel Prize winning idea. The idea was to say, well, this polarization, this truncated propagator, let's just treat it like a Feynman rule. I thought it was just a nice little convenient trick, but it turns out going through the BRS papers over Christmas break, because this is what I do during Christmas break. There's a small, especially there's a kind of a review paper by Becci in 2014, 2015. it pretty much says explicitly that, when you're doing any sort of calculations with polarizations, the longitudinal polarization should never be treated in isolation, because there are all of these extra bits in it related to gauge fixing that I'm just not going to talk about, but they should be treated on the same level as gauge fixing contribution and scalar polarization, Goldstone bosons, and Faraday-Popov ghosts. And these are really the papers that said this is how gauge theory works. And I'm not gonna argue with these people. And so this idea of saying, well, let's just put polarization on the level of Fermi rules, on the level of, say, Goldstone boson, actually isn't so sensible. This was something that Betty was saying and others were saying back in the 70s and 80s. Okay, so that's a little more on firmer footing than I thought. I accidentally rediscovered stuff. And then, if we're treating each polarized component diagram as a full diagram, then we can talk about polarized diagrams. So then we just take the full unpolarized amplitude. We use this completeness relationship that Giovanni pointed out and say, let's just put this as a linear combination of states, and then we can just do the expansion, do the square. And when you square things, one of the things that took a while with Trina is to realize that these expressions for the polarized propagators that we have here actually have really, really nice analytic properties. So some of the stuff that wasn't shown in February is literally because in March we figured out the last missing piece. And it's saying that, if I have some momentum q, so suppose I'm going in the forward direction, then I can always draw three additional momentum vectors. One that's perpendicular in one direction, one that's perpendicular in the other direction, and then there's a backward direction. And altogether I have four. I kind of need to take a linear combination, but essentially I'm able to build up four orthogonal directions for my momentum. And that means that I can write any tensor as a combination of my four momenta. So example, that's a nice little decomposition. That's the exact decomposition for the transverse propagator. It's just the transverse component. Surprise, surprise. The longitudinal I'll mention in a bit, and then there's the gauge fixing part that we needed to keep track to make sure we're doing things sensibly. And what's totally not obvious is if you, let's see, if I sum up the orange parts, the transverse components here, and this theta bit I'll get to a bit, you do get the matrix. So we do keep track of everything exactly. This theta part is kind of cool because it captures essentially the forward and backward momentum of the propagator. Renee, it's when I was talking to you about a term that goes like momentum over energy or width over energy, that was the term that I was talking about. So that's the term that survives when you take the difference with the double pole approximation. Double pole approximation is a really good approximation, it turns out. What's funny thing about this kind of decomposition is that for the theorists, for the calculators in the audience, I'm working in the covariant gauge, and I'm working in the arc-C gauge or unitary gauge, whatever you want, but this is a structure, and this is a structure that shows up in the axial gauge. The reason why we like the axial gauge is that it makes power counting manifest. All of these, if I'm dealing with conserved currents, all of these momentum factors that are multiplying a vector current are going to vanish. And so that just means I'm dealing with something that goes like mass over energy or is zero altogether. So this shows also that all of this nice real power that we have in the axial gauge is also present in the unitary gauge and arc-C gauge, which wasn't actually known. Well, maybe to other people. Then the step 4 is just chug and plug because we have all the ingredients. So essentially, if I took W plus jets as just an example, and so I can just say, well, let's just assume that I have all the diagrams here. I can calculate this by following whatever's in Hausen and Martin or the Pink book, and then I just do really do the calculation by hand. Just evaluate the current. There it is. That's what you'd see in a textbook. Put in the momenta. Do a little boosting and rotation, and this is what the interference looks like. Now it kind of seems messy until I do a little bit of organization and do a phase-space integration over the outgoing angles up here, and two things happen. One is that if I do the integration over the azimuthal of the outgoing angle, so suppose I have some W propagating here, and it splits into a neutrino charge lepton. If I do the phi rotation, it turns out that there's azimuthal symmetry in one or two bodies splitting. So that means the interference with respect to the azimuthal is going to vanish. If I then consider the polar angle, what's funny is that you actually see that
a left B minus A structure here. It's a forward-backward asymmetry. And what's funny about that is that Giovanni, Emanuele, let's chat about it later if Giovanni ever mentioned this to you. Giovanni and Ansgar, when they were doing their studies of polarization in WW production and ZW production, they found that the interference in WW production, polarization interference, was larger than in ZW. And maybe it's clear to them now, but this essentially says it, that if you have, say, a photon splitting, it's a vector current, so you're not going to get, you have a forward-backward symmetry, and therefore vanishing polarization. If you have the double, it's maximal parity violation, so you inherently have polarization interference there. And if it's Z, it's softer, which explains exactly the results that were observed. Now, the sort of cancellation isn't universal; it's process dependent. For example, in top quarks, what's kind of cool is that the polarization interference, if you were to calculate it for a left-handed top quark and then a right-handed top quark, you find out that there's an exact cancellation. The cancellation is at the 25% level, but it's exact, which means if you start with an unpolarized top quark and it decays, that you can treat the W as a transverse or longitudinal, and the polarization interference is 0 from the get-go at the totally differential level, which has some implications for doing tomography in top quarks, and which, if you were to invert it, if you considered, say, single top quark production through electroweak currents, then this is broken, or BSM. So it's some kind of cool results. So in short, I'm probably out of time, so I'll just leave it here. QFTs are weird. Gate QFTs are weird. We had a lot of fun with the polarization. Version 2, I'm literally trying to submit version 2 to the archive today, and so all of the new results that are here that were not in Graz should be on the archive tomorrow or Wednesday at the latest, depending on if I hit the cutoff. So thank you.
Thanks a lot. We have again time for one question.
I didn't catch. What did you say about single top?
So the polarization interference in unpolarized top cancels exactly at the fully differential level. There's no polarization interference. If you have an unpolarized top decaying to massless final states, a massive W, of course, but this really depends on an exact depends on the fact that you have a left-handed top quark and a right-handed top quark both decaying, and there's an exact cancellation between the polarization interference. So if you start off instead with a polarized top quark, say from single top production, or if you introduce EFT operators to induce the tiniest bit of polarization, you break this polarization interference, or you break the cancellation. It means that if you have new physics or operators that introduce any type of asymmetry, thank you, then you're gonna go from having 0 polarization interference to non-zero polarization interference.
Is it related to the spin analyzing powers?
Absolutely, okay. Absolutely. It means that spin analyzing power is really, really strong. And in fact, you can just, it essentially kind of gives an explanation for why the narrow-width approximation for top quarks works so well. Is that there is no polarization interference in unpolarized top quarks.
Okay.
Thanks a lot again, Richard.
It's the polarization of the W.
So we have
the interference
one last
between
talk.
the longitudinal and transverse W.
So Samuel will talk about the calibration of a transformer-based quark gluon jet tagger in Atlas.
Thank you. Yeah,
you have to push twice.
So let me, at the end, talk a little bit about the experiment, because we had nice sessions for the theory in this short talk session. So today I'd like to talk to you about the covalent jet taggers in Atlas, and also try to explain why they are interested in the multi-boson studies. So let me first start saying, what do we do? So
At LHC, at Atlas, we measure jets, and these type of jets can be initiated by quarks or gluons. These two type of objects are very similar. Their jet structure is very similar, but there are some differences that we can use in order to infer whether a given jet came from a quark or gluon. For example, quarks tend to have a smaller number of constituents within the jet. These tend to be more energetic. On the other hand, gluons have more softer constituents inside there, which is as a result from the Barron shower. And why do we care? And this is where the multi-bosons come in. Is that this type of tagger can be used to distinguish between, for example, DBS processes and GGF processes. It can tag DBS scattering, or it can be also used in the GGF only samples, where, for example, in here where you have H decaying into two taus, and the first associated jet is going to be more gluon-like, whereas in the Z plus jet background, which is the major background for these type of analysis, would be quark-like. So this would also help to differentiate between the background and the signal. So let me quickly just summarize how quark gluon died in the Atlas. The first dagger that was deployed and calibrated was the simple cut-based dagger that just used a number of tracks within the jet to sort of separate the quark and gluon jets. Then we had this BDT-based dagger that used several variables that described the jet as a whole. So for example, the number of tracks, the PT of the jet, or the width of the jet. And now today, I'll try to present you the work where we use the constituents of the jet as an input, the transformer model, and use more information that is available as through reconstructed tracks and colorimeter cells, or clusters. So one major improvement that we did is the increased phase space coverage. It's very important because the previous daggers were only available in the tracker, where in a part of the detector where we have available tracks. This is where we call it within eta 2.5. But this DBF and DBS processes produce these quarks in the fold region. So we wanted to extend it to eta 4.5 so that we also have coverage for these, so that this could be used also for, especially for this type of signals. But here was a slight issue because in the inner part of the detector we have the tracks, and these are very important for us to distinguish between quark and gluon jets. So these are inside of the physical object, but outside there are no tracks. So we had to sort of we wanted to regain the performance, and we can do this by introducing these topological towers or top of towers, which provide more granular information than just the simple colorimeter clusters that are usually used in this region. So here's a slight visualization of how this looks like on the left, where we see that the track is a collection of hits in the detector. Cluster is a 3D sort of clustering of multiple grid, multiple cells in a colorimeter. But tower is basically just summing the grids in one radial direction, and as you can see, there are multiple towers within the cluster. And we can use this information together with a sort of p-flow object, which are again clusters merged with tracks, as an input to transform. And for these, we construct these constituent variables. So this is the simple variables that are constructed from the form momenta of these type of objects, and also some identification whether the given object is charged. So this is 1 for tracks and 0 for clusters and towers. And then whether it is a topo tower or a topological tower, or whether it is a cluster, so the 1 for the towers. And we also have the pairs of constituents used as an input to the transformer. So we have heard already about the particle transformer today, and this is sort of a small extension or enhancement on top of this. So as you know, the transformers use the attention mechanism that exploit this relation between the constituents of the jet. And the particle transformer introduced these pairwise features that can be used together with the constituent features with the aim of enhancing the performance. And with the deeper architecture, we sort of introduce a couple small enhancements that allow us to train deeper models slightly easier, and also that allow us to utilize the interaction features in the attention mechanism more than just using them simply as it is in the parallel transformer by summing. So let's first look at the multi-channel performance. So we see that inside of the tracker, when we compare the DPAR model with a fully connected network. So this is a simple DNN that just uses general features. At the low PT region, there is not a lot of gain, but as we go higher in PT, we really try to use the transformers capabilities that come with a larger context length, and the DPAR performs much better in those regions. But if you look outside of tracker, so this is really when we don't have the tracker information, the towers that we use in here add the performance quite a lot, which is a great improvement. But of course, we cannot really look at just the Monte Carlo, but we also need to look at data, right? Because we need to calibrate this. We see there are some differences in Monte Carlo data, and we can see from the histogram there, especially there are deviations at the ends of the distribution, and we need to correct for these. And to do this, we need to measure the efficiency of the stagger on both round 2 and round 2, around 2 and around 3, and then derive the calibration, sort of correct the efficiencies in Monte Carlo. But in order to do this, we need pure quarter and gluon samples and data. And this is a hard challenge because there are no such processes that would allow us to do this easily at the current scale. So we need to be slightly clever about it. And we start from mixed distributions. So instead of using pure distributions, we assume that we have sort of mixed distributions where the fractions of the quartz and gluons are different between these mixed distributions. And we start from digest processes. And a digest process, we have in the final state two jets. And the one with the higher eta between these two is more likely to be quark. And the one with the lower eta is more likely to be gluon. So this is given by the QG to QG scattering kinematics. Because of the PDF, the quarks tend to be more boosted, and therefore the whole system, therefore also in the final state, they have higher eta than the gluons. So we can write then the fractions or the mixing as as a so sort of sum of the quark and gluon distribution, but we have different fractions for the forward and central distribution in here. And the method that we where we go from the mixed distribution into the pure ones is called jet topics. And here basically we obtain the pure distributions by maximally subtracting the mixed ones. So there is one assumption of this method that needs to be satisfied, and that there is an existence of a phase space region where there is only quartz and where there is only gluons. And if you have a Dagger score, this sort of means that if you go towards 0, this where gluons are more clustered towards 0. So when you go to 0, the quartz are basically non-existent, it's all gluons. And if you go towards 1, you have only quartz and there are no gluons. So this is sort of the assumption is satisfied, but of course we address some uncertainty on this later on. And then by deriving this irreducibility factor and using that to scale distributions, we can subtract this distribution and obtain the pure distribution on the right, as you can see. So, of course, we compare this method to the previously used one, where these fractions are estimated from Monte Carlo, and then you solve for these pure distributions, basically just inverting the linear equations. But as you can assume, it's very Monte Carlo based, and therefore the Monte Carlo uncertainties coming from here are quite large. So this new jet topic method assumes another condition and gets this pure distribution from the mixed ones in a different way that is less dependent on the Monte Carlo, and therefore the dependencies, the uncertainties are reduced with this. And here you can see on the two plots the comparison between the matrix method, the topic method, and there is also topic method without correction. So we need to still do some small Monte Carlo correction in order to sort of recover the performance, because the condition of mutual reducibility is not fully satisfied, but we can do small Monte Carlo correction to address this, and then the distribution match quite nicely. Of course, with this we can then try to measure the efficiencies in data, so we can simply define the cut, integrate, and we obtain the efficiencies for quartz and also for gluon efficiencies, and we see there are some phase space region where quark efficiencies are higher, especially in the mid PT region, and there are also some differences in the gluon efficiencies, especially in the low PT and higher PT regions. And at the end of here, we try to compare the uncertainties of this method. So we of course derive the full uncertainty, so statistical, theoretical, and statistical. We combine these this into the sort of scale factor, which are the correction factors between data and Monte Carlo. That should be around 1. And then when you look at the relative total uncertainty between the matrix method and the jet topics method, you can see there are some phase space regions where the jet topics method really improves the accuracy, or the uncertainties are much smaller. So let me conclude. We've developed this transform-based quadral integer. We've extended the phase space region to cover also high eta regions where it's used in for VBS and VBS processing, where we have these forward jets that could be tagged. We have measured the performance in data using the new jet topics method that allowed us to reduce the calibration, allows us to reduce uncertainties. And we have this calibration ready with the correction factors for both round 2 and round 3. Ready for deployment.
Thanks a lot.
Is there any question? Yeah, go ahead.
Can you study the interplay between the hadronization molecule and your tagger? Because quark gluon jets, they will hadronize also differently, and so there will be some correlation with hadronization tune.
Yes, so we try to look at it, basically comparing different Monte Carlo generators, right? The different Monte Carlo generators tend to have different both hadronization and partner shower descriptions, and there is a quite deviation between these sort of generators. Therefore, it sort of tells you that there is some dependence on the hadronization modeling, right? Because it was trained only on Bithia, but then you can look at Herbit, let's say, there's quite some big gap and difference between these. But of course, we adjust this in 2 ways. First one is also some Monte Carlo because in the collaboration we correct Bithia to data, right? And then we sort of to derive the corrections for different Monte Carlos. We use this MC to MC maps that have been mentioned also earlier for beta-ing. But given that our method is also Monte Carlo dependent, there are some uncertainties, and that maybe I have somewhere that come especially from this one. Here you can look at the uncertainties, and we have the partner shower uncertainty, actually the highest one for the matrix method, but also for the new jet topic method, it's still quite dominant one. Whereas the hadronization uncertainty is not that dominant.
But from the thing you showed before, you would expect like 100% uncertainty because the spread was like plus minus 2.
Yeah, but this was rejection, right? So the resistance okay, go differently, right? So yeah.
Okay, thanks.
Thanks a lot.